Good morning, ladies and gentlemen. My name is Debolina Shakalle. I'm a principal engineer at Intel, and I'm going to be your host for this morning. Hope you all have been enjoying the various events and the conference over here. And we have an equally exciting day lined up for you today with a host of keynote sessions by industry experts, presentations, and panel discussions on various topics related to technology and innovation. So, without much ado, I would like to introduce our first keynote speaker of the day, Mr. Ruchir Dikshit, Vice President and Country Manager, Siemens EDA. Ruchir has close to 25 years of experience in the semiconductor industry, having executed multiple levels of responsibilities in the design and development of ASIC, FPGA, and PCB products. Over the years, he has held various leadership roles and helped customers worldwide define problems and create solutions. Currently, Ruchir serves as the Treasurer and Executive Council member of ISA, India Electronics and Semiconductor Association, and the chairperson of the Bangalore chapter of ISA. Ruchir, in his talk today, System Design X Factor for the Semiconductor Industry, will examine the trends fueling the adoption of SoC design by system companies and how EDA is enabling this long-term growth. Ladies and gentlemen, please welcome Mr. Ruchir Dikshit.
Yes. How many students do we have in this room right now? Well, when in life everybody's a student, but how many of you are going to college right now? All right. Looks like in your classrooms you're not encouraged to raise your hands often enough because I don't see the hands going up with pride. But the reason I asked that question is because everybody who's going to come up here and talk to you, everybody who spoke yesterday, was exactly where you are right now. We all started there. And over time, we did something good, something bad to end up here. So I hope that in a few years, I will see some of you up here where I am and giving a talk just like this to fellow students. So, Debolina, thank you so much for the kind introduction. They shut me off already. But, in the last 2 or 3 years, we have transformed completely, right? We learned new things. We learned how to collaborate. We learned how to work. We learned how to shop in a way that we had never done before. Things changed. The change and the transformation that happened to us in the last 3 years was greater than the transformation that happened in the 10 previous years. Because despite all the tragedy that happened in the world, it did open up a lot of new opportunities. And people like you, people who are in the industry, took advantage of those opportunities and built something for us so that we can move on. So I thought I will talk about that to begin with. And especially 2022 was a difficult year because we saw almost a perfect storm that we had never seen before. We were just all coming out of COVID. In addition to that, we had trade wars heating up. On top of that, we had physical wars. On top of that, we had supply chain issues. And everything kind of seemed to be broken down. It was so bad. The things were so bad that the people who spent their lives forecasting what is going to happen to semiconductor, they had to keep changing their forecasts every quarter. And you can see the same agency every quarter changed their forecast. Finally, in October, they seem to have gotten some handle. And if you look at the consensus, it is about minus 7.4%, which means everybody is predicting that in 2023, there's going to be a shrink in the amount of silicon we ship, in the amount of revenue our industry makes. But like we all know, every cloud has a silver lining. And I'm going to talk today about the silver lining. What are the opportunities that we have in front of us? How can we take advantage of those opportunities, not just for 2023, but beyond? And the thing that is driving us, which is also the theme of this conference, is digitalization of everything. You could be working and servicing any one of those things that you see up on the screen, any one of those industries, whether it is aero, military, industrial, agriculture, whatever is getting digitalized now. And if you look at what is driving this digitalization, is based on sensors, our desire and ability to collect data. Right? Somebody has said data is the new oil. So our desire and ability to collect data starts with it. Once we have collected the data, we have the desire to process it and make meaningful information, take out meaningful information out of this data. Now, all of that data cannot be processed close to where the data is captured. Some of it has to be sent over somewhere else to be processed. So that's why we need high-speed networks to move the data. And once the data is moved, it ends up in a data center to be processed. So these 4 pillars are what I believe are going to drive us forward. And what's underneath all of this is a massive AI ML infrastructure that we're all working on. Now, your students, you should go back and read some of the research papers that were published back in 1960s that have the ML algorithms that we are implementing now. So ML is not new. It's just that now we have the ability to process that amount of data that we can collect. So inside of Siemens EDA, oh, by the way, how many people know that Siemens EDA is what used to be called Mentor Graphics? In case you're wondering what is Siemens, oh, brilliant. So our marketing is doing a good job. Because I've been asked this question, what is Siemens doing in EDA? Where did you guys come from? So we came from there. So we've been tracking about 300 companies who have publicly stated that they are working on an AI ML application specific to a problem that they're trying to solve. And you can see what they are working on. A majority of them are working on voice recognition, facial recognition. But then there are others. People are working on AI ML for biometrics and medical. So there's a huge body of work. And some of you in this room who are working in the industry today might already be working in some of those applications. And the students who are in college, when you get hired, you will end up working on one of these things shortly. So where's the silver lining? Despite all the turbulence, despite all the problems that we see in front of us, we are still going to hit about $1 trillion in the next 5 to 6 years. We are on track for that. And it's not just one agency saying that, both agencies who we all trust to make those predictions are agreeing on that. So that's a good thing. What's going to drive this? Can you guys see the charts from back there? Can you read what's in there? If you can't, I'm told that there are 2 larger screens in the back. If you have any challenges there, just let me know. I can read out some of the things that are on the chart. But McKinsey states that we are going to grow at 7%, despite all those minor turbulences that we see. And where is this going to come from? It's going to come from computing, communication, and automotive. That's where all the growth is going to come from. So the other thing that we track is when you look at an electronic system, how much of that electronic system is actually semiconductors? And if you look at and go back all the way to 1970, till about 1980, 1993, about 8% of the content of a electronic system was electronics. It went up to about 16% from 1992 to 2014. And now we are going to be around 25%. So just imagine all the semiconductor devices that people are working on, each and every one of them is going to add more and more value to every system that we're going to use as a consumer. 25% of the total electronic system is going to be semiconductors. Now this chart talks about what is happening in the automotive industry when it comes to silicon nodes. So the automotive industry is still talking about 90 nanometers because for a lot of applications in automotive, 90 nanometers is good, sufficient enough. But we still see 11% growth over the next 5 years. How many of you have an electric vehicle, 2-wheeler, 4-wheeler? I won't ask for a 3-wheeler, 2-wheeler or 4-wheeler. Be proud. We are all contributing in our one way, right? I have one. Across the world, EVs are getting very popular. And one of the conceptions, which I'm going to call a misconception, that we all have is that the EV is going to drive electronic content in the vehicle. Well, that's a fallacy because if you think about it, an electric vehicle has very few parts that need to be controlled. There's infotainment, yes, but then there is a battery and a motor. So what's going to drive the electronics because of EV is not the electronic content in the car, but the number of EVs that get sold. So we're going to make that money in the volumes. Another transformation that's happening is Gartner predicted in 2021 that half of the top 10 automotive companies in the world will have their own silicon by 2025. Again, another question for you. How many of you believe that Gartner might be right or wrong? How many think Gartner was right? The rest believe that they were wrong? Or you have no opinion? Kind of, could be. The point is, whether you raised your hand or not, you're all wrong. Because not 5, almost all of them have their own silicon programs now. Almost all of them. So in one way, Gartner was wrong. They underestimated what is going to happen in the automotive industry. And if you are working in the automotive industry now, or designing something for semiconductors and automotive, you are in a very good space. So what's happening to India in the automotive? Well, India today is the number 5 auto market in the world. We will be number 3 by 2030. And that's phenomenal. Where were we 10 years back? So from 5 to 3, we're going to get there in just a couple of years. And EV, look at that, 4x growth just in EV market in India. And again, please don't think of only cars when we talk of EV. It's the scooters, it's the 3-wheelers. Right? That's what's driving the demand. In India, there are about 250 companies who are working in the EV space. They are either making their own vehicles, or they're making electronics that goes in EV that controls the EV. One thing that we need to do as industry in India is to solve problems that nobody else is solving. And that's what I say the opportunity for us that very few companies in the world are focusing on are self-balancing 2-wheelers. Now think of how big an application that is for India, where our country runs on 2-wheelers. We don't run on 4-wheelers. And if we can do that, the number of accidents that we can prevent if a scooter through a gyro is self-balancing. So that's what I believe we should be working on. Let's not do what everybody else is doing, control infotainment, connect phone to a scooter. There's no value in that. I talked of sensors earlier. Right? In 2015, we had 1.6 billion transistors connected. Just look at how many sensors we're going to have connected in just the next 2 years. Almost 30 billion sensors. We have talked of IoT for the last 4 or 5 years. What is IoT? It's nothing but a sensor collecting data and sending it to somebody else to deal with the data. So 1.5 to 30 billion in a span of 10 years. Where are we when we look at that? I'm not going to talk to this slide because as you can read what's in the boxes and just imagine if we take our entire diaspora, if we take every little village, every little town, every city in the country, and try to look at what is possible, whether it is healthcare, whether it is predicting what happens to the pandemic, how the pandemic moves, whether it is about where industrialization can happen, whether it is about predicting movement of population. We have this ability and the opportunity to really drive this market. So start thinking about that. After the sense, there's the edge. Why do I say that? Because as soon as we've collected data, we need to make some sense out of the data because data without information is useless. Right? And there are applications where we need to make the decisions at the spot because we don't have time to send the data, wait for the cloud, wait for the data center to tell us what to do. So there comes the edge. And we look at the edge. Again, what I talked about, what is available in India. It's people and it's diversity. And we are just on the brink of data collection. We've just started collecting data. We collect about 10% of data that we have the ability to collect. Once we start doing that, we will need compute devices because there is no way we can transport everything. It's not physically possible to transport everything to the cloud and then wait for the answer to come. So I did a little bit of research myself, and I said, what are the top 100 companies who are working on what is called the edge? It turns out 4 of the top 100 companies in the world are Indian. And they are involved in what you see in the... I'm hearing an echo. Are you also guys hearing an echo? No? Okay, all right. So it's like bouncing off the walls for me. What you see in the center of the chart, it's not just the semiconductor device, it's the entire service that goes around it. It's the facility, it's the software. All of that comes under the edge. So if today we are 4 in the top 100, what stops us from being 10 in the top 100 or 15 in the top 100? Looking at some of the semiconductor revenue, so let me step back a bit. From 2022 to 2023, in that just 1 year, while we were doing and dealing with all these things, automotive and industrial semiconductor consumption grew by over 200%. And that's what's driving. So what I'm giving you is proofs of all the claims that I have made. It's not just things that I believe in. It's not things that I heard somewhere. There is data to back it up. There is the highest growth is coming in from automotive and industrial. Once we have sensed, once we have made some decisions at the edge device and we need to move data, we need 5G. So right in the middle, I'm so happy that our government made the announcement of investing $30 billion to take 5G networks to every single corner of our country, because it goes back to what I said. What if we take these things and start collecting data and giving decisions back to every small little corner of India? That gets possible. And in India, 70% of enterprises have said that they are making some sort of an investment in 5G. These are Indian companies. These are not global companies. Huge potential. The numbers are out there, right? 5G can cause a 1 trillion impact to our economy. 150 to the GDP. That's what just 5G can do, the infrastructure and the services around the infrastructure that we can build. So once we have used the 5G network to push data, then you will need the data centers. And here's the data that tells us, and proof that tells us that the data center market is also growing. So now that brings me to huge opportunity exists in front of us that we can take advantage of. How can we now reliably design the semiconductors and electronics that we have to take advantage of this? And in my mind, it's based on 3 pillars. We have to be able to take advantage of technology scaling. And what I mean by technology scaling is you've heard of 90 nanometers, you've heard of 65 nanometers, and now we're talking of 3 and 4 nanometers. That's technology scaling. As technology shrinks, it gives us the ability to compute more. It gives us the ability to compute faster. It gives us the ability to compute in a smaller segment. How do we take advantage of that? Second pillar is about design scaling. Things that we could do earlier, we are not interested in those anymore. We need to now start solving problems which are more complex, which have more dimensions. And the question that you should ask yourself, the practices that we followed for the last 30 years, are they sufficient to take me to the next 30 years? And system scaling, I'll come to that. How do we start thinking as a system? So I started back in the industry in 1996. And the first few things that I started to hear about, Moore's law is dead. Oh, Moore's law is going to die. Here is data published by Apple. And we've been tracking it all the way from 2013 to their latest public A15 announcement, right, across various parameters. Pick any 2 consecutive years. You will see that the Moore's law is still valid. Pick any. No, sorry, not consecutive. Skip one, 2-year interval. That's what the Moore's law says. Talk of number of transistors. Not just the number of transistors, but look at the performance as well. And you can do these arrows that I drew in your mind. So Moore's law is definitely not dead. But there is other thing that's emerging is more than more. We are not designing planar anymore. We are now designing in 3D, right? So both these things, technology scaling, not just on shrinking the technology, but also taking advantage of our ability to do 3D ICs, is something that is going to drive us to the next level. The one thing that everybody keeps talking about is the cost. So in principle, the learning curve that we talk about is as our ability to produce more silicon goes up, the cost of producing per unit silicon should go down. Cost of producing a transistor should go down. That's the theory of it. And here's proof that it actually is happening. We have been tracking what is called as a semiconductor learning curve. As we ship more and more silicon, our ability to reduce the cost of that unit silicon also is tracking. So our learning curve is alive. I had to put the second graph in there because I am from EDA, and everybody keeps saying, your EDA continues to get expensive. Well, it doesn't, because the EDA is also following the learning curve. Right? Cost of EDA per unit of silicon is also following the exact same curve and is running parallel to the cost of semiconductor devices. Here's data. If you want to have a more passionate discussion about this with me, right after this, I'm available. We can have a discussion there. So coming to what I believe is as we start taking technology and scaling it, we cannot really continue to think the way we have thought before. Oh, I am an implementation person. Oh, I am a logic verification person. Oh, I'm a packaging person. That won't work anymore because every decision that we make at every stage in the design process has an impact on something else either before or after. So a view of the system where we co-optimize different parts of our system simultaneously is going to get critical. If you are in the industry today, you will recognize this graph. The cost of doing a design today is increasing non-linearly as you move from one tech node to the other. Now, you may disagree with the number that I have there. Your research may show something different, but I can bet that if you were to chart, your chart shape will be exactly the same. So if you move the same design from 5 nanometers to 3 nanometers, you're going to have to spend almost $130 million more just to move one node because the complexity of the node has changed. Can we continue to do this? I don't believe we can. Because if we continue on this path, people are talking of 1 nanometer. There will not be enough money in the world to produce those designs that we produce today. We're going to run out of money. Forget people, forget time, forget compute resources, because that's also going to create an issue. So something has to fundamentally change. Again, I go back to 1996. When I started, Verilog and VHDL were the dominant forces in the market. 1996. They are still the dominant forces today. Now, if you talk back to people who've been in the industry, who started the industry before I did, I have heard stories. Oh, we used to design at the gate level. We had to draw gates by hand. People before that designed at the transistor level. Every transistor was drawn by hand. Then we had the ability to design at gate level. And that created a huge non-linear, almost a logarithmic increase in our ability to design. From gates, we came to RTL. Now, earlier, if we could do 1,000 gates a day, writing Verilog allowed us to do 10,000 gates a day. 1996, 2023. We're still doing the same thing. What's the next thing? And that's when I say that we need to raise the level of abstraction. Just like we went from transistors to gates, from gates to RTL, we need to go beyond RTL. Start designing at algorithmic level. Write C code. Because what you can do in C, you can do it in Verilog, but only about 100x slower. Why do we choose to be there? And we have the ability to change this paradigm, and I believe the time to change the paradigm is now. What enabled the transition from gates to RTL was synthesis, logic synthesis. Right? That allowed us to do that. Today, we have the ability to synthesize Verilog from C. Today, we have the ability to go from C all the way to GDS without having to write a single line of Verilog. So if we have it, why don't we adopt it? Because we're afraid. This is the world that we have known. We have not known any world earlier than that, different than that. But in a few years, that's what I believe we will have to do. Otherwise, we have no option. System scaling, I talked about this earlier. And a few years ago, Siemens announced a system called PAVE 360. What is PAVE 360? PAVE 360 is about giving the ability to a designer or a group of designers the ability to visualize and validate and design the entire system in context. So let's say you're making an ADAS chip. Let's say you're making a chip that needs to control the brakes of a car. How do you design it today? Somebody gives you a spec that, hey, these are the kinds of inputs that are going to come, and this is the action that your piece of silicon needs to perform. How do you know that the input you got is correct? How do you know the action you're taking is going to be accepted by the system that actually applies the brakes? So imagine a scenario where you have your silicon, actual RTL code, residing in a system and has the ability to take real-world input along with the real-world input. So let's say you saw what's in the middle. There's your DUT, the RTL that you wrote is taking in real-world camera inputs. But then how do you plan what may happen in the real world? What if your car is running in a situation where it's raining heavily? You have the ability to model all of that. How do you model traffic that you don't see in your input today? So you can model all of this upfront. Give it as an input to the system. And then you can take the action. Do you know you can also model your actuators? You can model the exact brake that is going to go in the car. And now when you combine all this together, as a silicon designer, you will know whether the part you're designing is going to work in the real world or not. No more tossing things over the wall. Hey, this is my design. You take it. They send things back. It's crap. Go fix it. No more Rev 1, Rev 0, or Rev 5, Rev 500. And not just on the hardware side. The same thing happens on the software as well, because software makes assumptions of what the hardware will look like, what the hardware will behave, and when it doesn't, software has to change. So this is the system view that I'm trying to put in your minds. Start thinking system, because we now have the ability. This wasn't available until a few years ago, but it's now. The other thing that, when we start thinking of system, I talked of AI and ML. The basic reason we want to do AI and ML is because we want to learn from what's happening, what has happened before. How much of that we implement in our silicon? When our silicon is designed and sent into the field, how much of the data are we collecting back to see, is it performing well? It got, let's say you, again, I go back to the brake system. You built something that controls the brakes and there was a hack attempt. As a silicon designer, do you know? Would you not like to have the ability to know? I think that's critical. So you build a system which is looked at in 3 phases: design, realize, and then you optimize over the life cycle. So you build an instrumentation into the system. All of this is being done today. If not in your design, somebody else's design. So if you're not doing it, your competitor is. So start thinking about that. How can I compete with my competitor? How can I compete better? How can I design a system which is more robust, which not only I know will work, but I also know will not do things that it is not supposed to do. And it is learning as it goes along. So I talked about a few things. I talked about how bad 20, 21, and 22 were. I talked about how 23 looks to be a year where we will see a small dip. But I wanted to focus on all the opportunities that we still have that are yet unutilized. Because we have technology scaling. That is still with us. We have the ability to scale our design processes. And we have the ability, which is in our control, to start thinking system. And we do that, we'll all be in a good space. Thank you so much, and I hope that I have prevented you from falling asleep.
Thank you, Ruchir, for that really exciting and really engaging talk. And I really apologize for the glitches in between. I would now like to request Mr. Sumit Goswami, Senior Director Qualcomm and a member of the organizing committee, to please join us on the stage and present a memento to Mr. Ruchir. A round of applause, please. Thank you. Thank you, Ruchir. Thank you, Sumit. Our next keynote address will be by Mr. Bruce Weyer, Vice President, Microchip Technology. Bruce is a semiconductor industry veteran with over 35 years of experience. He's a corporate VP at Microchip Technology. In addition to leading the FPGA business unit, he leads Microchip's corporate initiative for the development of IoT and edge compute solutions. In his talk, titled Empowering People to Excite Innovation, Bruce will discuss Microchip's culture of collaboration and their corporate-wide focus on developing a total system solution for clients to excite innovation and accelerate product time to market. Ladies and gentlemen, please welcome Mr. Bruce Weyer.
Good morning, everyone. I am excited to be here this morning, and I'm looking forward to talking about empowering people to excite innovation. If you think about the semiconductor industry, it is the embodiment of innovation. So we all focus tremendously on innovating. Today, I'd like to talk about how do we empower people to innovate. At Microchip, the center point of that empowerment is in collaboration. Microchip has a very broad portfolio of semiconductor solutions. So how our teams collaborate together to deliver total system solutions that can enable our customers to speed their technologies to market, to bring their innovation to market, is very critical. How we partner with other technologists in bringing new technologies to market, like RISC-V and RISC-V ecosystems and development environments. Can you guys still hear me on the speaker? Very good. And of course, how we engage with our end customers to enable them to innovate. Rashir, I thought you debugged this for me. So if you look at Microchip as a corporation, we have a very broad footprint of products. And many people recognize us for our leadership in microcontrollers and the breadth of our analog technologies. But if you look at our portfolio, it's much broader than that. That's an understatement of what we deliver. We deliver PCIe switching technologies that are the center point of storage and router solutions. Our frequency and timing solutions are the heartbeat of 5G and next generation 6G technologies. We have atomic clocks that are the highest precision in the industry for both critical communication networks as well as deep space exploration. Our FPGAs are the most power efficient solutions in the market. We have connectivity of wireless and wired connectivity, including time-sensitive networks that are critical to Industry 4.0 applications. We have silicon carbide solutions that are driving low power solutions in power management. So all these are collectively part of our total system solution. So it really comes back, that empowerment comes back to how do we collaborate and bring this total system solution to market. And what you'll learn is that if you look at this silicon and software and solutions layers, 25% of this entire technology is developed here in India. So how we collaborate at a corporate level and how we collaborate in India is bringing this broad breadth of technology to market. And we're building state-of-the-art facilities and infrastructure to be able to enable to expand our teams here in India by more than 50% in the next coming years. So if you look at our total system solutions and you look at the signage in the lobbies when you came in, we talk about smart, connected, and secure capabilities. But if you look at our total system solution, you realize it's even broader than that. It's sensing technologies, it's power management technologies. But bringing this entire solution to market is critical of how we differentiate our product solutions. So if you look at our Internet of Things, if you look at our go-to-market strategies, we're now exceeding about $8 billion in revenue. So if you look at the market segments we service, each of these is approaching and exceeding $1 billion each. So we look at these markets and say, well, what are the mega trends taking place for us to expand this growth? 5G, data centers, e-mobility. Today I want to dig deeper into the Internet of Things market space. So when we talk about bringing smart to the Internet of Things market, Statistica and other market segment analysts estimate that there's going to cross 15 billion units of IoT products in 2023. So you think about that from the very low end of intelligent doorbells, intelligent fire alarms, upwards through health products, all the way to the heavy industrial equipment that is IoT connected. And we have a very broad footprint to deliver many of these products. Microchip has 150,000 customers, many of them in the IoT space. So our ability to deliver from 8-bit through 32-bit microcontrollers for these very cost-sensitive applications, and upwards through 32-bit MPUs, ARM-based systems, MIPS-based systems, and RISC-V systems, and FPGAs as we approach more into the embedded compute areas. And of course, machine learning. We all think about machine learning and what it means to an automobile and ADAS systems at the very high end. But machine learning actually starts down in maintenance systems, sensors for vibrations that might affect the outcome of product maintenance. We have human mechanical interfaces for automotive applications. And of course, smart vision and advanced AI/ML applications for the 32-bit MCUs and FPGAs. And then how do you connect these technologies? When we think about the wireless and also the wired technologies, it's a continuum from the IoT application into, for instance, an industrial floor space. So time-sensitive network applications, moving that into the data center, we have the connectivity of the switching technologies. Microchip offers the broad continuum of this connectivity for the IoT space. Then, of course, bringing security. Microchip has solutions where we ship over 1 billion security devices per year. Security ICs, full security-focused MCUs and MPUs, and FPGAs, which embody the smart, connected, and security layers inside an individual device. DoD-class root of trust capabilities within our FPGAs. And of course, this is all wrapped up into a total system solution, from silicon and software and solutions layers to bring the full IoT and edge compute capabilities. This simplifies the complexity of our customers and allows them to bring their technologies quicker to market. It drives their growth rates as well as accelerates the Microchip growth as well. So I want to now dig deeper into our FPGA technologies. 55% of our silicon software and solutions layers for FPGAs are developed here in India. So it was very critical back around 2015, early when I was leading the group, I talked to the team and said, do not strive for independent leadership. You need to strive for worldwide leadership. If we're going to continue to drive these complex solutions, we have to lead worldwide from within India. And I think that's the next major stage for the Indian development efforts. So Microchip PolarFire FPGAs are the most power-efficient solutions in the market. They're twice as power efficient as our nearest competitor. This is very measurable, and it's been true for the past 5 years. If you look at our end customer products, the total power consumption due to the FPGAs, they can save 40 to 70% versus the competition. And this has a very profound effect on their ability to innovate. So for instance, if you were in the IoT space and you want to bring a gateway onto your premise, you're probably going to want to have lower cost solutions because of the vast volumes involved with those gateways. So you might want to take out the fans to lower costs. You want to put it in a plastic enclosure. You want to be able to reduce the overall cost of the system, reduce your maintenance costs because you no longer have a fan. It shrinks your operating expenses. We have a customer that has designed a portable ultrasound appliance. It's about the size of an electric razor, and it plugs into your mobile phone, and they can scan your internal organs. They had a prior solution that they could only have that appliance on a patient for 3 minutes before it became uncomfortable to the patient. With microchips, PolarFire solutions, they can assess their patients for over 20 minutes. So that has a very profound effect, saving 50 to 70% power on their abilities to innovate in the market. Along with being the most power-efficient solutions, we also have exceptional reliability. We have zero configuration upsets from single event upsets. So you can take our products deeply into space and not worry about high energy particles changing the state or configuration of the FPGAs. We have security that's DoD quality capabilities built into the architecture. So this is the baseline for which we were looking at when we looked at providing our first SoC solutions on our PolarFire platform. And we decided to collaborate with our strategic partner, SiFive, on a RISC-V architecture. This decision was made back in 2017. And the reason is that we wanted to continue this leadership of 2x power efficiency versus our competition. And that was achieved through having access to the architecture of RISC-V. At the same time, we also said, well, if we're going to have a quad-core processing solution inside this architecture, we'd like to have the flexibility of have the broad input on various applications. So we have an asymmetric processing capability built in this RISC-V platform that allows each of the processors to operate in Linux mode or in real-time mode. And along with that, we thought, okay, now we want to have some flexibility for more application spaces. So we built in a flexibility within the L2 cache. A much larger cache allows us to partition it in different ways for specific application spaces. This is all innovation based on our partnership and collaboration with SiFive and how we developed this RISC-V architecture. So if you look at an application space, so also around the innovation and partnership, the entire ecosystem of the RISC-V architecture has been developed over the last 7 years. If you look at the very robust architecture capabilities, design capabilities around RISC-V, it's very complete now and not a stumbling block at all for the industry. So if you look at this then at an application space and you look at, say you're designing a drone, you could have an FPGA running your Linux operating system and at the same time running real-time operating systems for multiple 6-axis motor control operating up to 100,000 RPM. We can manage the entire video pipeline within the FPGA, including AI/ML, object identification and classification. We can do all these efforts while burning half the power, thus extending flight times, having DoD class security within the device. It's SEU immune, so you can take it into space applications. And we service this product for over 30 years. And imagine the applications in industrial, automotive, medical applications, and in space, all offering these same benefits. At the RISC-V Summit in December, we were very proud to give a preview of our next generation PolarFire 2 architecture. PolarFire 2 will once again double the power efficiency of PolarFire. We're going to offer twice the performance for the exact same power envelope as PolarFire, building on our leadership in that way. PolarFire 2 SoCs, again in collaboration with SiFive, will offer up to 15 times teraops per second improvement versus PolarFire as well. So when you look at the breadth of the solution space for microchip and the collaboration we're putting in place, we see that as a strong differentiator of how we bring our products to market. And that's empowering to excite innovation. Thank you very much.
Thank you, Bruce, for that very insightful address. I would now like to request Mr. Viresh Shetty, member of the organizing committee, to join us on this stage to present a memento to Mr. Bruce. Thank you, Bruce. Thank you, Viresh. Our third keynote address today is going to excite the hardcore technologists and geeks among us today. The talk, which is on the prospects and challenges of the continuous time pipeline ADC, will be presented by Professor Shanti Pavan. Dr. Shanti Pavan serves as the Alexander Chair Professor of Electrical Engineering at the Indian Institute of Technology, Madras. His research covers areas of high-speed analog circuit design and signal processing. Dr. Pavan is the recipient of several prestigious awards, including the Shanti Swaroop Bhatnagar Prize and the IEEE Circuits and Systems Society Darlington Best Paper Award. He is a fellow of the Indian National Academy of Engineering, the Indian National Science Academy, and the Institute of Electrical and Electronic Engineers, IEEE. He is a co-author of Understanding Delta Sigma Data Converters, which received the Outstanding Technical Book Award from IEEE Press in 2020. With that, let's welcome Dr. Shanti Pavan to deliver his address on continuous time pipeline converters, where filtering meets analog to digital conversion.
Good morning, everybody. So my talk is going to be a little more technical. The outline of this talk is as follows, and there's a lot of latency. So I'll give a brief motivation to the topic, and then I'll discuss some fundamental difficulties of prior art. Then I'll talk about the continuous time pipeline ADC, which is the main subject of this presentation. I'll show you some prototype results and conclude. Now, all of us know that whenever you have sampling, you need an anti-alias filter, and many wideband medium resolution signal chains look like this, where you have an anti-alias filter and an ADC that follows the filter. Now, because of the sample and hold operation in the ADC, it turns out that the filter will not be able to drive the ADC as is, so you need to have a buffer or a driver between the filter and the ADC. Now, let's take a quick look at what needs to go in to the filter, or the challenges that one encounters while designing the filter. Nyquist told us that if you have a signal with a bandwidth B, you need to sample at least at the rate 2B. So if you sample at the rate 2B, however, there's a fundamental problem in the sense that the filter you need to design needs to have a response as shown in red, and a brick wall filter like this is impossible to design. So what one does in practice is to sample at a rate which is higher than the Nyquist rate. For example, here if you sample at 1.5 times the Nyquist rate, the filter is difficult to design, but it's possible. Now, if you keep increasing the oversampling ratio, or the ratio of the sampling rate to the minimum rate as recommended by Nyquist, you will find that the filter becomes easier and easier to design. So at an oversampling ratio of 1.5, that's the kind of response you need for the filter. At an oversampling ratio of 2, the filter response becomes gentler and therefore is less difficult to design. Now, a typical oversampling ratio that's used in practice is 2, where that means that the sampling rate is 4 times the signal bandwidth, and therefore this leads to the general conclusion that the application bandwidth of a Nyquist converter's sampling at a rate Fs is about 1/4 Fs. So the key takeaway is that if you want to reduce the oversampling ratio, or if you want to sample closer and closer to the Nyquist rate, you must have a very high order anti-alias filter. All right. Now, so let's take a look at the challenges that one encounters when designing a high order filter. A high order filter is realized by cascading a whole bunch of lower order filters as shown here. As you keep increasing the order, as you can see, the magnitude response falls off at a higher rate, thereby allowing better filtering in the frequency domain. Now, unfortunately, as you keep increasing the order of the filter, we must understand that each filter stage adds noise. So as you keep increasing the order of the filter, while you're getting better rejection of higher frequencies, the noise of the filter keeps increasing. So when you go from a second order filter to a fourth order filter to a sixth order one, you can see that the noise added by the filter itself is going up. The same thing happens to distortion. So again, this picture shows the distortion added by the filter as you keep increasing the order. And as you can see, every time you add an extra filter stage, nonlinearities in each filter stage will essentially add to result in more distortion at the output. So the key takeaway is that a high order filter results in more distortion. So to summarize, if you use a high order anti-alias filter, it not only causes you to dissipate more power, but also increases the noise of the filter and degrades the linearity of the signal chain. Now let's take a quick look at the ADC, which is a Nyquist ADC, given that we are talking about wideband signal chains. A typical way of doing this is to either use a pipeline, as shown here, or a successive approximation converter. I'm going to just use a discrete time pipeline as an example in this presentation. Now, a pipeline ADC basically works on the principle of creating a coarse approximation to the input, subtracting that coarse approximation from the input, and amplifying the difference, and repeating this step all over again, and combining the outputs from many of these coarse ADCs. Now, let's see what goes into a typical pipeline stage. A discrete time pipeline ADC kind of looks like this. The input is sampled onto capacitor C1 in phase phi 1, and in phi 2 it gets dumped onto capacitor C2. Now the problem with having a switch capacitor stage is the following. Whenever you take a capacitor and dump it onto the previous driving stage, the capacitor, which is initially uncharged, now suddenly needs to get charged to the input voltage, and therefore results in a huge spike of current being drawn from the previous stage. And it's very difficult to drive this kind of spiky current without degrading the linearity of the previous stage. And therefore, what people do is to insert a buffer between the previous stage, which in our case is the anti-alias filter, and the switch capacitor stage of the pipeline ADC. Now, the buffer must be at least or more linear than the ADC itself. And it is almost impossible to design that buffer with adequate linearity in the supply voltage that the pipeline operates in. So the buffer is typically designed using a higher supply voltage and oftentimes consumes as much as 30 or 40% of the power of the ADC itself, simply because to achieve the kind of linearity needed to drive the pipeline, it consumes a lot of power. Not only that, the buffer also dissipates power and adds noise. It also adds a distortion of its own. Another challenge in every discrete time pipeline converter is the design of the op-amp. As all of you know, a discrete time circuit is predicated on the fact that the output of every discrete time stage settles to an adequate degree of precision in the half cycle available to it. Now, if you want things to settle quickly, again, it means that the op-amp's bandwidth must be very large, which again translates to higher power dissipation. Further, in low voltage CMOS technologies, it's kind of difficult to get the high gain required to be able to get the DC settling error to be sufficiently small. So to summarize the challenges in the pipeline ADC, the switch capacitor input load is a serious problem and necessitates a high power on-chip buffer, which typically operates with a higher supply voltage. The buffer adds noise and distortion of its own, and the op-amp design is challenging and is becoming increasingly more challenging as technology feature size keeps becoming smaller because the inherent gain of the MOS transistor is decreasing with technology nodes. And a common way of getting higher gain is to cascade stages. If you cascade multiple stages, the amplifier becomes slow. And finally, gate leakage is also something that one has to worry about. The op-amp challenges are currently addressed by extensive digital calibration, which obviously adds complexity and into the whole project. So if you look at the entire signal chain, you have the anti-alias filter, a buffer, and the ADC. And each one of these stages, being in tandem, add noise and distortion of their own. So even though the ADC has got low noise and the filter's got low noise and the buffer designed to have low noise, when you cascade them, the effective noise is simply the sum of the noise powers of all these stages. Now, please note that people have worked very hard over the years to optimize the power dissipation of filters. People have worked very hard to optimize the power dissipation of ADCs. But when you put all these together, it doesn't mean that just because the individual blocks are optimally designed, the chain is optimally designed, as you will see going forward. So, and remember that the higher the order of the filter that you use, not only does the filter consume a lot more power, it adds a lot more noise and degrades the linearity. So in a filter, buffer, ADC chain, even though the ADC is itself designed to be very linear, it turns out that the filter is the one that actually limits the linearity of the entire signal chain. Now, a solution to this is what is called the continuous time pipelined analog to digital converter. Let me quickly introduce you to the basic idea. So the input is processed in continuous time, and ADC1 and DAC1 create a coarse approximation to the input waveform, and the two of them are subtracted to result in a continuous time residue signal. This continuous time residue signal is processed by a residue amplifying filter, and the output of this filter is sampled by the back-end ADC. Now, the contribution of V1, which is the input to DAC1, is cancelled by using the digital reconstruction filter H sub D of Z. So that's the reconstruction filter. And you might be wondering what the delay line in the input path is doing out there. Let me illustrate. So U, shown in blue, is the input signal. The black waveform with a step-like characteristic is the coarse approximation to the input, and that's delayed with respect to the input simply because it takes a little while for the ADC and DAC path to create that replica. So therefore, if you simply subtract U from V or V1, you will find that the residue signal is very large, which is not what you'd want. So if you delay the input signal by the same delay as the ADC1 DAC1 path, the residue becomes much smaller, as you can see in the second picture. Therefore, if the contribution of V1, which is the input to DAC1, through the analog path and the digital path cancel, it turns out that this structure behaves like the equivalent of a filter and an A to D converter rolled into one. Now, here is an example. So that's the delay line, which can be realized using a lattice RC structure. That's the coarse ADC and DAC, which creates a replica of the input. That's the residue amplifying filter. And since this filter incorporates gain, basically the filtered residue which is amplified is what is digitized by the back-end ADC. Now, what are the features of this continuous time pipeline? The input impedance is resistive, and therefore, the challenges with respect to driving a big switch capacitor load are gone. There's a filter which incorporates gain, and therefore, the effective quantization noise of the back-end ADC is divided by the gain of this filter up front. And therefore, the back-end ADC's precision can be a lot lower. Now, because the whole system operates in continuous time, the op-amps no longer need to settle, and therefore, the power dissipation in the op-amps can be greatly reduced. Now, using the same concept, you can extend it to a multi-stage pipeline. So here, the picture shows a two-stage continuous time pipeline A to D converter. And you can see that the effective filter that the input undergoes is basically a cascade of two delay lines which have a flat magnitude response and two filter sections. So you're effectively getting a fourth order filter, assuming each one is a second order stage. Since each of these stages incorporates gain, it follows that the noise and distortion introduced by the second and higher order stages of the pipeline get divided by a large number when referred to the input. The step size of the back-end ADC in this particular example is now larger by a factor of 16 because of the gain 16 before the back-end ADC. So consequently, as far as the signal chain is concerned, it is equivalent to taking the input, filtering it with a high order filter, in this case, a fourth order one, and sampling the backend. So when compared to a conventional solution where you have a filter followed by an ADC, if you can recall the earlier picture, which is not showing here because of Mac to Windows transformation, the noise of the standalone filter is about 3 times the noise of a second order section. Whereas with the continuous time pipeline, remember that the noise and distortion of the second and higher order stages don't contribute to the noise, and therefore the continuous time pipeline represents a situation where you can get high order filtering without the penalties associated with designing a truly high order filter. So in the conventional case, if you increase the filter order, the noise increases. In a continuous time pipeline, as you increase order, the noise remains the same. So this is a fundamental improvement over prior art. The same holds for distortion. I'll spare you the details here, but this shows the simulated distortion of a standalone filter driving an ideal ADC, whereas the second the picture below shows the same situation with the same op amps and having the same amount of nonlinearity, and you can see that the distortion is way smaller. So the key takeaway is that a continuous time pipeline processes a noise-like residue signal and therefore results in lower distortion. So let's take a step back and compare the signal chain when you have a discrete time pipeline versus a continuous time pipeline. As we discussed before, each of the stages in the signal chain, namely the filter, the buffer, and the ADC, all add noise and distortion in equal proportion. Whereas when you have a continuous time pipeline, the gain that you have upfront basically allows you to use a back-end ADC whose step size is much higher, and therefore the design of the back-end ADC is greatly reduced. And because that back-end ADC is much simpler, its input capacitance, assuming it's a Nyquist converter, is also much smaller, and consequently, the buffer can be removed. And finally, even though you have a high-order anti-alias filter, the noise and distortion only comes from the first stage, and therefore, this equivalent anti-alias filter, which is inherently realized by the continuous time pipeline ADC, has less noise and less distortion. Finally, the input impedance of the continuous time pipeline is resistive, and therefore driving the ADC is much simpler than driving a discrete time converter. So this is the list of advantages of a continuous time pipeline versus a discrete time one. And the bottom line is that the continuous time pipeline realizes a filter and ADC combo with much lower power for the same performance. So here is an example of our very first prototype. This was done in 65 nanometer CMOS and realized a 100 megahertz bandwidth converter while sampling at 800 megasamples per second. And for those of you who are used to 2 nanometers and 5 nanometer CMOS technology, 100 megahertz bandwidth turns out to be actually very difficult to do in 65 nanometer CMOS. And we implemented a 6th order anti-alias filter by realizing it with a 3-stage continuous time pipeline. The back end is a 7-bit 4x time interleaved SAR ADC. And these are some details of the filter. I'll skip the details here. And this is the die photo. This shows the measured performance of the converter, which has a dynamic range of about 73 dB. And most interestingly, this is the signal transfer function of the pipeline. And as you can see, beyond 100 megahertz, the response of the A to D converter basically falls off like a 6th order filter, thereby proving that this is equivalent to a filter followed by a high-speed Nyquist ADC. And this is the usual comparison table. And all ADCs are characterized by some figure of merit. And the key point is to realize that the continuous time pipeline, when looked at as an ADC, is more efficient than discrete time converters designed in the same or even better processes. But more importantly, this includes both a filter and an A to D converter. Any anti-alias filter that you had to use for the other converters in this comparison table would have consumed a lot more power to be able to achieve the same performance. And all of you, I'm sure, have heard of this, that those who ignore history are condemned to repeat it. So let me take you through a quick history lesson. This is, on the x-axis, is time over the last almost 50 years. Initially, there was a lot of excitement when MOS technology became possible, and all the filtering earlier was all done using switch capacitor techniques. Then And as you can see, there's a lot of spike in the initial 80s, as shown in red. And the moment people discovered continuous time filters, you can see that the research in discrete time filters has kind of fallen off. Another case in point is delta sigma data converters. Again, people started working on this in the mid-80s, and in the beginning, they were all done using discrete time. And somewhere in the early 2000s, people discovered how to make continuous time delta sigma work. And you can see that the amount of research in that area has taken off after that, and the discrete time stuff has pretty much tapered off. And this is what happened with discrete time pipeline ADCs. And there's been a lot of activity, as you can see, beginning the late 80s. And we are still in the beginning of research in the continuous time pipeline space. And I'm betting that 10 years from now, we will see pretty much the same trend in discrete time pipelines as you will see in continuous time delta sigma and continuous time filters. So, of course, we're all engineers. We know that something that sounds too good to be true is probably too good to be true. So it's not often that you can realize something with lower noise, lower area, lower power, and increased performance. And that's what I've pretty much told you. So there must be some catch somewhere. And the key challenge in realizing the continuous time pipeline is basically making the digital reconstruction filter track the properties of the analog path in a way that's robust to process and temperature and supply variations. And that's basically where a lot of research is going on right now. So to summarize, the continuous time pipeline ADC breaks fundamental performance limits when compared to an anti-alias filter driving a switch capacitor data converter. It's enormously more efficient in area, power, and design effort when compared to a filter plus a discrete time pipeline ADC cascade. And I'm speculating that this will eventually be commonplace, just like how continuous time delta sigma and continuous time filters have replaced their discrete time counterparts. Thank you for your time and attention.
Thank you, Professor Shanti, for taking me back 20 years to my college days. I would now request Mr. Subhash Chintamaneni, Senior Director and ASIC Head at Micron, and a member of the organizing committee, to please join us on the stage to present a memento to Dr. Shanti. Our next keynote speaker is Mr. Noam Mizrahi, Senior Fellow and Corporate Chief Technology Officer, Marvell. He is responsible for the company's long-term technology vision and strategy and oversees its entire span of technologies. Noam, who holds several patents, previously led the definition and architecture of Marvell's unique approach and implementation for scale-out network storage connectivity and AI-based storage solutions. In his talk, An Infrastructure for Scale, he plans to unravel infrastructure architectures in today's mega data centers that is driving the technological transformation in the vehicles we see around us. Ladies and gentlemen, please welcome Mr. Noam Mizrahi.
Hey, good morning, everyone. No, I was always inspired by technology, and I feel privileged to live in an era where technology paints our future in such strong colors. But I better hold on, because technology moves fast, and we move fast. The iPhone you have in your hands today is already so much stronger than the world's #1 supercomputer of just 20 years ago. I mean, in 20 years, we were able to take a room-size, multi-million-dollar computer and shrink it into a handheld $1,000 device. That is certainly a lot to accomplish in just 20 years, but today it seems that we are shooting at even higher targets than that. This is Tesla's FreeDojo supercomputer, purposely built in order to train autonomous vehicle neural networks. And with about 2 hexaflops of compute power and just shy of 30 megawatts power consumption, it's already 275,000x stronger than its year 2000 predecessor. But all of that for what? It's in order to replace a human driver brain that works at approximately 20 watts in a contained 37 degrees environment and is small enough in order to fit our heads. So what would it take us in order to get there? And can we rely on the existing pace that we have been using, maybe represented by the Moore's law of 2x every 2 years in order to get there? Well, probably not. Because the scale represented in this graph that was also shown here yesterday is at a completely different level. And if you look at it, it represents the size of the trained AI models over time. And you can see that over the last 5 years, the size of the trained AI network is an order of magnitude larger than the year before. That's 10x every year. And just last year, Google released a neural network which has 1.6 trillion parameters in it. And if we'll continue by that same cadence, we're expecting to have a 100 trillion parameters network as early as next year. And at the same time, progress has been made also with the training platforms that are the compute platforms that are needed in order to train that. And just recently it was announced that now we can train a 1 trillion parameters network in just 3 days, going down from much more before, which is exceptional. But since we have a path to 100 trillion parameters, it all seems like a drop in the bucket. Because a scale of that magnitude cannot be handled by just beefing up the compute anymore. We should move away from that mindset. It's got to be a holistic approach, an approach in which we optimize and we scale every parameter of the system in order to grow. And the paradigm shifts today from what is known as application-centric, where the most important thing that you possess is the application, and the data is only there in order to serve the purpose of the application. And as a result, the most important thing that you possess is the platform that runs the application. It moves to a data-centric approach, where the most important thing that you have is actually the data, and the application is only there in order to extract the maximum value out of the data that you have. And with data become the center of everything, then how you store it, how you secure it, how you move it around, how you minimize the latency and increase the bandwidth becomes your key for efficiency and your key for scale. In other words, it's the data infrastructure that would enable the growth at that magnitude. And accordingly, I want to point out 3 strong trends and enablers that I recognize as the ones that may contribute significantly to the growth of the infrastructure. And the first one is disaggregation. And to understand why we need it, let's look first on the very common alternative for that, which is a converged platform. And with a converged platform, we have everything we need, all the resources like the compute, the memory, the storage, the network, all together in one place, managed together. And if we want to scale, we just add one more box. Very easy to manage. That's why it's so commonly used. And that works very well if your scale is relatively moderate, and more importantly, if every time you scale in a balanced method across all these parameters. But what happens if you don't know in advance So what happens if you don't know in advance how your scale would look like? Or even more importantly, you want to scale only one of these parameters. Maybe you need to grow your compute resources because you replaced your model and you need more compute to consume it, but you need to run it on the same amount of data, or the other way around, right? What would you do in that case? And if you will add one more box in order to satisfy, for example, your storage growth needs, then you will end up with compute memory resources not certainly utilized, and that is just unacceptable when you go at scale. So wishfully, what you want is to be able to grow each of these aspects completely independently of the other, and this is what disaggregation enables you to do. But obviously, as you try to disaggregate, you need a very powerful media. One media that would enable you to disaggregate on the one hand side, but on the other hand, will take care of integrated inefficiencies that comes with it, like increased latency, bandwidth bottlenecks, and so on. Now, I want to point to one example of disaggregation and show a media that actually enabled that to happen. And to do that, let's look at memory, which is always such an important thing for increased performance, right? Or if you look at this graph, the green line represents the amount of memory that you can attach today physically to any CPU, GPU, TPU, you name it. The red graph represents the amount of memory that is needed in order to train these AI networks that I mentioned earlier. And as you can easily see, there is a gap between them that only continues to grow over time. This is known as the memory wall, meaning how you can scale and increase your memory interface when it's just not physically possible to connect more memory to your host. And on the other hand, the pace of DRAM technology is so much slower versus what the requirements are. And when I say scale the memory interface, I mean that in terms of capacity, bandwidth, utilization, and TCO. Now, one technology and one media that addresses this gap is CXL. And the low latency, the high bandwidth, and the memory semantics of CXL enable it to expand a memory interface by connecting more memory components behind what is known as a CXL bridge, and connect this bridge, on the other hand, to the host processor over CXL media. Now, additional value can be added by connecting compute resources to that bridge and enable near-memory computation. Now, the next evolutionary phase of that is, of course, sharing those memory components across multiple hosts and servers in what is known as memory pooling. And I mentioned earlier the need to optimize and better utilize our memory interface. So let me give you an example to that. So if you think about data centers, memory is one of the largest spends every year. That is billions of dollars every year spent on memory. Now, consider one of the most common use cases over there, like hosting, right? So not necessarily you know in advance what kind of application would run on your servers. Would that be a one that is very memory consumptive, or maybe very memory modest consumptive, right? So you may end up with your memory underutilized. And in fact, if you read the paper for some of these hyperscalers, you would see that they end up with 20 to 30% of their memory underutilized in that type of use cases. That is billions of dollars that are not being used, and maybe billions of reasons why to adopt a technology like pooling that would enable them to allocate more or less memory in real time and upon need to those servers. Now, another additional use case, interesting use case of CXL is to connect GPUs, CPUs, memories, FPGAs around a CXL switch in a coherent manner and enable and heterogeneous compute platform that is so important for the next growth of compute clusters. Now, CXL enjoys a very strong endorsement of everyone in the market, and I do believe that we would see a lot around CXL in data centers in the years to come. Which leads me to the second meaningful trend that I see, which is of optical connectivity. And in here, I think that many of you would agree with me about the importance of co-packaged optics, or CPO, to large networks. And accordingly, most of the developments in the world today are around high-capacity switches being used in large data centers as spine switch or end-of-row switches. But I believe that we would see at least one more use case for that type of optical connectivity, maybe even with a greater need in AI training clusters. And consider the following thing, right? If you'll consider bandwidth, which is such critical for these training clusters, because the amount of data that is moved around during the training procedure is just tremendous. So large that GPUs that are being built for these training clusters today already have anything between 800 to 900 gigabytes per second of aggregated I/O bandwidth just to connect to their peer GPUs within the cluster. And just to give you a reference for that, what that means, so if you would consider the highest capacity Ethernet switch today in production, that is 25 terabits per second, or maybe using the same jargon as before, the 50 terabits aggregated, these are used in order to connect racks together, right? So that means dozens to hundreds of servers. But it only takes 7 of these GPUs that I mentioned in order to saturate that very same capacity. So the need for bandwidth is obviously there, and optics can give you that. But consider also power that optics can help you reduce, power density problem of these power beast GPUs that optics can help you resolve. All of that would lead to a very increased usage of optics within training clusters. So yes, currently the market is focused on networks, and in my company with our switches and optical solution, we're certainly right in the heart of it, but I do believe that we would see optics being used very strongly in AI training clusters, maybe even sooner than one may think. The third piece I want to point out is customization. I think that we all learned to love general purpose devices, right? Great job done by great companies. Make them so easy to use. And even if they are not 100% tailored to the exact thing that I need, they are certainly way more than just being good enough. They're way more than that. However, as I mentioned, when you go into scale, that might just not be enough anymore. Because over there, if it's not 100% optimized, then every one non-optimized watt turns to be a megawatt. And every non-optimized bit per second turns out to be terabit per second. So we need to optimize whatever we use to our exact use case. It doesn't mean that, a general purpose that addresses everything very closely is not good. It just means that we need to optimize 100% of it in order to enable ourselves to scale and to maintain our TCO. So these big hyperscalers, what they want to do today is to customize their silicon. And they want to do that in order to differentiate themselves, to maintain their competitive advantage, to control their own destiny, and in order to optimize their TCO to their exact and 100% needs. And to do that, of course, they would need to push the boundary on each and every aspect of silicon technology. So that's where most advanced chiplets technology, I/O connectivity technology, package technology, SerDes technology, IP libraries, and of course, undisputed execution all comes into play in order to make that happen. That is a key strategy for all these hyperscalers if you follow, what they do today. And there are very large prizes for those who can execute upon it. Now let's shift gears. I think if I will ask you right now, okay, what is the largest vertical market for semiconductors today? I think that most of you would say cloud, right? But would you hold on to that same answer if I will change my question to be what's going to be in 10 years from now? How about 15 years from now? I think that for those of you who were here this morning, they should already know the answer, because the answer to that is it's actually going to be automotive. If the clicker will help me, okay. It's going to be the automotive market. And the automotive market 2022 ended with about $49 billion size for semiconductor in automotive. And this number is expected to grow to 115 billion by the end of the decade, and estimations are that it's going to grow to 250 billion by the end of next decade. So what is driving this growth, and why now? Well, I believe that the car is going through a revolution, nothing less. A revolution similar in size and nature to the one that the phone went through just years ago when it was reinvented as a cellular computer that runs over a very capable software platform. And accordingly, software will not only drive the future car, but it will also provide us with the software platforms on which we can port upgrades and application and services, everything that would make the car so much more tuned to what we need exactly, and personalize the car for our specific use case. And that type of car will have a completely different set of requirements, because there's going to be dozens of cameras and screens and lidars and radars and sensors all feeding in information into the car at very high rates, information that needs to be collected, moved around, processed, analyzed, and acted upon, and everything in a fraction of a second. So of course, you need an architecture that can support that kind of data center magnitude traffic. And if you look at the architecture of the car today, that's called a domain-based, I think that the first thing that you would see in front of you is a nice collection of wires. And these wires are going to be very low bandwidth, low capacity, legacy type of protocols, all brought together in an impossible mesh, which is obviously not suitable for the type of growth that I was mentioning earlier. And think of it as not only from a technical perspective. VW published an article saying that the 2017 Volkswagen Golf had over 1,000 different types of cables in it, in an aggregated weight of 80 kilograms and extend to 1.6 kilometers in length. Now think what it means in terms of labor cost in order to put this complex thing together. What the weight means in terms of gas consumption of the car, power consumption of the car. This complexity, what it means of putting together the wiring harness of the car. It's just mind-boggling, right? And the architecture today in the future car moves into what's known as a zonal architecture. And with zonal architecture, the car is divided into zones. And in each zone, we have an aggregator that provides real-time response to the zone it's in charge of. But most of the heavy lifting in the car would happen in very specific and few places where very beefy compute resources going to be there serve the purpose, which means that all the data from the edges of the car would need to be routed, moved around over a very capable, scalable, high bandwidth, low latency, secured, easy to manage platform and network. And that network is Ethernet. And Ethernet have presented two very strong momentums in the market today. Number one, most of the car OEMs today are moving to Ethernet as their baseline architecture within the car. And number two, and maybe accordingly, the number of Ethernet ports shipped is in a steep growth. And 2022 ended with about 600 million ports shipped in automotive, which is higher than data center number. And even more than that, data center Ethernet growth is a single-digit number versus 40% CAGR in automotive. So it's quite clear where we are going from here, right? Another interesting thing to look at is the growing speeds of these ports within the car. It's in the yellow line, you can see the numbers represent the introduction point of these speeds within the car. And as you can see, time is also shrinking between introduction points in the car. So it started with 10 meg, 100 meg, went into 1 gig. It is going into 10 gig very shortly, and there is a path already to 25 gig in the car. And this number would grow in the future. Now, I mentioned data center on wheels types, and I talked about software-defined vehicle, and I talked about the scale. Let me show you a practical example for what that scale means. So if you look at this graph here, what you can see is size of a database represented by the number of the code lines. And you can see that the Google Chrome is about 6 million lines of code. A 787 Dreamliner runs on 7 million lines of code. And the most advanced F-35 stealth jet fighter is about 25 million lines of code. But an existing generation luxury car is already running over 100 million lines of code. A level 3 car, which is only halfway between the current generation and full autonomous vehicle, is 300 million lines of code, and a full autonomous vehicle, as published by VW, is expected to be 1 billion lines of code. 1 billion lines of code. What type of data set are you familiar with of that size? That's the scale that we're talking about here. And that's the type of amounts of data that we will need to deal with here. But before I leave you, here is something to think about, okay? And I hope that there are a few software programmers too in this whole hardware conference. With the data set at that size, how well can you write your code in a way that a very talented hacker will not be able to find a hole in your very well-written code and maybe take over your car, your autonomous car, as you are in it, or worse, if your family is in it, and maybe ask you for a few bitcoins, or otherwise the car will never reach its destination. It's not a science fiction. This can actually happen. And I believe that security would be one of the major challenges of the entire automotive industry and one of the things that may delay introductions of autonomous vehicles, because technology-wise, it's not that far out. Now, last word about my company, Marvell. So we chose to focus our strategy on 4 vertical markets that we thought were the fastest growing and the highest growing. These are data centers, enterprise, automotive, and carrier, 5G, right? And within those markets, we focus our strategy on enabling that infrastructure that can scale. And accordingly, we built a very wide portfolio. Some of the things are listed on the left-hand side in order to address that. Now, in India, over the last few years, we doubled our presence, actually more than doubled our presence, and we continue to grow. And the teams here in India have been involved in the developments of all these things. And just to give you one example, just recently we announced the tape out of a 3 nanometer technology-proof device. The India team have been taking a major part in taping out this design. And I think that's just a proof of how much we rely on our India's teams at Marvell. And with that, I would like to thank all of you for the opportunity to be here on stage, for your attention, and please come and say hi at the Marvell booth if you have any questions. Thank you all.
Thank you, Noam, for that very engrossing talk. I would now like to request Mr. Siddharth Rele, Senior Director at AMD and the member of the organizing committee, to please come on the stage to present a memento to Noam. A round of applause, please. Our next keynote speaker, Mr. Manish Kothari, serves as the Senior Vice President of Software Development at Silicon Labs, Inc. He also leads Silicon Labs' presence in India and is responsible for growing wireless engineering talent, building scalable infrastructure, and fostering local partnerships in Hyderabad. He has more than 20 years of technology management experience, has built and managed teams of over 1,000 wireless developers and system engineers, and holds several patents. Manish is going to talk on a very pertinent topic, IoT. I think we can all agree that we've seen an exponential increase of IoT devices all around us. Manish, in his keynote session, is going to discuss the important role of silicon and software innovations and other major industry developments that are driving the growth of Internet of Things. Ladies and gentlemen, please welcome Mr. Manish Kothari.
Thank you. Thank you for the kind words. I think I've learned to be on this side. This is probably a 2.4 gig transmitter, so there is some interference or whatever. Anyway, folks, good morning. What I wanted to talk today, roughly, is about what is happening in IoT. IoT as a word has been around, but there is a confluence of things that has occurred that will provide an explosive growth from now on. And what is happening, what are the challenges, what are the exciting things that are occurring, and what the future looks like. So I'm hoping I can paint a picture of that. So all of us in the technology industry, the leaders here, we are driven to innovate, push boundaries of the technology, bring new products that can transform industries and lives and our planet. And those of us, like Silicon Labs, who are a pure play IoT player, share a common vision of a smart, connected devices as ubiquitous as electricity in our homes and beyond. Now, I think, folks, it's important to understand these words, like ubiquitous, present everywhere. in the world we live in today, it's made up of humans and a multitude of things in our offices, in our homes, everywhere. And what we are talking about is these things coming to life, interacting with us, and making our life better, our planet better, and so on and so forth. For example, this particular floor that I'm on today could be connected in an annoying way, could be telling me, hey, Manish, you've gained some weight post-December, which would be an annoying feature of the technology. But jokes aside, a pillar that collapsed in Bangalore yesterday could be prevented, right? A bridge that's collapsing can be prevented. The technology is here. The question we have to ask ourselves is, why is it not happening? And what does it take for it to happen? And I think that's really important for us to think about. There are several things that need to come together for these things, this physical world, to become real. So they can talk to each other and talk to us in a way that makes our lives better. So I'm going to talk a little bit about that and why I'm so excited about where things are. First, let's look at the outlook, and several folks have talked about it. It's, when you look at this graph, just the number of units, it's mind-boggling, right? First is the size. You're not talking about tens of billions of units, you're talking about hundreds of billions of units, and if you look at 20 years out, you're talking about trillion. That's massive in terms of number of units. Second, when you think about this kinds of units getting connected, sensing, inferring, and doing a variety of different things, what does it mean? It means it's going to have a major impact everywhere we are, in this conference room, in our hotels, in our offices, in our homes, in hospitals, in retail stores, everywhere the impact is going to be felt. So the IoT is finally here, and I think the term IoT actually was coined about 20 years ago. We did some little history around that by an individual from MIT called Kevin, and that time it was all around RFID, right? But we believe that the IoT is finally here, and I think it's important to understand what's happening today. Silicon Labs has two different business units, home and life, and industrial and commercial. Just look at the different applications. This is just a snapshot. It's massively heterogeneous, right? There's not just one big market. It's made up of tiny, tiny, small markets, different applications that are driving transformation. So the possibilities are endless. But what has happened is there are some key enablers that have all coming together now. For example, sensors and embedded computing, right? They have been there for 20, 30 years, but they're all very important part of what we need. Wireless protocols, a variety of different wireless protocols have come together to solve different kinds of problems, from cellular to Wi-Fi to Zigbee to ZWAM to LoRa. There's a variety of different cellular, wireless protocols. You needed cloud connectivity, which is now present. You also needed smartphone penetration, because a lot of the onboarding of your devices today, of your things, can be done via phone, via mobile computer. That didn't exist 10 years ago, right? So that is now here. You also need communities and ecosystems. And what I mean by that is, the best example is you can think of Google, Apple, Amazon, and Samsung as an ecosystem, right? They are very, very important. These ecosystems now enable a lot of things to happen. And then, the last but not the least, I would say open source hardware and software, right? A designer of this table or this floor has to think, if this has to get connected, first it's the total cost of the solution. The total cost of the solution is not just the silicon. It's the board that needs to go in. If it requires 10 software developers to bring it online, it requires 5 application engineers to maintain it over the lifetime of the product. That's not a viable solution. You're not going to get hundreds of billions of devices there. Open source movement is big in our industry. And what that does is it drives the barrier to connect things and do intelligent things with it really lowers it. So there's a large movement of open source software and hardware, like the Arduino project, which have really kind of come together. And the last but not the least is Matter. And I'm going to spend some time on Matter and why I believe it's so transformational and important. So all of these things have now come together for really the IoT to take off, right? Driving the total cost of ownership so low that you can now connect virtually everything, and it's happening today, right? So we are working at the other end of the spectrum. We're doing tiny ML, we're doing tiny compute, we're doing tiny sense with a very tiny battery, a coin cell battery, that has to last 10 years. So it's a very interesting problem, and I want to give you all a little bit of color on the challenges of defining this kind of system, right? So if you look at what you have, you compare data center, PC, mobile, and embedded. Embedded is really the largest and the most constrained computing platform. I think this has been known, nothing new there. And I think what we are seeing is every embedded platform will get connected over time. That's just natural for it to happen, right? The connection gives you the ability to now communicate. So what is the complexity for those players like us who are playing in this IoT space? So when we think about silicon, it's actually, people, talked about software-defined vehicles, but really, if you peel the layer below, it really needs to be software-defined silicon as well. Otherwise, you really don't get the full benefit. So when you look at what is happening underneath the hood of an IoT silicon that we work on, it has 50+ wireless protocols that have to run on this silicon. I just mentioned a variety of different wireless protocols. The budget that we've got, whether it's area, power, cost, memory, is super, super tight, right? I don't have 100 billion lines of code to, that budget is just not there. The things that we want to connect cannot support that. They will not last 10 years on a coin cell battery. So the hardware software complexity is quite high on a different scale. The product life is 10 years. I cannot do a software upgrade and then kill the battery life of the device. So the budget that I have is extremely tight. So you have to think about what is a time-relevant hardware software design. Can I reprogram my hardware over time to make it more relevant? The wireless protocols evolve. The standards evolve. They are not constant, right? So a time-relevant hardware software design becomes very important. So very exciting times ahead of us. The applications are phenomenally diverse, right? You've got an irrigation, to a lighting, to a doorknob, to a vibration, vibration sensor, machinery, to a positioning in a retail environment. There are very, very different applications, and you have to think about how do you take your hardware and software and configure it to various different applications, right? Product management is a lot easier when you can go and talk to 3 or 4 customers and define your platform. You can't do that here. It's extremely challenging and not easy to do. You also have to think about open source, and this is really an area where we pay a lot of attention to. We pay attention to developers' NPS score, right? We think about the NPS score of the developers. Why? If it requires 10 developers to create a product, you will not get to trillions of devices. It's just not going to happen. You can't require a large company or an Amazon to do this, right? You will have literally somebody in the university thinking of an idea, connect something, do something useful with it, and get it to the market, right? So that is something that all the things that we're doing has come together. It also is leading to new opportunities with SaaS. And I don't have enough time to talk about it today, but there's a lot of interesting applications on the security side, which obviously is super important, right? So very complex, super important. Now, what is the last pillar that came together? And I want to talk about that, which is really important here. That's matter, right? Matter is super exciting. Now, I would not have thought Google, Amazon, Apple, Samsung would come together and agree on a standard. They did, right? Along with semiconductor players to create a standard called Matter. What is Matter in a simple terms is the ability for things to talk to each other in a common language. Why is that important? Well, let me give you a fun use case. You've got you have a security system that detects an intrusion and your lights could flash. Now, to do that, it will require some complex programmer or a geek or an IT company to do that. No longer you don't have to do that with Matter. With Matter, it's there. It's simple. They all talk to each other. You know how they work. So it's a very important initiative that the industry has taken. It was launched in September. And it's an open source project. I talked about the power of open source, power of communities. If you have communities, you don't need to go to application engineers. You post a question there, you query, and you get an answer, right? So that's the power of Matter. I'm proud to say that Silicon Labs was the largest semiconductor player to provide code in the Matter project, and the third largest overall, working with Google, Apple, Amazon, and Samsung. What is happening is we as silicon players have to think like software companies. It is so important, which is why you've seen a lot of these players building bespoke silicon or going vertical, right? Because they are defining increasingly their silicon based on software, not based on, okay, let's look at GPU performance, this memory bandwidth. That comes later. So that is really a challenge for us as well as Silicon Labs, as a merchant silicon vendor, to do that. But it's very important with Matter, this thing is going to happen. So this Matter world is here. The other beautiful things of Matter is security is inbuilt into it. I'll talk about it a little bit. It solves the interoperability between ecosystems. You don't need to have an IKEA app for an IKEA bulb or a Tuya app for a Tuya smart lock. You can basically operate it from any ecosystem that you want. And this has very important implications for the industrial and commercial space as well. Large amount of money in the industrial and commercial space is spent stitching all of this infrastructure of things and machines and sensors together because they don't have a common language, right? So you have to project 5, 10 years from now how these things are going to transform. So that's really very important. And it's an open standard. So Matter is here, super excited about it, and it's really the last underlying piece that has come together to transform our industry, right? So it's going to bring the consumers, the developers, which are super important in this business. You got to think about them, and the businesses. So very, I would say the last holdout in getting this confluence right to really drive an explosion of connectivity. Now, the beauty of Matter is it's rooted in silicon, right? So this Matter is a stack that's running on a networking stack underneath a variety of different IP-based wireless protocols, right? So it's built into the silicon, it's tested in the silicon. So if you procure it from any vendor, you buy a Matter certified product and it's got a nice logo in a retail store, it's guaranteed to work and interoperate with other Matter devices, right? So it's built into the silicon, which makes it really easy for consumers and everyone to kind of adopt it. So, and the security is built into Matter. And I don't want to go into the various mechanisms of security and what Silicon Labs is a leader in providing that capability and kind of embedding it into hardware in a variety of different ways. Not only at, authentication is clearly one, onboarding, but really maintaining that secure level of performance all the way throughout the life of the product. So we have a complete Matter development platform, and you have to think about a platform kit, right? So that's really what's happened. Now, one application that I want to talk about to give you the heterogeneity nature and the power is low power WAN, a low power wide area network, right? So what are we talking about is tens of square kilometer wide area network. And if you look at the current technologies that were there, they were proprietary, they were not reliable, not secure, non-IP based. And there is a protocol called WISN, Wide Area Smart Utility Network. I don't think many people know about. Already 100+ million devices are on it, okay? This runs on a sub-gig spectrum, below sub-gig. It's an unlicensed spectrum, it's free spectrum. Almost, you can just look at the coverage of how many countries, 46 countries already have it, right? And we are a part of it. And what this does is provide a very large network for an application like smart cities, right? So when you think about what we are doing with, sorry, I'm going to skip to a smart city. So we have a WISN network, a living lab in Triple ID Hyderabad, right here, about a few kilometers from here, where all the poles, the light poles in the campus, are running on this network in a mesh network format. And this WISN network can run on thousands to 10,000s of nodes. And from each light pole, you can do a star network and connect meters, waste monitors, and so on and so forth, right? Very low cost, very effective. It's an IP-based technology, and this living lab is available for anyone to use. So what hopefully I've kind of walked you through is, IoT is here. The buzzword of IoT has been there for a long time, but there were a lot of things that had to come together. It's happening. And what I feel is we are at the inflection point of IoT. And one of the things we have to look at is what has happened in the history. History may not repeat, but it rhymes for sure. And the best way to think about it is, in my background, in mobile industry, you've seen how smartphones, as they were connecting people, as they went from 2G to 3G to 4G to 5G, and as the silicon technology node shrunk, they disrupted multiple industries, right? MP3 players went away, cameras went away, right? You could say even the need for regular computing, let's say laptops for most people who are running, kind of has disappeared with ARM class processors that have come about. When you think about IoT, as you're just connecting these things with tiny little ML, tiny little compute, running on 40, 90 nanometer nodes today, just project 20, 30, 40 years from now. Silicon technology will shrink. And as they shrink, you're going to have such powerful capability in your lights, in all your things around you, that you could do unimaginable things that we have not even imagined. Right? So that's why I'm super excited about the future, not just what's coming, but certainly 20, 30, 40 years from now for all the students who are going to be working on this beyond certainly my career in terms of the opportunity that's there in front of you to really change the world. So with that, thank you so much.
Thanks a lot, Manish, for that very interesting talk. I would now request Mr. Jaideep Kulkarni, professor at UT Austin and a member of the organizing committee, to please come on the stage to present a memento. A round of applause, please.
Thank you. Thank you. Nice meeting you.
Thank you, Manish. Thank you, Jaideep. We will now move to the industry forum discussion on semiconductor manufacturing and OSAT. Venkata Semadri, the General Chair of the VLSI Design Conference, will be the organizer of this session. Mr. Venkata Sudhakar Semadri is a serial entrepreneur and a proven executive in the semiconductor industry with 30+ years of experience. He was the founder, president, and CEO of Gigacom Semiconductor LLC and founder and director of Gigacom India. Both of these companies were acquired by MOSCHIP. Earlier to Gigacom, Venkata was the founder, president, and CEO of Time to Market (TTM) from 1998 till its acquisition by Cyient in 2008. Mr. Venkata is currently the MD and CEO of MOSCHIP Technologies Limited, a member of ISA Hyderabad chapter, and the brains behind the ISA AI Summit started in 2021. With that, let me ask Mr. Venkata to please come on the stage and moderate the session. Thank you.
Thank you. Thank you for the kind introduction. So we all know that this conference is more focused on VLSI design and embedded systems design. But right now, India is going through a revolution. The manufacturing has become a key topic for the whole country. We know that the Indian government announced a $10 billion package, and majority of it is focused towards the manufacturing side of things. So with that in the background, I felt it is very important for us to at least have a focused session on manufacturing as well. And that is the reason I kind of, chairing this small forum here and put together some very important topics, interesting topics, as well as a panel discussion. And as the first keynote speaker in this forum, I invite Tushar Dayagude from Transform. So Transform is one of the leading gallium nitride fabs in the world, and Tushar works as a worldwide sales head, and he has been partnering with MOSCHIP and PowerX to bring some advanced power management solutions to the country. And with that, I invite Tushar Dayagude onto the stage.
Good afternoon, everyone. So, we have been working in India for the last few years, and instead of just presenting a topic or technical details, wanted to show actually what we have done. And we'll get back to that at the end as well on what our roadmap is. But with the help of MOSCHIP, Venkata, our silicon partners, Selana, who will also present later, and new startup company called PowerX, we actually designed, developed, and manufactured a complete USB-C charger, which is a very advanced charger made here actually locally in Hyderabad. So with that backdrop, I want to introduce Transform GaN, its comparison with other power semiconductors, and see how we can make India more self-reliant and efficient in these power systems. So I think this presentation is a mix of technological advances in power semiconductors, as well as for some of the experts, I don't want to go into circuits, that if you want to talk about circuits or see some other demos, we have a booth here, the Transform booth, along with PowerX. So I'll introduce GaN applications vis-a-vis other power technologies, talk a little bit about where GaN applies from, all the way from 30, 40 watts to 10 plus kilowatts, including adapters, computer power supplies, PV solar inverters, 2 3-wheelers, as well as automotive and UPS. A little bit about the company. Then I'll compare Transform GaN with other power semiconductors, and then we'll give you an overview of systems that are enabled by Transform GaN. And we do have a few customers who do some design work in India, but this has truly been our first foray into India. Most of the other adapters are either designed in China, manufactured in China, or in Taiwan. So I hope with this we can get India onto the bandwagon of not just manufacturing. Like India manufactures a lot of iPhones, but we can actually design the components, develop everything here, and do it not only for India, make in India, design in India, and sell it in the world. So GaN is the future of power electronics, power semiconductors. Silicon, as they say, it's an old technology, it's a reliable, proven technology. Silicon carbide is coming very strong in automotive and high power. And then if you want to make the power systems very efficient, smaller, lighter, and actually lower cost, GaN is the material to adopt. And again, I don't want to make parallels between other countries, but China has adopted GaN in an extremely widespread manner in all their applications. So I think this is a good time for us to catch up, not only catch up, but be on par with the rest of the world. So again, I promise that I won't make it very technical, but just to see where GaN plays. GaN plays in the high frequency, domain where power density and efficiency are critical. That improves, they call the figure of merit in power semiconductors. So this is where GaN actually, and what does it mean for India in terms of power savings? So in 2025, we believe that moving to GaN in adapters, electric two-wheelers, four-wheelers, and other power supplies, we can save about 1.1 terawatt hours of energy that will supply about 2.6 million rural households. And if everything had moves to GaN by 2030, the annual savings could be about 150 terawatt hours, which is actually enough to supply all of the rural households. So GaN is now getting very pervasive in everything from the wall adapter to automotive. And I will talk about each of these as we go along. So fast chargers, servo motors, PC gaming, all these things. The old technology was MOSFETs, IGBTs, BJTs. They are migrating to GaN as well as silicon carbide devices for high power. It will be unfair to not talk about the ecosystem. So Transform is a dominant player, but not the only player. But we have the widest portfolio of products that can work all the way from all the applications that I just talked about. So the founders, one is from Bombay IIT, one is from Kanpur IIT. Professor Mishra is kind of the father of the GaN devices. I'm very fortunate to work with them. And we just opened the India office, and also we have a very strong partnership with MOSCHIP over the last few years. So Transform owns its own GaN wafer production supply chain, all the way from designing the GaN devices to EPI, which is the core manufacturing process. And then we have a joint venture fab in Japan. We are looking at bringing some of this technology to India, as well as working with Venkata on some of the other initiatives, including OSAT and system level solutions. Our GaN FETs are now into all the markets here: adapters, data centers, crypto, industrial, aerospace, and automotive is the next big one for us, especially starting with the two-wheeler, three-wheelers. I've spoken with almost every scooter, motorcycle manufacturer, and they're all hungry for getting the OBCs made from GaN. So the market opportunity for GaN worldwide, as of last year, is about $1.8 billion, getting to about $6 billion. And if we can get into the traction inverter for automotives, like for Tata or Mahindra, that could balloon to about $15 billion worldwide. And not just that, this is just the GaN component, but you also have controllers, DSPs, FPGAs, and of course the mechanicals, PCBs. So that ecosystem could be close to about $40 billion. So this is, again, a very, very good market for India to participate in. It's almost like, not going with the, telephone line and going straight to 5G. So I think India can actually, embrace this much faster. Growing opportunity in EV, like I said, OBC, inverters, EV powertrain, and I think the big opportunity also in two-wheeler, three-wheeler. I can go in more details in that as well. This is a kind of a eye chart on how GaN competes with other devices, and especially the transform GaN. But I think let me go to the next slides because those are a little more, yeah. So GaN has enabled kilowatt class power supplies for servers. HP, Dell, Facebook, Amazon, Microsoft. They have started now going towards GaN power, and India with its huge potential for data centers, I think will have a policy for what they call as a titanium rating or platinum rating, so that you can reduce the overall power consumption of the country. We are into all kinds of hardware. Corsair, that's a gaming power supply. AES, that's a aerospace power supply. TDK, some medical devices, as well as the computing devices. So GaN is a power semiconductor. It comes in various packages, and of course then it's bundled with the controllers, the PCB, everything to make the whole solution. But this is the enabling device, and these are the packages we are in. So all the way from the 30 watts to 250 watts, all the way to about 10 kilowatts. And then when you parallel them, you can make it multi 10 kilowatts. So in comparison with silicon, that's the current state, is simpler to use and interface and makes systems smaller and efficient. Next slide. In comparison to silicon carbide, again, they are much simpler to use and interface and make them smaller and efficient. And then with respect to other GaN, we are, like I said, we are not the only GaN company. There are other GaN companies, but make it higher reliability as well as the same, more efficient and simpler to use. Again, this is more for some of the academics. We do a lot of work with the end customers in terms of their application. So whether it's power adapters in this category of 65 watt, there are various power categories, there are various applications or end applications, and then in power supplies they call it the topologies. So there are various topologies. I think Silana is going to talk about one such topology in the later sessions. So it's a bit of a complex field. There are controllers, DSPs, microcontrollers that are used to make the whole system. So we will work with customers and enable them. I'm just going to give a brief summary of some of the power supplies that we are into. And this is where, again, all these are used in India. They're mostly kitted from China or maybe Taiwan, and then probably assembled here, or just end products are sold in the Indian markets. So this is an opportunity for us to work together and make this a reality, not only from a manufacturing perspective, design perspective, but also from a power savings perspective. So these are some of the adapters and chargers that you probably see on Amazon or Flipkart. We are one of the dominant players in those, from 30 watts to 240 watts. So the one that we have is a 65 watt 1A 1C, and I'll talk a little bit more about that. But we are trying to put India into the game, whereas all these have mostly, I believe, have come from China. Again, I don't want to get into the details of these solutions, what is there inside, but they are pretty intricate. They are in a very small form factor, and a lot of electronics is packed there. So it's, it looks small, but it's pretty complex. Um, and the reason why is it is complex, it's pretty multidisciplinary. You have to do a good IC design, you have to do a controller design, you have to do a processor design, you have to do protocol software, and pack it into a very small system. So to get the right kind of efficiency as well as the industrial design possible. So again, I don't want to get into the details of these systems, but I just want to show how complex some of these systems can become. And again, from 70 watts to 360 watt, the systems get more and more complex, and you have more and more options on how to address them. So we have more designs in the pipeline, and we will work with Indian companies. We already have demonstrated that with one partner company, but we will bring more products. 65 watts was the first one, 100 watts, another one. Next slide, please. 250 watts for computer medical power supplies, 330 watts to 800 watt platform for telecom and servers. And again, these are all best-in-class solutions. They are not just going to be made in India, but they'll be world-class solutions made in India for the world. I think another topic of a lot of interest in the country itself is the powering of electric 2, 3, 4-wheelers with GaN, all the way from 300 watts to 30 kilowatts. And when I say 30 kilowatts, it's not for the two-wheeler. It's mostly for the battery charging stations like Gogoro, where people can go and swap the batteries. So there are various types of categories. There is portable chargers, there is a fixed chargers, then there is battery swapping, as well as what they call as the pole chargers or fast chargers. So in all of this, GaN can make the solution smaller and actually reduce the losses by 50%. And inadvertently, because of this, you will make the system also cheaper. So one of the things that when I talk to Indian customers is GaN very expensive? And unfortunately, GaN was expensive a few years back because it was a new material. So the volume was not that great. But now, over the last 2-3 years, GaN has become, at least on a solution level, on par or lower cost than its silicon counterparts. So we, again, can work in every relevant power conversion segment and bring very world-class solutions, to this market. So this is one of the architectures for a battery swapping station, where you have 10 kilowatts to 30 kilowatt power level. It can be either a pole charger or a battery swapping. So this is one solution that we also have worked on. We are actually developing a 750 watt OBC. One of the reasons why the market in India is actually taking off is I don't need to tell everyone here, why the two-wheeler, three-wheeler, electric two-wheeler, three-wheelers are taking off. Low noise, low pollution, and reasonably easy to operate. But one of the reasons why the penetration has not happened as fast as it should is because it's also missing what is called as a onboard charger. And we are working with companies to develop a complete OBC, onboard charger, with power delivery, charging electronics, and battery profile management that can reduce the size by about 20% and 30% lower on the losses. So a sample of this assembly is actually there in our booth. So if anybody wants to look at it, welcome to come and visit us there. We will be sampling this part by end of March, and so again, this is another full design that is designed, developed, and will be made in India. And India is one of the largest markets for two-wheelers, three-wheelers. It's also a protected market. Sometimes we may not make the best products, but we protect it, so it doesn't matter. Either way, we'll take advantage of that. Okay. Yeah, and last but not the least is the UPS systems, UPS and PV systems, which are, again, getting a lot of traction in India. So GaN will allow them to make it smaller, cheaper. Same thing, make it higher frequency, make it lower cost, make it higher power density. And, instead of having what is called as a 2U size, you can put it in 1U size. Again, these are huge market opportunities for India, to kind of leapfrog some of the existing power electronics and move to the next phase. There's another slide to show all the applications of, GaN in the electric vehicles. So we are also working with some of the electric vehicle companies. One of them starts with T, one of them starts with M. You know who I'm talking about. So. Okay, so with that, next slide. So, I really want to thank, our partners here, Moschip and Silana for doing a fantastic job in, getting this whole system. It took, I would say, 2 to 3 iterations. It was not a simple design. So in China, people started developing GaN adapters probably in 2017, 2018. And it took about 3 years for them to start penetrating the market. From 2020, you could see GaN adapters in the market. But actually, I think within a year, this design from inception to complete delivery of the whole, package, I'm really, proud, that, we have accomplished this. And I think there are more such designs on the way. And, again, the thing is, Indian conditions, for the power supplies are slightly unforgiving. So, in terms of compliance and safety, right, we had to make sure that they don't burn out like the Chinese counterparts. So again, with that, this is, I think, is a very good accomplishment. So Venkata, I want to invite you, to showcase this. So again, this is not the only thing that we'll be doing. We will be doing, more, advanced power systems here. Lighting is another one, especially connected lighting. We have some work going on with another large company. It starts with R and ends in E, so you probably can guess the name. Two-wheeler, three-wheelers, as well as inverters and UPS systems. So with that, I would like to conclude my talk. Next slide, last slide. So all I want to leave the audience with one message, Indian companies should really adopt GaN as soon as possible, and produce world-class, cost-effective systems. I think this is a good opportunity because we have not taken advantage of the existing solutions. So let's leapfrog everyone and go to the new solutions. Just like China did. They didn't build any wiring infrastructure for cell phone for the phones. They went straight to 2G, 3G, 4G. So I think this is a good opportunity for us. So with that, I would like to thank everyone for listening to the talk. Thank you.
Thank you, Tushar. Thanks for taking the time and fly from all the way from California to educate us on the GaN. So GaN is going to be a game changer for India, I believe. Tushar, please, 1 second. So, and a lot of times we think designing a 3-nanometer chip is the most exciting thing. Trust me, every 5G base station that is installed out there, it needs power supply, and GaN can be a game changer for us. With that, I invite Satya Gupta to give a memento to Tushar.
Thank you, boss. Oh, wonderful.
So I think Tushar and Venkata has laid out the advantage of the GAN. And I think a lot of innovation in product space can be done by all of you. You will get the lure of using a Chinese GAN chip. Don't fall for it. Talk to me, Venkata or Tushar. We have been working with the transport team for more than 1.5 years. Anybody wants to do a GAN product, please get in touch. Don't use the Chinese GAN chip.
Thank you. Thank you, Satya. What Satya is saying is if you see a PowerX product on the Amazon, and which is like 500 rupees more than the Chinese product, please buy Indian product. Right, Satya? Thank you. So we are running a little behind, and we have another exciting speaker next. So people keep saying that, India doesn't have fabs, we don't have this, we don't have that, no manufacturing here. But trust me, there is a fab in Hyderabad. And this is a gallium arsenide fab. It is owned by the Indian Defense, Government of India. And I like to invite Mr. Anant Naik, who is the CEO of GATEC. This fab is very close to the Hyderabad airport. And they are actually manufacturing some old class gallium arsenide products. And these are, going into some very critical missions for the Indian defense and aerospace. So Anant Naik is an IIT Kharagpur graduate, and he also has a master's from University of Mumbai. And he has been the CEO of GATEC, and again, he is from Hyderabad, and this fab is in Hyderabad, right in our backyard. Not many people know about it, so let's hand it over to Mr. Anant Naik. Give him a round of applause.
I am thankful to Venkata Simadri for inviting and making this a very small industry session among the VLSI designers. And ours is a 3-5 compound semiconductor fab, and we have our own PDKs, our own design centers, and our own fab line and product development. We are not right now open to the market today, but it is a strategic application fab, and we cater to most of our output goes to ISRO for satellite applications and DRDO for EW and radar applications. So I will just like to take this opportunity to introduce you to GATEC and what kind of products we are making, and there is a big opportunity ahead in this direction of compound semiconductor also. And silicon is way ahead in design as far as India's output is concerned. Most of the design centers from world-known fabs are in India, Bengaluru, Hyderabad, and for that, I think this is a slightly different area compared to that. So recently, because of the pandemic, we all know of the supply chain issues. Then a lot of tension between US and Taiwan, and most of the time, all the countries had a lot of challenges with products which depend on the semiconductors. And we know that a lot of pressure on Taiwan because they have the foundry TSMC, which almost 50+% of world over deliveries of silicon ICs, memory chips, and processors are supplied through Taiwan. So we need to have a foundry in India, and that's why the government of India has come out with an aggressive plan, and they're pumping in 76,000 crore rupees to begin with this, and this is not the first time. There will be a couple of more such tranches coming over the period of time. So maybe all the foundries working in India for design should also try to work with some Indian partner and set up a foundry, which can, like after maybe 5 to 10 years, it will start generating a lot of profits. India is a big customer, big user, and a big design center. For GATEC, we have an ecosystem. We have a design and technology development at solid state physics laboratory, which is in-house is a DRDO laboratory, and that is the technology goes to production when it comes to GATEC. So we most of the time we do it concurrently and implement it for the production at Hyderabad. So. So let me introduce briefly what is an MMIC. It's a monolithic microwave integrated circuits. The density is nowhere near to the silicon-based ICs, but the application is in area up to terahertz level as of today, and only the material. Silicon is also catching up in the way of silicon germanium-based RF ICs, but the power levels are not much. And as in the previous talk it was mentioned, gallium nitride, Tushar has mentioned about the application on the DC switching side and commercial applications. But gallium nitride also finds a huge application in RF segment. And that caters to all this radar system as well as EW systems and communication systems. So an MMIC is okay, so you can see a wafer and there is you can have around 150 or 300 MMIC chips on it. And that actually goes into radar, satellite communication, and ISA radar, which is latest radar technology for fighter craft. Our LCA using ISA radar technology, and ground-based radars for tracking and air defense radars, for example. So MMIC is functionalized by designing a module. A solid state, say for example, I am putting up 2 modules as an example. IC goes into it, and it is made functional by way of solid state power amplifier or a trans receiver module. So these are 2 products of GATEC which are used for space applications, and that I will briefly say. And this one TR module is the one which was used in the recent launch of ISRO satellite we know EOS-4. We call it as a RISAT-1A. And that is made, the chips are made at GATEC. The modules are assembled, tested through private partner, but qualified by GATEC. And it is now flying in the space and giving good results. Each satellite requires around 10 to 11,000 MMICs. So right now we may say very easily that we have got 50, 60,000 MMICs flying in this space. Made in India, modules made in India, designed in India. So just to compare the market, like there are gallium nitride as well as gallium arsenide. Gallium arsenide, a precedent of gallium nitride. Gallium nitride is taking the market by storm because of its power efficiency and power handling and the ease of design, and the chip size is smaller than the gallium arsenide. So, but however, gallium arsenide still not losing the competition because there are certain niche applications that can only be met by gallium arsenide. And this is the market YOL report which shows that gallium nitride will have almost 21% of CAGR, whereas the gallium arsenide will still progress with a moderate CAGR of 3.1%. You can see the defense market for gallium arsenide is not changing. So we are a gallium nitride as well as gallium arsenide foundry. And whereas the gallium nitride is increasing very fast in defense sector also. And as we know, semiconductor ecosystem, what does it mean? Anyway, we are all working in the same area, so that it covers fab equipment, chip design, for processing, then embedded application software. We also need a lot of raw materials, and these are the challenges for India as of today to set up a foundry. But with the help of government and all the planners, I think slowly at down 4, 5, 6 years, we will start getting our own raw material as well as equipment support team established by the vendors, OEMs in India, to cater to these fabs which will be coming up as well as the existing fabs. So as I said, we have many design centers in India. Fab-wise, India is having a moderate application, 3-5 application. Because of the strategic requirement, we initiated this around 28 years ago, and we are trying to overcome the restrictions that are put in by the import countries which are holding these technologies. So we work on a model called IDM. Means we have our own product design team and we make our own products, as well as we offer the foundry service as a pure foundry to our users in ISRO and DRDO. So we have got design centers at these units of ISRO as well as DRDO, and they design on our PDK, and then we load it on the foundry and then supply, qualify the product and hand it over. So this is how we function. Right now we have got 0.7 micron to 0.13 micron technology, and now we are actually entering into 80 nanometer technology for compound semiconductors. These are some of the tools that are required. This is unlike semiconductor tool. This is electron beam lithography, then reactive ion etchings are involved, then plasma enhanced deposition systems are involved. The processes are completely different than the silicon fab. So this our setup is available at GITEC, Hyderabad. And these are on wafer RF testing tools. That is required because when you process a wafer, you have to monitor the wafer progress over a period of time. You need to monitor all the performance parameters for the wafers that are being processed, and we have to qualify them. Then only it can go ahead. So these are some of the tools which has a high power load pull system and low noise noise parameter measurement system. They're all in-house at Hyderabad. Next. Then we also have a set of reliability tools because you need to qualify this for space. And there are very, very stringent requirements for space applications. And the device has to pass through 2,000 hours of test, storage tests and burning tests at elevated temperatures. And once the product is clear, then only it is handed over for space application. Because you cannot go above and repair the system. So once it is gone, it's gone. So this has to go through a very rigorous quality and reliability cycle. So this is some of the technology that I'll just try to depict it because 15 minutes time is not sufficient to go into all details. These are very complex technologies. So we have got mushroom gate technologies. Now we can say that the picture in the bottom, you can see 0.13 micron for feature which is making a gate and very big mushroom stretch above it for reducing the parasitics. So this kind of technology is already working at SN and products are being delivered by GITEC. Next. So right now we are into 80 nanometer and 35 nanometer feature development for active transistors. So maybe in next couple of year or so we'll have product out of it. When GITEC says product, it's a qualified product. We do not go by the demonstration of a circuit because most of these devices are already demonstrated. But once we qualify it through rigorous this thing, then only we give it for display it as a product. Next. Now these are some of the technologies and products. Just now I mentioned about the products and technology. This we are also into laser diodes, semiconductor laser diodes for some of the applications in directed energy weapon possible. Right now we are not using it, but we are developing for that. And so there are a lot of application areas in RF field, like broadband amplifiers, narrowband amplifiers, limiters, oscillators, multiplexer, mixers. So all these are now available from GITEC Foundry, which are a qualified product designed by us. And as of today, we have got more than 150 IP, design IPs and product IPs, and many of them are space heritage ICs. This is some of the examples I'll say. This is phase shifter integrated circuit, which is heart of any radar, electronically scanned radars. Without that, you cannot scan the radar and detect the incoming, intruding aircraft or a missile or anything. So this is developed by us for L-band applications. Next. And this is, we are also working for a project by DRDO Anvesha, which is a space-based product. And our systems are going into that also. These are a collection of some of the products which have gone into ISRO applications, which is Chandrayaan-1, RISAT, 1, 2, and now 3 also we are giving the products. And all TES, Cartosat, TETSAT, and most of the communication band satellites. So any data link or a communication download, upload speeds, all through this MMICs are happening. Here there is no silicon chip because these are already radiation hardened material. So it can very easily go to space. Next. So this is one more satellite which is likely to be, I think one version is already launched by SRO, and the second version will be coming in less for a couple of months. Next. Now, this one example, what we can have when we have our own indigenous technology. For example, the earlier series satellite, we have the top row, we have that TR module, which was quite bulky and which was used in RISAT 1, which was launched in 2004 or 5. This worked for almost 7-8 years, and right now, the satellite is no more in the space, but we supplied another version, that is the second line, which is a LTCC based, which has reduced the weight of the panel by almost 150 kilogram weight. So that actually for a space application, the reduction in weight is a prime requirement, so that your satellite can, or the rocket can carry additional payloads. The last one is a core chip, for C-band core chip. Now, the complete prop line is made into a single integrated circuit. That will actually reduce the weight by almost 1/4 of the original weight of the satellite. This has been now, next generation satellite will use this MMICs. Now coming to the gallium nitride part, I think Tushar has given a lot about the reliability, power efficiency of gallium nitride for commercial applications like charger and DC-DC switching and other things. But for RF side, we have a gallium nitride technology. We have the PDK up to X band, and we have 0.25 micron gate length transistors, and now we are into X band MMICs, as well as the power bars, which are very high power, 130 to 150 watts power out from a single transistor, which can further be combined into a kilowatt level of powers also. Next. And there is a very wide band, 5 to 18 gigahertz wide band core chip. This technology is absolutely restricted. Nobody can give it to India because it has a very significant EW applications. This has been developed and designed by us, and this has been demonstrated for actual applications. And it is actually a lot of many MMICs into a single IC. You can call it as a system on chip for a kind of a system. But when it operates at a gigahertz frequency, the design becomes very sensitive and very difficult. And this is similarly a very technically competent product for our defense electronics laboratory. And this is called wideband bidirectional amplifier. So in any ISR radar, there is a transmit signal, there is a receive signal. The signal tend to drop in between. So this IC cater to amplify the signal which is weakened during the operation. So in both the directions this works. So it will be a bidirectional amplifier. This is also qualified and fabricated by us. And this is same thing, this is a gallium nitride based core chip. So TR chip. This is designed and developed at GATEC. Next. Now finally, we have gotten our internal molecular beam epitaxy system also that we are using for developing a terahertz. Now terahertz and quantum technologies are the things in future, and you will see a lot of publications and products out of these two technology range, terahertz as well as so we started working on that, and we have a detector diode for terahertz, which is right now we are targeting through 3 terahertz technology. Right now we have demonstrated up to 2.3 to 2.5 terahertz device, and now this PDK is available for designing mixers and other circuits out of that this technology. We can see a very difficult technology called air bridge interconnection technology, which was evolved in-house. And these are some of the device and device configurations for terahertz. Next. Okay, thank you very much.
Thank you, sir. It's a wonderful presentation, and give him a big round of applause. And we all should be proud that there is a real fab sitting, right in our backyard and doing some of these products that are really putting our satellites and into the orbit and powering our missiles. So with that, I invite Srini Bairi to give a memento to.
Next, we have a panel discussion on semiconductor manufacturing in India. We already have Venkata over here who's going to be moderating the session. I would now like to call upon the panelists on the stage. Mr. Suraj Rengarajan, CTO Applied Materials. Mr. Harpreet Singh Jatana, SCL ISRO. Mr. Anand Muttaya, VP TESOLVE. Mr. Devesh Dwivedi, India Site Head Global Foundries. And Mr. Brahmanand Reddy Patil, Managing Director, Vector Informatic. With that, I hand it over to Mr. Venkata to take it forward.
Good afternoon, everyone. So this is an interesting panel discussion, and we have some eminent people from the industry who are with the manufacturing background here. So I'll quickly go around the team and introduce them. We have Anand Muttaya here. He's from graduate. He is a graduate from University of South Florida, and he has 25 years of experience in semiconductor industry, and he worked at companies like HICC, Intel, and mostly in the test engineering side. And when we talk about manufacturing, testing is one of the key components in there, and he brings in a lot of experience in the test side of things. And he is currently working for TESOL Semiconductor as VP of Engineering. And then we also have HC Zatana. He is, he retired from Semiconductor Complex Limited. As I said, we keep complaining that India doesn't have fabs. In fact, SCL is the first semiconductor real fab in India, and it is still operational and producing chips. And Mr. Zatana will give a little bit more information and details about it. So he's a former scientist G and group director, and he's a design and process group at SCL. It's right now part of Department of Space with Government of India. And he led a team of 78 scientists and recently retired from SCL. And his key achievements during the last 8 years, he indigenously developed an SOI CMOS process at SCL. And he's involved in the development of high voltage process, 20 volts, 40 volts bipolar process. And he taped out over 205 designs. I mean, when I say not taped out, he actually taped out and got them fabricated at SCL. And he brings in real semiconductor manufacturing experience to the panel discussion today. And, welcome to the panel discussion today, sir. And then we have Devesh Dwivedi. He's the India site leader of IP Development and Design Engineering Center at Global Foundries. So we all know that Global Foundries is one of the leading semiconductor fabs in the world. And they have a presence in India. They're doing some R&D as well as IP development here. And Mr. Devesh has 23 plus years of experience in VLSI design industry and leading product and IP development. We all know that IP is one of the key components for a foundry business, and he's going to give us some insight into it. And he's actually has a PhD, he's Dr. Devesh. He holds a PhD degree in electronics engineering from IIT BHU Varanasi. And he has 3 decades of strong association with IEEE. He's an IEEE senior member since 2015. He is IEEE CAS Bangalore chapter executive chair since 2020 and 21. And then we also have Suraj Rengarajan. As we know that manufacturing needs the most advanced equipment. And Suraj Rengarajan works for one of the more leading equipment suppliers, probably the leading equipment suppliers in the world. And he works there as a India country head and CTO. And he started his career in Applied Materials, Santa Clara in 1997, where he held different positions ranging in the semiconductor industry, ranging from process engineering, technology, program management, and so it's nice to have you all with us today. As you all know that the manufacturing has been getting a lot of attention now, not only in India, in worldwide, and especially the announcement from the central government last year with the $10 billion incentive package, mostly targeted towards manufacturing. There is an increased attention to this segment, and to begin with, I like to have Mr. Jatana to give a little bit background about this policy, what actually it is offering to the industry, and the yeah.
Hello, yeah. About the government policy which they have, few initiatives which they have taken, and last year, I think in January 2022. So it has four broad categories of pertaining to semiconductor manufacturing. Most important is it's a overall budget outlay, overall is around $10 billion or 76,000 crore to be given in the next 5 years to support at least 2 mega fabs, CMOS mega fabs, at a node maybe 65 or below, then at least 2 display fabs. And then another category is of semiconductor fabs. As you know, semiconductor fab, they don't need that kind of capital outlay as a CMOS or a logic or a digital fab needs. So there can be more, even 10 to 20 kind of fabs pertaining to gallium nitride, gallium arsenide, solar. We have a lot of sun, and there are a lot of innovative multi-junction solar cells which have a efficiency of more than 40%. But we are not making, even for our satellite use, we are just importing those devices which are used in the satellite solar panels. So that is the second category. Another is the assembly and test, that OTMP or ATMP or OSAT services, because wafers, after wafers, post fab operations, testing of wafers, packaging of wafers, testing of devices, qualification of devices, and all those things. Those are, again, not that capital intensive as a CMOS fab. And then another category is of the design, fabless design. India already has made a good mark in the design, but unfortunately, we don't have our own IP. We are good at making designs if somebody gives a specification. But what we need is, we need ourselves to design the specification, to design the product, to make it. As you know, manufacturing is, today in a CMOS circuit, manufacturing is not like very tough. If you have a design, if you have an idea, you can get it fabricated, done. And then finding the market, finding the right market. So this is what, in a nutshell, and the government is willing to support close to some 100 fabless design houses. I think they should have been done, because they have announced the policy in the last 1 year. And this fabless design houses is the easiest part, and it doesn't require much of outlay. Government should support the design houses in terms of EDA tools, in terms of at least giving 2 to 3 fabrication services outside. Testing, packaging, it costs around 30 to 40% of the total cost. So all those things the government needs to give to encourage various design houses. And the idea is, at least in the next 3 4 years, we should have at least 4 or 5 our Indian design companies having a outlay of 5,000 crore or more.
Thank you, sir. With that, I'd like to, invite Devesh to, give a little bit introduction about Global Foundries and its operations in India, and is there any plans to help India to achieve its goals in manufacturing?
First of all,
Thanks, Mr. Venkata, and I'd like to extend my thanks to entire VLSI the 2023 team for giving me this opportunity. So let me start with a quick overview about the global foundry. So as name says, it's a true global foundries, and we are a global semiconductor manufacturing company, having these fabs in the multiple locations in the US, starting from Malta in New York State, Burlington in Vermont, and then we have fabs in the Dresden in Germany, and Crolles in France, and in APAC region, we have multiple fabs in the Singapore. So as I said, it's a true global foundry, considering the footprint across the globe, and we provide solutions to our customers around the globe. And also, not only in the fabs, we have multiple R&D centers, design and development centers across the globe. And GF India is one of the largest design center. And not only it's the largest design center, also it's unique. Maybe I'll spend a few seconds why I am saying it's unique. So we have this GF India presence in the Bangalore, in the Manata Tech Park, and we started our operation in 2015. And in terms of the uniqueness, so the center has all the components or the teams related to the VLSI design, starting from very first, like a device physics or device modeling, to the TCAD, process design kit, to IP and design, even manufacturing support and services, although it's a remote. And we have a very strong team over here in Bangalore who do the support for the fab operation across the globe, whether being Europe or Asia Pacific or in USA. And also we have the pre and post fab validation till the silicon validation. So it's a complete ecosystem we have. That's why I'm saying it's unique, starting from your device to the complete silicon validated the IP or the products. So that's a quick overview about the Global Foundry Corporation and more specific about the Global Foundry India.
Thank you, Devesh. And with that, I request Anand to give a little bit background about TestSolve. As I understand, you are very focused, one of the leading players in test engineering, which is an integral, a key component in the manufacturing itself. Please give us some background about TestSolve and your future plans here.
Thank you very much, Venkata, for the invite and also the VLSI Forum for inviting us. TestSolve. TestSolve is actually a global player. We are located in 12 countries. In India, we are in 7 different locations. We have offices and people working in US, in Canada, in Romania, Japan, Taiwan, China, Malaysia, 12 countries. We are an 18-year-old company which started in 2004. It was started by really visionary. Rajamanakam, who was our first CEO, Srinivas Chinnamili, our current CEO, and Mr. Veerappan, who is the Chief Operating Officer. 2004, I don't know if anybody in India thought about testing silicon, right? So we started with a 50,000 square foot office in Bangalore with the first tester. Testers started coming to India from all these big design houses and tech MNCs only 10, 12 years ago. But 18 years ago, we had a tester in-house in Bangalore. We had FA capability. We had FIB capability in 2004. Design houses were using FIB only in the last 6 or 7 years. So that is how we started. That was in 2004. We wanted to develop the infrastructure and for ourselves. So 2007, we found the biggest component that we needed to develop was PCB capabilities for our test equipment. So we acquired a PCB company in 2007. Today, that's the second biggest acquisition, number of engineers working. We have about 250 people just designing load boards for testers. We did not want to make it a captive market just for us. We opened it up for any user. All tester manufacturers partner with us to build their load boards. In fact, they share the designs and they give us the early indications to what the test head and what the layout will be. So we started that, and now we are a global player even in tester hardware design. In 2009, we started a complete reliability and package qualification capability at TestSolve. Today, we have lots of test chip manufacturers, IP manufacturers, and fabless vendors who use our services for qualification of the product. We also moved from just PCB design to package substrate design. We design substrate packages for many customers. We acquired, around 2010, we acquired a IC design company to start supporting IC design, because we said we did test, next it was DFT, then it was design. So we wanted to move up the ladder. We acquired a digital semiconductor company for IC design. 2013, 2014, I think we got acquired by Hero. Hero is our owners today. 2017 or so, we acquired an analog design company, 2016, 2017, where we were able to offer full analog test services. I'm giving you all of these steps to just show how we progressed, because in 2020, we designed our first chip where we got a test spec from the customer. We designed, we got it fabricated, we tested it, and we released it to the market on a customer's behalf. So we have, in India, we just want to show we have the capability to do all of this. Not only did we design and release a production-ready chip, we also partnered with other vendors where we designed, fabricated, and also tested IPs about IP in a test chip. And we are using that IPs to develop SoC, and we will be doing the fab out of this in a month or so. In 2020, Novatelus also acquired some percentage of our company. And 2021, we opened up test floors in San Jose. So we have a test floor in San Jose. It's not the other way where US is doing it here. We did it in San Jose. Next week, we are opening a test house in Austin. So this is the capability that TestSolve developed, and we are very proud of this because we are basically an indigenous Indian company that has come up to this level. Okay, thank you very much.
Thank you, Anand. We are very impressed with your design skills and all that stuff.
Yeah.
But the topic is, can you do anything for the manufacturing? Are you planning any OSAT or move up the food chain?
Yes. When we talk about test services, right, at the test houses that I talked about,
Yeah.
these are all engineering test program development, right? So when you talk about manufacturing, we have to do a final package test program release, and we have to make the volume manufacturing happen. So we have the capability to do that. In fact, TestSolve ran a small manufacturing floor for prototype in Bangalore. We have that capability also. The main goal for us when we started in 2004 was to start a OSAT. In fact, we had land already bought in Perambur, and we wanted to start a OSAT for package testing.
Thank you. We want you to get back to that original plan. So with that, let's talk to Suraj, and he will give a background.
Just one, but about the chip that I talked about, if anybody wants to look at the chip that we taped out and tested and released to production, it is available in our booth. you can go look at that chip.
We'll do that. Thank you. Suraj, I will hand it over to you. You are one of the key players in this whole ecosystem.
Thank you. Thank you, Venkata, and thanks to the organizers to give us a chance to present to the design community. So the first thing I'm very happy about is we have very strong association with all these players. With SEL, a lot of our equipment is in SEL. Global Foundries, we were one of the big suppliers of equipment. And TESOL, we were one of the early investors. Applied Ventures invested long time ago. So Applied Materials, for those who may not know, is the leading semiconductor and display equipment manufacturer. So just from a very basic perspective, when you make a chip, there are about 1,000 process steps that a chip goes through, and any electronic item, semiconductor item that you have would have gone through one of those steps with an Applied Materials equipment. Our company is 50 years old, Silicon Valley, California based, about 26 billion last year in revenue, but the industry is very R&D intensive. So we invest close to about 11% of our revenue every year in R&D. So this year we'll be investing about $2.8 billion in R&D. So that's one big aspect which will continue. Very IP rich, about 16,000 patents, and also very diverse. So we have close to about 27,000 people in 18 different countries, 90 different locations. From an India perspective, we've been in India now for 20 years, and we have 7,500 people in 6 different locations. Most of our people are in Bangalore and Whitefield, but we also have a presence in Mumbai. We have a R&D facility in Mumbai where we do a lot of cutting edge development for the company. We also have a facility in Chennai, one in Delhi, one in Pune, and one in Coimbatore. And we are growing in India mostly based on the capability over here. What we do here is design, equipment design, product design, software design. The IT for the company runs out of here. And we also do a lot of leverage of the local ecosystem in a lot of new areas, especially the new digital areas, algorithms and things like that, where the company is looking at coming out with solutions. Then can we do manufacturing? So one of the reasons I moved to India 15 years ago was when Applied ventured into the solar field, right? So the first turnkey factory for Applied Materials was built in India, in Noida, in Mozambique. So manufacturing definitely can be done, and once we are able to move this forward in terms of any semiconductor manufacturing in India, Applied will be front and center of everything that happens here. Supplier development is something that we are doing right now to prepare for this to happen.
Thank you. So you are gearing up for the manufacturing in India?
Yes.
Wonderful. So let me come back to Jatanaji. So SCL has a special place in my heart. I started my career in 1985 with a 3-month internship in SCL. That's when I wore a bunny suit and went through the whole manufacturing chain there. We know that SCL is like founded in 1985 and was the first fab in India. When people say that there is no fab in India, I countered that. So we'll let Jatanaji give a little bit of history about SCL and see, maybe he has some views on how to make it world-class fab in the near future.
Sure. So I will start with the initial remarks from Dr. Venkata, that India has a chip manufacturing facility for the last 35 years. You see, SCL was conceived in late 70s, And first production batch came out in 1983, May 1983. It was a 5 micron CMOS 4-inch wafers. It was a TOT from AMI, American Microsystem Incorporates. AMI was a big company those days. They gave TOT to us and to Austria. So Austrian government, it was also a government company, government PSU, they named us AMS, Austrian Microsystem. So 5 micron and US also was almost, we were only one node behind. And in fact, initial batches were NMOS and G-line, sodium lamp, 4-inch wafers. Maximum operating speed was those days 3 megahertz, 4 megahertz. After TOT, it was planned to develop our own process R&D. And design was over, in those days, full custom or gate arrays. The standard cell library concepts came quite later, 10, 15 years. Software was not that powerful. We used to do the layout and put it on a paper and see those metal lines are not touching each other. There were no software kind of thing in those days. But agreed, designs were also not that complex. So 2416 was a wall chip, 9495 pulse dialer. So those were the chips which we were making. We did our own 5 micron to 3 micron, 3 micron to 2.7 micron. Then in 1988, there was a big fire. Everything got burnt. The fab got burnt. We were giving some telecom chips to defense, DRDO. It was a 7-set chips. Defense told, we want those chips. You do whatever you want. So we hired AMS, Austria, because it was the same technology. Now that defense people say, you cannot give up a design to a foreign company because the Ministry of Defense will never allow. So you have to manufacture yourself there. So we were a team of 4 or 5 engineers used to be stationed there, AMS Austria, and running those batches. So I also went there and spent some time there at Austria. And while we were also developing our own lower nodes, after that 2.7 micron, 2 micron, 1.2 micron, 0.8 micron, double poly processes, E square, PROM, 10 volt, 12 volt, these all processes were developed. And then after a fire, there was an inquiry and cutting the long story short, a new fab came out with the 6-inch wafer size, I think in 92, 93. We were running 0.8 micron successfully for around 9-10 years. Lot of devices were made, many devices for defense applications. PSP-1, PSP-2 for sonar, then there was a Prithvi missile, PCM encoder for there. Many, I think more than 70, 80 ASICs for critical defense applications and for space applications were made during 0.8 micron era. And then finally, it was transferred to Indian Space Research Organization, ISRO, in 2005, and we decided to upgrade to 0.18. It took 3-4 years. Presently, we have a 180 nanometer, 8-inch DUV lithography, 248 nanometer, around 8 to 10 aluminum mask stack. It's an excellent process. In-house, we have developed 5 volt, 20 volt, 24 volt, bipolar, and a lot of products have been made. And we have an installed capacity of you can say close to 1,000 wafer starts per month, total around 12,000. And it can be upgraded to around 20,000 wafer starts per month. This is the CMOS foundry, and not only the fab. There is a lot of paraphernalia which goes into the fab. There are more than 100 chemicals and gases. We have a nitrogen plant, hydrogen plant, oxygen plant, DI plant, power plant, fire brigade, all those things. And we have the manpower who can run all those plants. It's not that easy. You have to 24/7, you have to run that. You have to maintain a particular clean room. We are maintaining class 1 clean room, class 10 clean room throughout the fab. It's a big fab. I think some of you might, if you get a chance, you please visit that. Excellently maintained fab. This is the CMOS. Then post-fab operations. As Tessol explained, there a lot of activity goes into it. It is quite expensive. Fib, failure analysis, packaging. We have a ceramic line because we were supposed to make devices for defense and military use, and their plastics are not used. SCL also has a gallium nitride G4 reactor, it's a MOCVD, and then G3 reactor, which is a gallium arsenide reactor. We don't have we are working on to develop a GaN and a gallium arsenide processes. We are working on that, basically the photodetectors on gallium arsenide and gallium nitride basically for RF applications. You see, initially, as you rightly told, we have a chip manufacturing. Only thing is, it is at a very limited scale. Ecosystem also exists at a limited scale. Only thing is, we have to optimally use that. So at least we have to demonstrate that we can fabricate 1,000 wafers. We can upgrade that plant to 2,000 wafers. So at least we have to show that we can fabricate 2,000 wafer at a reasonable yield, which is 90 to 95% is expected in that geometries. 180, and that plant can be upgraded to 90 nanometer with a very costing with a budgetary support of around 1,000 crore or so, and you can get 2,000 wafer starts per month easily at a 90 nanometer node. Only thing is, design we should have the market, we should have the product, we should have the buyer, we should have the user, and for that people are asking for a lot of reliability data and things like that, which I, in shortage of time, I will skip those things. And
thank you, sir. Thank you. See, I just want the whole audience know here, SCL is a hidden jewel in India. And you have done phenomenal things there, what you accomplished with whatever limited resources you have. And we hope to see SCL as a world-class foundry in the near future. Thank you. With that, I will come back to the real topic of the today. We want manufacturing to happen in India. See, there is no second guessing on that. And the central government has put $100 billion on the table. They are willing to fund up to 50% of the capital expenditure. And some of the state governments are coming forward, including Telangana government. They're saying, we're going to give you additional money, probably 10, 20%, whatever it is. With all that stuff, we still haven't seen a leading foundry in the world coming and announcing that we're going to set up a fab here. But there are a few announcements. But one of the challenges I see here is, let's say somebody wants to set up a 28 nanometer fab. Even though let's say we get all the money lined up, we still need the process technology. So where do we get it? Shall we go ahead and invest in R&D, or shall we go and partner with peoples? This is an open discussion here. I like to, one of you raise your hands and start talking about it, and we will share our opinions on this. Maybe first we will go with Anant. Yeah.
See, from what I see in the industry, right, it is not just one technology you buy and then you have this running all the time. There is a very big example. National Semiconductor bought Cyrix Technologies thinking they can use their main fab to keep building x86 processors. They were very wrong, because if you want to change the speed of the frequency, your fab process has to change. And process changes are not something like you just tweak a button, it happens. There's a lot of R&D that goes behind it. When you have R&D, we are not talking only about your fab R&D. When you talk about R&D, you're talking about the physics of the devices, you're talking about mechanical engineering, your step size and things like that, where your light physics, which is lithography, all of that come into picture. So R&D and this fab technologies go hand in hand. I can't just say I buy a 28 nanometer technology and it will run always.
Your thoughts on this?
Yeah, I agree. Actually, in a process, you can have a TOT of one baseline process. There are a lot of flavors, or whatever you can say, a lot of process options. And those options have to be developed. And what is missing in India is though we have good strength in IC design, but we lack in designing a transistor. And I have seen a lot of work, a lot of PhDs going on at various academic institutions on TCAD. But TCAD is one part. basically it has to be done on a machine. TCAD will simply say, yeah, grow a 5,000 angstrom PR. But when you start doing it on a machine, it's not that easy. So in 180 nanometer also, there are 450 steps. Each steps have to be done very correctly. You can imagine in a node at a 45 nanometer, the number of steps will be close to some 700 or 800. Geometries are so small, there is no scope for rework. One step is wrong, your yield will be affected. So we have to, what is lacking is, the manufacturing is itself a technology. Designing a transistor is another, the physics part, the mechanical part, and the engineering part, and then how running on various machines, on the process tools, then the failure analysis part. Because finally, any, you can say, company can sustain if you get a 90% steady yield. Otherwise, there is a cutthroat competition here. So you cannot maintain that. So unless, now coming to that point, can we have a, why we are not getting fab for the last 10, 15 years? My personal view is, it's very difficult for any player other than top 3 or 4, Intel, TSMC, Global, Samsung, I think that's all, to set up a fab here, make it commercially viable at below 65 or 45. And I don't think any combination of 3, 4 players will be able to make it commercially viable. This is what I think, because I have worked 30, 35 years in this industry. To make money out of it, it's very, very difficult.
But
now,
I have a rebuttal for that. If you invite all of these companies to come and do it here, why would they have to come here? They already have facilities set up, and it will be cheaper for them because here now you have to set up the infrastructure.
I agree. That is why the government is giving 50%. If Global Foundry, if they have a need to expand their capacity, expand their plant, definitely they will try in the existing plant. But here the government says, we give you 50%. You have to spend 50% only. So that is the reason. But still they are not coming. Still they are not coming. This means still, even I am spending 50%, then also it's not viable. What I mean is, how do we start? We have existing manufacturing bases in the country. KTEC is one, SCL is one, it's a beautiful plant. As you have rightly said, anybody can visit that. But we are not utilizing that. It can be, we can do 2,000 wafers. At the existing node, 180. You spend 1,000 crore, you can do 90 nanometer. And now you will say, who is the buyer, who is the user? Buyers are there. There's a huge demand in DRDO, railways, your NTPC power plant, all processors in the atomic plants. We were talking to that, and Professor Kamakoti also, that processor, we did at SCL, and they say you cannot put a processor, which is a foreign made, at a nuclear power plant. You cannot put a processor in a missile. You cannot put a processor in a satellite. So railways, we were doing a chipset for railways, huge demand. So in our core sector, we have our ISRO, we have our NAVIC. Where is the ground electronics? You don't need 20 nanometer, 24 nanometer. All government buses, you put those GPS system enabled, all trains, you put that. All your ships, boats, you put those. Those can be done. So, but people have to think, we have to demonstrate we can manufacture 2,000 wafers every month. Ecosystem will expand. Right now, we are doing only 50 wafers. Government is already spending 500 crores to sustain that. And we are doing only 30, 40 wafers in a month. If we do 2,000 wafers, maybe nobody's buying, we will throw in the dustbin. Only thing, instead of 500, government has to spend 530. But we will demonstrate, look, we are manufacturing 2,000 wafers. And you can, slowly and slowly, you upgrade the node, upgrade your manufacturing level. Nobody will come set up a plant for 20,000 wafers starts per month. It takes 3, 4 years, 4 years. After that, another 1, 2 years to ramp up the yield to get 90% yield. Commercial viability is doubtful. It's not that easy. Only Global Foundry, TSMC, Intel, they can make it. But a new player, no way. There are around 6 and 7 verticals. I think I can speak the whole day on that, but due to constraint of time, so I will.
So all of you guys should read a book called Chip Wars. It captures a lot of the history of semiconductors. All countries have gone through this. No country had a 28 nanometer fab come and sit and get them started, right? Everyone has to start at the ground floor, and I think I agree with you with start with what we have. If we have some manufacturing capability, get better at that, start getting out products, make it commercially viable, that's how we will need to go. I think if we keep waiting for somebody to come and build a 28 nanometer fab here, it's not going to happen.
All right.
Devesh, you want to add anything to this?
Surely. Yeah, I want to, maybe I'll go a little back here. So now it's not question about setting up a semiconductor manufacturing fab here. You heard Dr. Jatana, already we have a fab, the SCL. And I heard the other presentation from Professor Nayak, the GETEC, the fab in different, I'll say, diversified technology. And Dr. Jatana said it very rightly. Now it's about in terms of the scale and the market. So our focus should be whatever the existing infrastructure is, whether it's SCL or whatever, how we can help that ecosystem in terms of bringing that scale or the market. And I'll give my perspective from the global foundry side. As you know that this setting up manufacturing fab is a complex process, lot of investment. And in that way, Global Foundry, as I mentioned, that has a unique presence here in India. How we can leverage that, even whatever the fab, you say SCL or whatever we want to scale up, increase the capacity, the market capture. There are different ways where we can collaborate and help on that one. Let's talk about that when you're talking about the scale up. The type of the skill required in the semiconductor fab is totally different from your design house. Maybe you don't need like masters and PhDs for that. They require a lot of like technicians, the operators, that maybe a diploma or maybe a Bachelor of Science may be a very good fit for that. But then on top of that, they require a different set of skill or training, like some sort of the basic understanding of all the VLSI fabrication process. Hands-on experience on this starting from your wafer cleaning till the metallization. Do you have infrastructure? Do you have ecosystem for that? Suppose tomorrow we need a couple of months or year down the line, 1,000, 5,000, these such technicians. Do you have ecosystem for that? I don't think so. Maybe like we discuss about like other presentation from GETEC. They have really nice infrastructure. Can we scale that up, open up for that such type of training and such type of the hands-on exposure? And from industry side, because we are expert in that domain, we can provide the consultancy. It may be like a course development, what exactly needed, a type of course, a theory for the manufacturing test or the packaging, and also having a remote manufacturing support from here. We can share our experience and the leverage from there to train these resources for whatever the foundry, whichever comes into that. So that's my view.
Actually, sorry to interrupt you. So we're kind of talking about the skill development, as I understand, right? You know, okay, let's move forward. There are fabs are going to come. There's money on the table. Now the next challenge is going to be finding the right manpower, right? You know, we've been investing in training IT people, chip design engineers. So we already have the critical mass in there. So now the next challenge you're saying is you know, how do we find the talent to run these fabs, to operate these machines? So I think Anant wanted to say something.
I just wanted to talk about the manpower.
Yeah.
Let's take example of Apple. How did they scale up? Right? Same kind of technicians, the same kind of skill set they needed. How did they scale up? I think they had a will or they wanted to do this. For all the other companies that we talked about, what is in it for them? Right? If it is an India market only that they want to capture, they are already captured it. There's nothing that they get out of coming here and developing the fab. I think mostly the nationalization where every nation wants to keep it secret to itself is hurting us. Skill set capabilities, I think we can develop. Let me give you an example. If you go back 20 years ago, 25 years ago, when one of the first IT companies or the chip companies, an analog company which set up in Bangalore, they wanted technicians to do characterization of their IPs. We didn't have, at that time there was no skill set available because none of our schools were catering for it. But TESOL was able to develop within 3 months 150 engineers, technicians who could go help do the characterization work. So that capability I think we have in India.
So that's good. So we have extreme, okay, go ahead, sorry.
Yeah, the capability is there, but we need to build the ecosystem where this capability comes out, right?
Exactly.
If
Yeah,
a
the
pump
Apple
goes
example,
down,
right?
and you need the person to come from Singapore to fix that, your equipment is down for a week. So that ecosystem we need to build. How do you make sure that your supplier or OEMs can help with stuff and do that locally in the same time zone, right? We need to make sure that.
Just want to make a small point. If you buy any machine, if you do a comprehensive maintenance, it will cost something around 10 to 15%. When we started at SCL, the first level of maintenance, we got our engineers trained because these VLSI fab tools, they're highly sophisticated. There is minimum 3 months, 4 months training of an engineer, and he only can handle and operate. It's not that anybody can go and touch that machine. It's not allowed. So first level of maintenance has to be done in-house, and after that, you can call visit-wise. So you can overall, you can make it a cost-wise, you can make it minimize. Another, what I find is, it's a clean room. Clean room, it's a protocol. One has to follow. And discipline is very, very important. If you sneeze or something, SCL was a government sector, there is a shift, and you go at 9, then there is a tea time, 10:30, people came out, then again go, there is a lunch time, again go. So 1.5 hours, we find the yield is drastically falling. So this is what we told. This is not possible. Clean room, they are throwaway garments. They cannot be reused. And moreover, more entry and coming, the particle count inside, you cannot maintain that. So we told a person, once he goes inside, he has to stay 5 hours there. No tea, no washroom. After that, he can go home. And we make a special provision for that. So you see, for the last 6 months, I am working in a hospital. I am attached with a surgeon and a heart surgeon. I have seen those surgeons, they stand, open heart surgery takes 10 to 12 hours, and a surgeon is standing there 8 to 10 hours. Nothing of that sort. And they are 50 plus age people. So we need discipline, clean room discipline. Fab at a lower node, it's very, very particle count to maintain defect density. It will kill your dice, it will kill the reliability. So all those things are not there. Why those Singapore, Chinese, they are successful in that one, not even US. Even the same process, US yield will be different. That's why the mass manufacturing, they have shifted. And that's the reason. They're also like us, though we may be more worse than Americans. But
Jatanaji, wonderful message. The message is clear. We do have the talent force. I don't think the talent is the issue.
Talent is there.
We can make the fabs manufacturing happen, but the discipline is needed to do. It's not like tea breaks and WhatsApps and go in the fab and start using WhatsApp is not going to work. So I think in the best interest of the time, Jatanaji needs to catch a flight soon. And we all do agree that we want to bring up manufacturing in India, right? It has to happen sooner or later. If you look at the government support, it's extremely good. We need to really thank the government. The government has come forward. It's put a very liberal and generous package on the table. And as an industry, we have to step up and make things happen. And whether it's fabs or OSATs or if not the cutting edge fabs, whether we talk to Tushar gave an excellent presentation. A GaN fab has a huge requirement opportunity in India. A gallium arsenide fab has a it can not only serve the strategic reasons in India, worldwide also. So with that, I mean, I want each of you to give a quick summary to the whole audience here and the whole industry. What can we do to make things happen in India today?
Sure, maybe I'll start with that. So you heard about that, the stage, and also I'm really also very excited to hear about the recent announcement from the central government, state government, and all the agencies. They're very positive way they are pushing forward in this direction. And you know that maybe 20, 25 years back when we started on the design, software, services side, that was the start. And today we have the state of art in terms of the world class, name any domain or area. And I'm very positive that same will happen in the second, other half, like the manufacturing, testing on that side. And also, as we heard about that some of the recent announcement, either from government side or some of the consortium, I think now our focus should be to, with the existing ecosystem, infrastructure, industry available here in India, how we can work together and make them successful to deliver that result. We discussed about one example about the manpower, skill development. And if I talk about the GF perspective, I said that unique presence GF has. Even we discussed about the gallium nitride technology. GF is one of the premier in terms of this technology offering. Maybe there is opportunity for partnership, collaboration on that one. And also, hope you heard about some of the initiative from Global Foundry side. One is called GF Lab. This is the worldwide initiative. Now we are expanding it in India. And last 2 weeks, we covered at least 7 IITs and NITs. We are going to all the IITs, NITs, tier 2 colleges. Yesterday, we had a discussion with the IIT Hyderabad, Triple IIT Hyderabad, and before that, we had with the BITS Hyderabad. And today, because I am here, I'm planning to meet the Triple IIT Hyderabad in terms of this GF lab opportunity. It's not just only like internship or faculty engagement, it's to the next level in terms of the partnership, the technology collaboration, services, consultancy, whatever. So I think in summary, my message will be lot of the positive, I'll say the push from government, industry, and academia side. Now we have to come together and work, collaborate, and help to make this successful.
Thank you. Anand?
I think I look at it as 3 different steps. First of all, we have to make the world accept made in India as something that will happen. Otherwise, I can create all this.
They're already accepting our mobile phones.
Until Apple came, they did not. Right? So the world has to accept us. Otherwise, whatever we manufacture, we'll have to keep with ourselves, like how Dr. Jatani said, we'll have to throw away the wafers that we are building. Second, we have the talent, but none of the talent is being utilized inside of India. We talked about all the fab, we talked about all design houses, everything. You go out there and see it's us Indians who are running most of it. But somehow we are not able to keep the talent in here and build the talent here. So the academia may need to step in here and try to develop things which we can give to the world. Today we all talked about getting technology from outside. What are we developing and giving to the world? Because once we do that, then there is value for it. Otherwise, we are also a consumer. See, when Global Foundry or TSMC or somebody comes and sets a fab, they are going to take the profits away from them, from us, right? We are just a consumer. They are happy to set it up for us. But we have to have our own indigenous stuff be done here. And again, now fab, all of us said, is going to be a more expensive thing. We may have to take a step back. Let's go do OSATs, just package testing. For package testing, don't go buy the package technology. Create the package technology here with the universities that you're working on, different package material, things like that. Do some research and give it to the world where they'll also come and buy technology from us. And that is when I think we will get there. Just buying technology will not.
Good message, Anant. One quick summary from you, Jatanaji.
Yeah, I think all of us know about Sam Petroda's contribution to the telecommunication area 20 years back. So here, at the ministry level, particularly the MIT level, quick decisions are needed. CMOS logic, I understand, huge money, it might take time, but it should not take much time on fabless design houses. What is there in giving free EDA tools, giving 3-4 batch fabrications outside, and all those things, and compound semiconductor fabs. They should quickly decide within 2-3 months. And then use existing infrastructure. You see, when there was a fire in '88, most of the Singapore fabs, ST Micro, Micron fab, First Silicon fab, they are running by ex-SCL chaps. Many of them will be willing to come back.
Yes.
And they are the people who have worked at the process development at a lower nodes. You bring at least 3-4 people, good chaps, give the keys of SCL to them, run them, and ensure product penetration. Some assure product market. We have automotives as Tatas, Mahindras, definitely they will be willing. So it is possible, but government has to policy decisions, making policies, they have to implement that at ground level, which is not happening. Making good announcements will not work. Use the existing thing first.
Thank you, sir.
Sure. I agree with all the things that people have said. One thing that I would add to all of this is pick areas where there is India demand. Display, right? Television, we are the 3rd or 4th biggest consumer of TV. Everything is important. It's easy to make that local with some small steps. Communications, where there is a lot of inflection happening. How do we make localization of manufacturing a part of that? Auto, there is again inflection happening over there. How can electronic semiconductor be part of our plan to that? So that way, we should have some pull, because I agree that if we build it and you don't have application, you don't have a buyer, this will not be sustainable.
Thank you, and let me do a quick summary. We are at the end of this thing, and I think the message is clear. The government has come forward. They put a very liberal, generous package on the table. The industry has to step up. The 3 nanometer, 5 nanometer fabs can wait. There are other things we can do. Compound semiconductor fabs can happen. OSATs can happen. And at the same time, we also need to focus on fabless startups ecosystem. The government also has a DLI scheme, extremely innovative scheme, extremely thought out scheme, very well thought out scheme. And we should also start having product companies designing chips. Initially, they can be to TSMC, but they can slowly transition to either SCL Foundry or some other foundry. That comes up in India. With that, please give a big round of applause to all the panel members here. It's been a great discussion. Timing is right for India. This decade has to be for India. Thank you all. And with that, I invite next, I invite Subhash. Srini, can you come next? Anant ji, can you please come on the stage and Anant for Anand. With that,
Thank you, everyone. Thank you for that very engaging panel discussion. With that, we conclude the morning sessions. The track presentations will begin at 2:30 p.m. There will be 4 sessions running in parallel. Please review the agenda and proceed to the corresponding venue for the sessions. Lunch has been served. Thank you.
Test and reliability. My first request is for everybody to please move up to the front of the auditorium. It's unlikely that we'll need all these chairs at the back. And I'm sure the speaker would appreciate having the audience close to him or her. So please come on up. And this specially applies to the speakers for the session. There are lots of very comfortable sofas up front. So come up and occupy them. Please make an effort to come up. There are lots and lots of chairs up front. On test and reliability, my name is Adit Singh. I'm a professor at Auburn University. And it's certainly a pleasure to introduce our invited speaker for the session, Professor Ujjwal Gwin, who's a colleague of the University of Connecticut, also in the area of hardware security. He's been a very successful star at Auburn, gathered a lot of funding from agencies such as the National Science Foundation, the US Air Force, and also from the defense agencies in the area of hardware security. He's published very extensively, written a rather well-reviewed book on detecting recycling of integrated circuits. But I won't take very much more time, so I'll hand over to him so that he can have his full 15 minutes.
Thank you, Adit, for the introductions. After lunch, it's always difficult to concentrate. So I'll try to make my presentations a little bit more towards that all you guys can interact. So the topic of my presentation is the complexity analysis of set. So majority of you guys are familiar with logic locking. So we'll say what logic locking is, but before going to that, we'll present a little bit of motivation. So how, what problem we're trying to solve and what's the difficulty and what should be our future directions of solving it. As you all know, the semiconductor industry becomes extremely complex, and now it spans over many, many countries. Say, for example, if you see that the design life cycle, it goes from chip design, manufacturing, then packaging, test, and assembly, and all these different stages, there are many countries involved in those phases. So what you can think of, like piracy become one of the bigger problems. Like when you send your design to offshore locations, then trust become the key component. How do you trust an offshore locations where you basically fabricate your chips? So to prevent that, logic locking was proposed. And you can see there are a huge dollar value associated with the threat, like the piracy. So my talk outline will be, I'll present what locking is, then I'll talk a little bit about the Boolean satisfiability attack, what that is, and then we'll talk about the complexity, why this attack is so efficient, breaking logic locking. And then I'll show some future directions that what we should do. I don't have a solution. This is an open problem, so you might think of finding a solutions, think differently, and who knows, you might find a solutions as well. Okay, so what logic locking is? You can see here there is a very simple circuit. There are a couple of gates, okay? And if you send this design to offshore foundry, what will happen? They can reconstruct the original netlist. And if that happens, that means your IP, intellectual property, is lost. So what you want to do is that you add some additional gates where you can see that K0 and K1, those are attached to two XOR gates attached in the circuit, and depending on the value of K0 and K1, your circuit becomes the original one. So for this circuit here, K0 equal to 0 and K1 equal to 1. So, but seeing the structure of the circuit, you don't know whether the value of K0 and K1. So this is the original locking scheme that was proposed, and what you do is that you keep your key secret and you put it on a tamper-proof memory so that the adversary cannot pick in. Now, what is Boolean satisfiability-based attack? So any digital circuit can be represented as a CNF, that is conjunctive normal form, okay, where we have literals and clauses and conjunctive form. So we have OR of ANDs. That's how we represent any digital circuit, no matter how big that is. And then you perform a mitre circuit that I'm going to present, and that's basically used to find the key, where you can see we have two locked circuit A and instance B, and then what you do, you start with a key K0, Ka, and then you ask the SAT tool to find a input pattern X that basically makes the circuit satisfiable. That means output of the circuit is 1. So that means output of instance A and instance B will be complementary. And once you find that input X, then you apply that to original a circuit which is unlocked. You buy it from the market, okay? And then you know for sure what's the value of Y. And based on that, you actually remove a group of keys, either Ka or Kb. And that's how the SAT attack works. And it's a very powerful attack, means each iteration, you remove a lot of incorrect keys. And the correct value of the circuit is added to the Boolean with the CNF clauses. So when the SAT attack been proposed, majority of the circuits, whatever locking was proposed at that time was broken. And at the same time, that the community has moved towards providing a valid solution, a SAT resilient solutions. And what happens, so many solutions was proposed, and unfortunately, within a very short time, there are attacks that actually breaks those circuits. So you can see here, there are like many solutions, and kind of like you can say, one solution and 5 attacks. So that means each solution can be broken in many different ways. Now we head back a little bit and try to understand why this SAT attack is so powerful breaking the circuit, and what's the solutions that we want to propose, instead of just adding some additional circuitry and providing the solution. So that's basically this talk is all about, okay? So what we see here is that, so when this is a representation of the locked circuit, that K, X is the input, Y is the output. And once you find out the DIP, I mean, it's distinguishing input pattern that provides a complementary output at the mitre, that what you do is that you provide that input to an unlocked circuit and find out Y. So at that point, you know X and you know Y, okay? And when that happens, so you apply that to the circuit. And you can see here, the only unknown here is that the key. And what happens, that this entire circuit now become a relationship among keys. So that means there are some keys, they are related to another keys. And what you can see here is that whenever you had a big cone, and that cone is now broken into multiple segments, and there are few input keys and there are few output keys, and that means there is a relationship. And that relationship makes to remove that lots of invalid keys. So we'll start an example to see how that works, okay? And before going that, we'll try to explain why and how we remove the keys, okay? So there are 3 different situations we might encounter. One is that in every iteration, half of the incorrect key is being removed. Then there are another instances where more than half of the incorrect keys are removed, and some cases where less than half of the keys are removed. Okay, so here there are 3 scenarios. So you can see there is an AND gate, K0 is the output, and K1, K2, K3 is the input. And if you find this relation, so you can see that 8 total, there are 16 incorrect keys, total 16 keys, and out of 16, 8 keys are kind of like correct with K0. So that means there are 8 invalid keys. So in this case, you basically remove half of the incorrect keys. Then the second figure where the output of the AND gate is 1, that means both input has to be 1. And if that happens, so that means, so you basically cone 1 and cone 2, they become disjoint. And you can perform the same analysis. Half of the keys can be removed and half of the keys. So that means you can remove more than half of the incorrect keys in this scenario. And for the third case, where you can see here is that if the AND gate output is 0, so you don't know what's the value of the 2 input. You cannot uniquely identify the input. So it can be 0, 0, it can be 0, 1, it can be 1, 0. So that means in that case, that K1 and K2, you cannot separate. And that's basically what you want as a designer perspective, but the circuit topology is basically mixed with case 1, 2, and 3. And this can be done for the same analysis can be done for the OR gate as well. Okay, so if you have the OR gate, if your output is 0, then you can uniquely identify 0 and 0 are the 2 inputs. If it is 1, then you don't know, the SAT tool doesn't know, and that's where you basically have the complex scenarios, and in some cases you have easier scenarios. Now let's start with an example. So you have this simple circuit, and we locked with 3 keys, K1, K2, and K3, K0, K1, and K2. And those numbers, basically, if you run it in the SAT tool, so those are the node numbers, and that's how the CNFs are written as numbers. Okay, so what happens? The first iteration, you find a distinguishing input pattern. So this is my distinguishing input pattern 1, 1, 1, 1. And if I apply that distinguishing input pattern to the oracle, that I get 1. Okay, say for example. And if I get this 1, then what I can do is that I can perform the analysis that you can see the output of the XOR gate, GK0 is 1, so that means 16 and node 6, they are kind of complementary. So what you have basically that an AND gate, and there are some relationship with keys. So, and you added that clause CNF to the original circuit. So that means basically every iterations you are connecting, you are removing invalid keys. In the second iteration, let's say that 1101 is the input, then you apply to that to the oracle, and you find out the output is 1, then you perform the same analysis, and then you get this. In the third iteration, so you apply the CNF, and then you got the output, and that's it. So you basically expecting that there are 3 keys, so we should have like 8 iterations to cube, but instead of 8, so you basically, the SAT tool basically removes in 3 iterations. And that's why the complexity of SAT actually increases linearly with the key size. And because of that, you basically find out the key in running time. And we perform analysis that shows that linear trend, but it's not strictly monotonic. Some cases you if you increase the key size, your complexity may go down a little bit, okay? And we perform with different analysis with different seeds of the SAT tool, and here also you can see that the complexity goes linearly, but there are ups and downs along the way. And we perform that non-monotonically increasing function because of the input-output pair. What you select is basically removes the key. Say, for example, here, input pattern 1, 0, 0, 0, 0, 1 removes only 1 incorrect keys. And then input pattern 2 basically removes all the remaining invalid keys. So that means the way you arrange those IO pairs, that depends on that complexity. So when you run the SAT tool, So you basically find out some I/O pair actually removes a lot of incorrect keys, and your complexity goes down. You find out the overall key very quickly. Now, we perform some analysis to other SAT resilience tool like anti-SAT. I'm not going to go in details. You probably all know the functionality. So we added two additional blocks, G and G bar. Those are complementary in nature, and then you compensate with the correct key. And here the answer is that if you constrain one of the keys, then you basically perform the same analysis, and you find out the key in one iteration. The same thing can be applied for CAS lock and also TT lock and SFLL, where you have F and G functions. Here that LC and F, they are combined together, and you perform the synthesis. So the synthesis tool basically merges the F function. So the basic assumption is that the adversary does not know the function F, so he cannot recover. But if you perform the cone analysis, then you can have multiple F functions, and then you can perform the same analysis and break TT lock and SFLL. Now I'll go with the last part of my presentations with the complexity analysis. So this is one of the benchmark circuits, C6288, where the authors have shown that the SAT tool takes a pretty large time to break it. And then we perform the analysis and see that the complexity still goes linearly. The key interesting part here is that the unsat. Basically, when your key has been updated, but the last iteration where you need to prove that there are no more DIPs exist, that takes majority of the time. And for this circuit, C6288, you can see there majority of the time is spent on the unsat. It's kind of 99%. And the time is computed between the first two, it's like when you see that the SAT statement when that is being updated. So in conclusion, so this is my overall presentation regarding the complexity analysis of the SAT tool, and then how and why the SAT attack takes a longer time in breaking C6288, it's a multiplier. So the question is that how we're going to achieve a true SAT resiliency in terms of for any logic cones. So what we need to basically implement a sort of solutions where, to me, that finding a DIP is a hard problem rather than just making the SAT attack itself try to build the exponential complexity in terms of iterations, because we can't do it, because when we have the I/O pair, so it basically breaks the internal structure of the circuit into small parts, and you actually perform the analysis very efficiently. Thank you very much, and I'd like to thank my sponsors, NSF and Auburn.
Thank you, Ujjwal. That was a nice talk. I think we have time for a couple of questions. Do we have any questions from the floor? No? Do I see a hand? Yeah, Professor Viren Singh from IIT Bombay.
Thanks for nice presentation and summarizing the overall domain. But when we talk about the complexity, then in what terms we evaluate the complexity? Because your complexity, the evaluation also goes up and down and up and down. So are we fitting that to a linear complexity model, or we are talking about that what could be the worst case complexity that we can get so that one can design the system?
Yeah, it's a very good question. So SAT attack itself is an iterative process. So you construct the mitre, and then you remove invalid keys, incorrect keys. So basically, you run that mitre circuit again and again and again, and then you find out the key. So now when we say complexity, means you start with, let's say that you add one key into a cone and find out how many patterns it needs to break it. Then you add 2 keys, 3 keys, 4 keys, and then you increase the key size and see how many iterations it takes to evaluate that, to find out the correct key. And, and that's basically, that's the plot you see when you increase the key size. So the SAT attack takes more and more iteration. That iteration itself is not monotonic. That means if you have 128-bit key and then if you add one more key, so that does not necessarily mean that you have more iterations. Your iteration count may fall down. So, and that's where that complexity analysis is, that at what instance you apply that I/O pair. Because not all these input-output pairs are same number of incorrect keys. So some patterns remove more incorrect keys, some patterns remove less incorrect keys. So that's where in the SAT tool, when you find out the DIP, at what instance you apply what pattern, that also depends on the circuit topology. And when you add one more key, so you basically change your circuit topology. Your SAT attack is basically start with some random seed and then goes through it. So yeah, so you cannot say it that this is my lowest time and this is my maximum time. So it will vary depending on at what instance you tried at what key. But the overall trend is increasing.
All right, in the interest of time then, let me thank Professor Gwyn again and present him this memento for having presented an excellent talk here at VLSI.
Thank you, Adit.
So our next presentation is on efficient M-based area and test time estimator using machine learning technique. Authors are Darakshan and Ratish. Ratish is here. So both are from Intel. So coming to Ratish's bio, he is a senior manager and DFT architect from Intel. He received his master's degree from IIT Guwahati. So he is having overall 17 years of experience in this industry, and he holds a few US patents and IEEE publications as well. And he is driving SOC DFT architecture of auto-grade SOC. Let's now have Ratish on the stage to talk about the MBIST area and test estimator.
Thanks for the intro. Good afternoon, everyone. Today I'm going to present efficient MBIST area and test time estimator using machine learning techniques. So most of you know that the problem in the MBIST, to get the right MBIST design without any iteration is almost difficult. When I say the right MBIST design, the best optimum MBIST area and better test time, and that has to go through the structural or a physical design implementation upfront is almost difficult. So this talk, what I'm going to concentrate is that to bring the machine learning techniques to calculate, predict MBIST area and test time, and then go with and arrive the right MBIST configuration upfront without going for any iteration, and then associated machine learning, how we arrived into the which model we are going to use it. So today's agenda, I'll give the overview. In that overview, I'll talk about what is the ROE or importance of this topic, and then we'll come to the problem statement, and then which is ML based, what ML algorithms are going to get used. Then come to the proposed solution and then corresponding methodology. We have a result on the actual design. We'll talk about that and I'll go to the conclusion. So as an overview, if you look at, this is the first chart as a number of SOC which we have taken from company internal. In this thing you can see around 5 to 15% of the SOC die area is consumed for the DFT. And second pie chart, you can see out of the DFT area, 65% is for the MBIST logic and 32 is the scan logic. So which means that if you go for a 100 mm square die, around 6.5 mm square is for the MBIST. Come to a dollar number, around 7 to 15 cents. You can just say that per mm square die cost. In different technologies varies, obviously. This producing like 100 mm square die, of a 10 million unit, you have to spend around $10 million for this embossed die area. So that indicates there is a huge opportunity if you make a optimum embossed design upfront. So just a few basic before I go into the problem statement. You can see here embossed is predominantly like embossed controller and interface area. Interface area typically covers like around 76% of the area, and the controller is like kind of 20% based on all our different implementation. So interfaces typically comes with the embossed comparator and then bicerbira logic for the repair, etc. And controller point of view, there's an algorithm, the address generator, data generator, those sequencer, etc. So any of the better embossed area test time or physical design challenges depends on how you group the number of steps, different implementation schemes, etc. you used. Now, coming to the problem statement here, to optimize the embossed interface area or a controller area, what you need to do is that you need to implement, take into the RTL synthesis, all the way it has to go to the structural design and then come back the feedback. So this has to take a different configuration and then do the thing. In real design, we have a lot of constraints like resource schedule constraints. It's almost impossible to take a lot of different configuration, take it forward. So here there is an opportunity where we can bring the AI/ML scheme and see whether we can predict the real embossed area upfront, and we can tune the embossed logic for the optimum area and the test time. So just to touch upon the embossed flow, what we used, or any of the ML flow, we have to have a huge number of databases. We have extracted so many data from the previous design, as well as we have generated some random data that mimics a number of IP embossed configuration. So eventually, at the end of the day, we have a big database where a lot of memory configuration corresponding embossed area and test time. This is the data which we will use for the ML model creation. Then the created model will go for a when the new SOC or a new configuration comes, we can use it for actual area prediction. And then second thing, model creation typically works. What you first start with the available data set, you go and process. Once after, this is called a EDA. And after the process the data, you will split for a training set as well as the test set or a cross-validation set. Some of the training set used for a model creation for different algorithm. And then that you validate with the cross-validation. Eventually, the test data, you will make sure your model is running properly. Eventually, that model can take into the implementation. So the first exploratory data analysis here, the first one which we have looked at is the embossed interface area. When we looked at the interface area, based on your domain expertise, you know number of memory, number of RF, number of word width, etc. Is giving a real correlation with the interface area. Here, if you look at the word width, is one of the highest configuration, highest correlation, which is giving more than 90%. And then that's the right side curve, you can see that is a linear relationship as well. So that is one of the parameters you need to consider. And then from the controller perspective, again, the correlation matrix is drawn with a lot of different parameters. Eventually, none of the parameters are giving, single parameters are giving a best correlation, matrix correlation. If you look at closely, it is coming less than around 0.8 only. Then what we have done is that couple of parameters we combine together and then get a better correlation matrix. That is the one which we use for the model, ML model training. So the graph shows kind of a linear. And then from the embossed test time perspective, again, all available different memory and design parameter, we have drawn the correlation matrix. None of them we could get a better correlation. And there also, we did combining the multiple features and then arrive into the better correlation matrix. That is the feature we are using for a training purpose. So then those features, if I draw the graph versus the MBIST test time versus that new parameter, it's not so linear, but it's kind of things coming in this form. So typical ML, this MBIST area, now you have what all the parameters used for a model creation. Now the steps to create a model. Whenever you create a model with model, you can increase the complexity. As and when you increase the complexity, your training error will go down. But if you overfitting model, if you take, then your test error will go. So we have to find into the sweet spot of this thing. So now the first graph, the MBIST interface point of view. We have taken the polynomial regression and drawn the degree from 1 to maybe higher number. Here you can see the test error as well as the training error is coming to a sweet spot on the degree 2. So in MBIST interface area prediction, we can use the polynomial regression of degree 2. And then second graph coming to the controller area. In the controller area itself is a linear equation itself is giving a good thing. As and when increase the model complexity is not giving an additional benefit. So in this, you can see the other metrics like R2 square for the polynomial regression 2 for the interface area, as well as the linear regression, which is both are giving a better number, which is a 0.9 plus. So in the test time calculation point of view, we have started with the linear regression, and then all the data set what we used is an average mean test time is 105 millisecond. Once we look at the MAE score or like MSC, RMSC score, it is coming to 22 millisecond, which is quite high. Then we started using the gradient boosting algorithm, which is making a better MAE score and RMSC score as well. So for the MBIST test time estimation, we stick to the gradient boosting method. So here, with this, what we have done is that we have created a model for a MBIST interface area, MBIST controller area, and a test time. So now with that model, we have done the testing. After that, it is taken into the actual design. Whenever actual design is coming, you can see this is a different physical partition. Each of the partitions, the number of memory, you will be upfront knowing number of memory, how many number of RF, how many number of SRAMs are there in the design, repairable memory, number of clocks, and max depth, and the total word width. This is the information which you already upfront knowing. Now this information you can take into the model and to predict your or estimate your MBIST area, test time, and other factor. So here, if you look at this second chart, what we have done, the first set of column is shown that the flop count information, what we got it from the actual implementation. We have generated the MBIST controller, taken into RTL, and then did the complete physical implementation, which is the first two column. There is a controller area and an interface flop count. For here we have used for a flop count. It's almost proportional to the total gate count area as well. Then second two column, it is like with the same memory configuration is fed into the ML model what we created. That's the flop count and other information that is reported. Now, if you look at overall, this model is giving around 95% of the accuracy across the partition. And then this scenario we have used for repairable, non-repairable memory case as well. So now from the test time point of view as well, we have looked at for all the partition and then extracted the available information upfront, like memory configuration, design information, etc. And then collected, okay, these are the way information we need to pass into the created ML model. So here, again, the test time is got calculated on the actual, which is the real pattern, what is the total test time on all algorithms, and then what is the ML predicted model, what it is giving. So this accuracy is more than 85% of the accuracy is attained for all the partitions. So with this, like from the result point of view, we have tested like around 10 partition or maybe more than that for the interface ML model as well as the controller area model as well, the test for the corresponding test time as well. So as a conclusion, the proposed model can be used to accurately predict the MBIST area and test time without RTL generation. So the model, what we have seen right now, we have predicted that one. In actual implementation also, it is turned to that the same thing. So whenever we have this model upfront in the design, you can go and tune your steps, grouping, etc., and then tune your hardware, get into the first time right implementation. Now, one of the parameter in this presentation I'm not shown, but there is an XY coordinate of the memory locations can take into the model creations, which will give a little more accurate area prediction as well. Thank you. So with this, I'm thank my co-author direction and then their audience here.
So in your model construction, you mentioned design type was a parameter that you used to train the models, right? So can you talk a little bit more about what were the different kinds of design types that were in your parameter, and what is the typical kinds of designs that you have trained and tested your model over?
Okay, so good question. So the parameter what typically used for the creation here, memory information, the number of memories used in the IP or a design, the what frequency the memories operate, and what is the type of memory. You can have a two-port, the other thing. You have a register file, you have a ROM, you have a RAM, and the clock grouping, and such kind of informations are majorly used for the memory model creation.
What kind of design types or block types? Were they CPU intensive?
Okay.
Were they interface blocks?
This is across the different kind of IP. When I showed the number of SoC what we used in company internal, which is in Intel, like we target the IP for industrial application. There is a target for a different kind of usage, automotive industry. So all sort of IPs are coming. So typically the IP behavior is not that much material here, but what is more needed, the real configuration of the memory that used for the MBIST logic design creation. Basically like MBIST logic, MBIST area is in proportional to the number of memories, one thing. Second thing is that what all the algorithms you wanted to test, what fashion you wanted to test it.
Ratish, first of all, very good presentation, so thanks for the work. I have one or maybe two questions. Let's take the first one. You are able to hear me?
Yeah.
So how this is different than selecting an option in the MBIST, like light MBIST or reduced MBIST, or using the same MBIST for a set of memories?
Okay.
So can you differentiate your proposed ML solution, what it does differently compared to when I have options available, that I will do light MBIST, which will already, let's say, throw out some tests which I already know not required. Similarly, reduced MBIST or common MBIST where I will reuse the same MBIST. Can you comment on that?
Okay, so good question. The thing is that when there are n number of options available where the EDA tool also suggests. So like you can use the, instead of comparing at the memory location, that's what you mean, right? Memory location, you can do the comparator at the source. You can make a pipeline which will give a better area. So different grouping kind of things are suggested, and a lot of EDA vendors supported different features. That is the one way which you can use it. Now assume you are going and using all those features, how do we know whether you can get a better implementation at the SD side? So now you optimize your area. It can happen that your structural design may struggle that to route it properly. You may end up with a higher test time. That anyway we can calculate. But structural design feedback is the problem. Now here in this solution, what we are doing is that we have collected the data for all the previously implemented design, which is given as a better area, congestion, timing parameters. Those informations are already backed into the ML model. Now, using this one, whenever you use these parameters and get it, it consider all those back-end implementation fact as well. So that's what it is.
Thank you. Then the second small question is, you mentioned you even can use this solution for automotive kind of application. One of the constraints in the automotive kind of application is that you want to test 100% inside the memory. So each and every transistor. So you do not want to optimize anything once you have decided that this particular MBIST.
Correct.
Do you think your ML solution still cater automotive kind of testing as well?
Yes, yes. So the optimization what I talked here, it is not with the cost of any test quality. The way is that it is not really removing the algorithm. But in then some way, whenever you do this one, you are not grouping it properly. You have a lot of area, but eventually your test screening will happen with the same algorithm or same thing. Now, if you group it properly, still you can do that one. Sometimes you have a little more test time. It is not like compromising the quality, but at the same time, optimizing the area and the test time.
So just one more question. In grouping of memories, one is how the placement of memories are, and I think you covered it saying that if you have an XY coordinate, it will help. Second is power dissipation. When I'm running either multiple controllers together or I'm running it in sequential. So is your machine learning also taking that into consideration and giving you an estimation about what will be the power dissipation if I run the memory based?
Yeah, that is a good point. As I mentioned, the XY coordinate, there is one more parameter which we considering, or the model is getting improved with the power estimate, power numbers also from the previous design. But currently, we started without that, because getting the power number from the previous design always be a challenge that we plan for our second phase of this work.
Okay, thank you very much, Ritesh. I think there were a lot of questions, and we can take more questions offline. But at the moment, let me present him with his memento and thank him once again for an excellent talk.
Okay, thank you.
Thank you, Ratish. So our next presenter is Sai from Intel. He is presenting a novel AI-based approach for performance validation. So Sai is from Intel. He is a pre-silicon verification engineer. He is graduated from RGUKT and received a gold medal in ECE department. So his experience includes 10th gen processor validation, performance validation of post-silicon cache interconnect, and EPIC. So he is currently working on core level power management and SOC. So his interests are in new methodologies, automation, and making life easier for design and verification. Sai, you can go ahead.
Thank you for the intro. Today I will be talking about the novel AI-based approach for the performance validation. I will be differentiating what exactly the performance validation when we talk in terms of functional validation that we are doing today for each of the IP. And then we will talk basically how exactly AI and ML at least helped us here in reducing a lot of manual effort and giving us the right place to look into. So let me start basically what are the things that we will be going over, right? So we will be talking about the performance validation overview. We will talk about the importance of bucketing in the validation world at least. And we will be talking about the challenges with the current methodology that we have, and the proposed methodology, and we will dive into the steps, what are the steps that we have done across, and we will share the results and findings. And then we will talk about conclusions, and then we will take the Q&A if you have it. So performance validation, right? Unlike functional validation, where you have a dedicated a design expectation that you have, and you try to check the design behavior by writing an assertion or a checker in whatever the language it is, and you basically do expectation whether it is working fine or not. Now, the performance validation, when it comes, right, so all the functional validation will be done by most of it. Because the world is now trending towards the more performance improving cores, right? And we have a lot of benchmarks also that generally evaluate the performance of each of the core, basically. Now, this brings us the importance having a performance validation, meaning whatever the features that we generally introduce to, right? I mean, the IPC, basically, that we generally introduce a feature, we generally expect that this feature would introduce some of the IPC that is going to be such that the product would be sold in the market. Now, these kind of features, when you introduce, you expect the IP has to be correlated with what the design that you have implemented. So for this, there is a need of the performance validation that we have. So for this, right, so we generally take the traces. These traces can either be a directed test that generally the validation engineers do, or this software snippets, or the benchmark snippets that we generally extract. So we incorporate them as the list with us in terms of the QOV, which is nothing but the quality of validation metric that we have, right? And then we run it on both the C-based model, which is basically our reference model, and are basically the design, which is nothing but the RTL. And then once you take the stats out, right, like, meaning you measure performance quantitatively. So this quantitatively generally measures that you have to take a stats out that how the core basically is performing. So you take the stats out both from the C-based model as well as your design, and you take those stats and you generally compare, and then you see if there is any correlation going wrong with any of these stats, basically. And once you identify the miscorrelated traces, right, you identify them as outliers, and then you go ahead and debug basically what is the stat that is going too high. Meaning, for example, right, so let's take an example. When I say stat, right, it's a performance metric. In a hardware, we do present the performance metrics, like what we call PMONs these days. So not only because there are limited number of PMONs, so we also implement test bench related performance metrics as well. So this will lead to a humongous of 2,000 or 2K or 3K kind of performance metrics. It depends on project again. Now you take this, like for example, let's take a STLB miss, or for a simple term, right? Let's take a cache miss. So you expect for one of the feature that your C-based model is expecting it should have a less of 2,000 cache misses, but your actual design is having, let's say, 5,000 or 10,000 kind of cache misses, right? Now this is a huge number. You see a huge correlation over there. Now you have to identify these kind of events. Now, so these kind of events generally are taken, and then will be taken ahead for the debug, and we will debug in the design what exactly catered to this, this correlation, miscorrelation, basically. And that is how we generally identify a bucket owners, and then goes ahead with the debug. So this flowchart, right, this basically talks about the process that I have talked about. So whatever the test, right, or the trace, basically will be run on both C-based model as well as the design. You take the stats out in either of them, and you compare, and you take the IPC correlation among them, and then you bucket on whatever the outlier that you found out, and then you give it to the debug owner, basically, to go ahead and the debug. With that, right, let's understand what bucketing basically. So bucketing is like in any function in validation world, right? So you do have a checker. You take multiple tests inside a regression list, right? You take all these tests failing on a same failure, you bucket them, and you give them basically to the validation owner to debug it. Now that is a classic scenario. So grouping those outliers into similar performance bottlenecks into one bucket is the what we call basically bucketing. Now unlike functional validation, performance validation do not have any dedicated checker where it generally reports at the end of any simulation cycle, basically, or at the end of the simulation. So that makes PV bucketing more challenging because you do not know what exactly is the stat that you have to compare to, such that all the tests that are having a IPC miscorrelation, right? You can bucket them into one and go ahead, you can assign one owner and go ask them for the debugs. So that is the big challenge. And on an average, right, per regression, there can be, with a huge list of 200 or 2.5K stats that you have, right? You identify major stats among them because you can't go and debug each and every stat. So you identify major early like 400, and then you, so of this 10 to 12 regression lists that basically, which are from the quality validation, right? So these outliers, once you identify from these among 400, right, you give to your owner, and your owner can debug them, and he may end up basically, whether it's a correct one or not. And sometimes it can happen that since it is always done around the 400 and you always take the highest correlated one, miscorrelated one, right? So it may end up that the design issue may not be in that particular stat. So you repeat the process, you give it to the another, either him or the other block owner, basically, to ask them to debug whether, if it's on the adjacent area or on the next highest miscorrelated event. So this is a very repetitive process, and it involves a lot of human hours, basically, to go on debugging the design issues over there. Now this calls for an improved bucketing mechanism. So this improved bucketing mechanism basically can increase the performance validation efficiency by finding more bugs, because you are spending your time and you always end up debugging the same issue again. And this can also, have to lead to shuffling of the outliers between multiple owners, before reaching the real owner and increasing a lot of human, debug time of individual owners. So that's what we talked about, right? So the challenges with the current methodology is like it's more time consuming with the manual process of checking what exactly is the outlier on the identified list of stats. And there can be huge number of outliers, and due to the absence of merging technique, right, it is basically involves in the manual bucketing that generally people do. And duplication of effort, because it always may not end up with a design issue, so it always ends up, or it may end up with having a debugged by a different person on a different outlier, basically, on a different stat, I mean. So some IPC stat-based correlated could have a real performance also issues hiding behind it. So this also calls for that it has to be instead of having a manual one, we should have a more accurate or a stat-based one. So due to the manual nature of the stat comparison, limited number of stats into taken. Instead of having with a list of 2.5K or 3K stats, right? You generally look into 400 stats, something like that. So this is what we propose. So why there is a need for a proposed methodology? Why there is a AI/ML coming into the picture, right? So we talk about numbers here. Basically, we talk about stats that generally are extracted both from the seam-based model as well as the design. So you know basically how much the count that we have, expected count, as well as the real behavior. So this data, when you map it out, right, with the entire regression list on one end, with each test, each stat having its own count, as well as the reference count and the design count, and the correlation that is going wrong, right, you have the entire vector with you. So each test, if you take it as a 2x1 vector, you will have a n by m vector, where n is the number of tests in a regression, and m basically is the number of stats that you have. That means you have to take into account of each and every stat that you have instead of focusing on a less number of stats. So, basically we take in the data. The data consists of an event config file and the stats file. So the event config file basically has the stat, and some of the stats, right, are very important. For example, the number of instructions the number of MUOPs retired per instruction, or for a particular software snippet, the number of instructions retired per that piece of OBJ that you load. So these type of stats are very critical, because a small hiccup can could cater to a very huge performance loss. So these will be given with a very high, weightage, and these weightages and the stats basically will be provided in the event config file. And then we have stats file. This stats file basically is the exact file what the counters that you have taken, right? The number of, for all the events basically from the C-based model as well as the design file. And we do pre-processing. So the pre-processing basically involved the number of MUOPs. When I say MUOPs, the micro operations for a particular instructions, right? If you see a huge difference, right? Because of our prior experience, this huge difference can cater to the C-based model issue rather than having a real design issue. So we pre-process it before, and then we give, and then we go ahead with the clustering of the other stats basically. If you look at the flowchart, right? So I hope everyone is seeing the flowchart over here. So we pre-process the number. If we have a micro operation difference, if there is no, then we go ahead with the ML algorithms or AI algorithms that we used. Here in that particular case, we used dbScan and z-score. And you go and check if you have any outlier found. So when you find an outlier, right? If there are more than one outliers, there can be chances that there can be more than one outlier found. So in that case, you check on the weightage of the particular stat. If that is more than, we will compare between the number of outliers that are found, and we will have assign the bucket, the test basically to the highest weightage that you provided as input, right, to that particular stat as a issue, or as a that is a stat that you have to debug on. So that is one case, and then if you do not find any outliers, right, then if dbScan did not provide you any outlier, then you go ahead with the standard deviation mechanism. We use a z-score for that, and then we will try to find whatever is the highest miscorrelated one. And again, if there are multiple stats found, then we use the weightage mechanism to identify whatever is the highest miscorrelated one, and we assign the particular stat for that to debug. So once we have all this right, so we suggest that multiple tests will be, now we have the suggestions made by both dbScan as well as the z-score, right? We now have the suggestion that we have to concentrate on particular stat, which is too correlated, or at least in that particular regression, it is miscorrelated, and then we go ahead and debug that particular one, instead of having a method, legacy where you identify each and every of the given 400 list, right, each and every one, which is having a highest correlation. So now this these algorithms helped us a lot in reducing a lot of, instead of having each and every one, every stat to be debugged, we will have a focused debug now onto that particular stat basically. So these are the AI algorithms that we used, dbScan and z-score. And they are basically run on each vector. When I say vector, the test and the stats, on the horizontal, and it is very basically helpful in identifying the stat which is outlier, and it was also useful for the clustering again. And for the traces where dbScan did not help us, right? We used the standard deviation mechanism using the z-score, and we used to we labeled the highest outlier for the given trace, basically. And these are the results. So we tried this on two projects. One is on the 10 nanometer project, and another is the 7 nanometer project. The regression 1 to 3 basically is on 10 nanometer, and the regression 4 to 6 basically is on 7 nanometer project. If you see, right, the legacy, right? The legacy methodology, we used to have 413 buckets to be debugged, basically. Meaning, we used to have 413, if you see, right, all the events basically has to be debugged. Now that got converged to only 28 buckets to be debugged, 28 stats to be debugged. That's a significant reduction, basically, in the bucket count that we have in a regression. And the same case, right? From the regression one that got reduced from 413 to 28, from regression 2 from 422 to 26, and from the regression 3 to 287 to 27. It's a huge decrease. If you see, 93% reduction rate is what we observed, and instead of having an entire array of the stats that you have to debug, now you have to concentrate only of the 7% of the failures that you have previously has to be debugged. Now let's see how much exactly the suggestion that was made by the ML model, right? How effective is that? Let's see that. If you see the hit rate, right, with the suggestions made by the ML and the AI model, so we have very good hit rate. So if, regression 1, regression 2, regression 3, basically for the 10 nanometer, right? Now we have a hit rate of 71.1%. And on the next regression, once you identify the issue with respect to a particular outlier, you provide a feedback to the design team, and the design fixes it. And you on the next iteration, right, your hit rate basically increased to 76.92. And once you identify the issue with that regression again, once you provide a feedback and you got the design, you run the regression 3, you have a hit rate of 91.67. Meaning out of the buckets that basically that suggested, right, you have a hit rate of 91.67%. That means all the 91.67% of the failures what the ML model suggested and you bugged basically have the performance issues where the design has fixed them. And remaining, right, like any AI or ML model, you cannot 100% rely on that. So the remaining 7% basically had to go through the iterative process again. So to conclude, right, so in this paper, basically we presented how the AI-based approach helped us to improve one of the most important phases of the validation, which is the identifying the right trace to be debugged. And this results basically clearly shows that the solution reduced a lot of duplication effort and goes us into the debugging of the performance issues by recommending the traces that help us in identification a proper set of bugs, basically, which is nothing but the design issues. And it also provided most problematic stats to the debugger, which end up helping us in easing the debug process of individual bucket owners. And to summarize, right, the core idea is to improve the performance validation, but it is not only confined to the core IPs. So any IP basically which has a counter-based method where you can quantify the performance of your IP with respect to a number, quantify it, right? So you can use this quantifiable factor. You can feed the algorithm in, and you can get the best, of the outlier that you can have basically on the performance-related issues for each of IPs. Thank you.
So I have one here. So why did we choose only the DB score and the other
Z-score mechanism?
Yeah, DB scan and
okay.
DB.
We were basically trying to identify basically the multiple clusters that are involved, right? Like we want to group them, all the outliers, group them into a single category. For that, we searched for all the clustering mechanisms. We first used the k-means, but that was not helping us. And our AI, basically our compute team basically suggested about the DB scan, where we do not also, we not only have to rely on the clustering, but we all can also cater to the outlier mechanism that it can suggest to. So hence, we incorporated DB scan in our methodology.
Reason for 7 nanometer and 10 nanometer things?
Those were the projects that were going on. If not, it would have been other things, basically.
Last call for a question for Sai. Otherwise, let's thank him one more time for an excellent talk. And here is the memento.
Thank you.
So the next speaker, Hanumant, he is from Intel. His title, Signal Agnostic Scalable Scan Wrapper Design. The co-authors are Ratish and Anvesh. So Hanumant is graduate from VTU Karnataka. He has like 16 years of experience. He worked in Cadence, Synopsys, PMC, Sierra. And his work is mainly towards the test and scannability. And he published multiple papers in ITC, CDN Live, and holds 2 US patents.
Thanks for the introduction. Good afternoon, everyone. So today I'm going to talk about the signal agnostic scalable scan wrapper. So as we all know, the core wrapping in the SOCs is a very common technique which we have used, across the industry, right? So there are improved versions of the core wrapping, which I'm going to present it today. Let's see the complete presentation to understand that. So first, to begin with, I'll start with the overview of the scan wrapper design, and then what are the current problem or current the limitations within the current wrapper design, wrapper cell architecture, and then I'll explain the scope of improvement in the wrapper cell design. Then I'll move on to the methodology, the ATPG methodology improvement that we can incorporate to get the better results. And then we'll see the results, what we have achieved for some of the partitions in handling with the improved core wrapper redesign. Then finally, we conclude on the how this improved version of the core wrapper cell has yielded the better results. Just to overview, give on the wrapper cell design, right? So today, most of the SoC designs are very complex and having a very large number of gates. So to handle such a large designs, we always break the design into simple partitions and then make them isolated with other partitions to test them independently each other. So in order to have each of these partitions have a higher test coverage, we have to have a core wrapping, judiciously wrapping these ports, only the valid ports. I'll explain what is that valid ports in the coming slides. So, and also now when we judiciously wrap them, there are impediments in identifying these, the valid ports to be wrapped. And we'll discuss about in the coming slide what are those impediments in identifying the valid ports. And now, at last, we'll talk about the proposed architecture to unblock these impediments. The problem statement, we have two problem statement to discuss here or to talk about. The first problem statement is the when we have the bigger partitions, usually we have seen that the number of input and output ports will be very huge in terms of thousands of input and output ports. Now, definitely, we cannot visually inspect each and every port, each and every input and output ports, and then decide whether to wrap it or not wrap it. So because of that, we will have the automated way to decide whether certain ports to be wrapped or unwrapped. So now coming to the problem statement here, there are scenarios where there are data ports, the true valid data ports, which can be wrapped. Now they will remain unwrapped because of the automated way which we have built into the tool. So that automated way generally will have regular expressions which to decide upon whether we should be wrapping it or not to wrap it. So now the example which I have taken here, data in and data out, which you see in the yellow highlighted here. So the ports were actually named as they had a string called CLK or a reset. So which generally we exclude them during the core wrapping. So because that there is a string, the CLK or reset or some test mode in the naming conventions, so these typically they will be excluded from the core wrapping. That's one scenario where the true data ports to be wrapped or now remained unwrapped because of the automated way. Now there is a second scenario where there are some test sensitive ports. When I mean test sensitive port, there are resets, there are clocks, there are test mode entry pins, there are power goods, and then isolation signals. There are many such signals, right? So these signals, by any chance, if we wrap them, then they will lead to test mode entry break, or even can lead to, if these wrapping escaped from all along the design, then if it escaped to the silicon, we may have to lose the test coverage for that partition itself because test mode entry is completely disturbed. So these are the two problem statement which is causing the with the current wrapper cell design. Now let us discuss what is the updated wrapper cell design to understand how this updated wrapper cell design will help us to overcome these issues which I explained. The first picture, what you see here in the left side, is industry standard wrapper cell design, where the cap enable, which you see in the top left side picture, right? The mux select line, the cap enable will be a static signal, which will either 0 or 1 depending on the input or output wrapper cell. And then in case of in test, if it's an in test mode and if it's an input wrapper cell, then it selects the wrapper cell path or the wrapper flop path, which will be from the flop which is shown here, right? Now, in the industry wrapper cell design, currently the proposed solution addresses the problem considering the following 3 design factors. One is the design efficiency, which means that how to modify this the existing wrapper cell so that we don't need to build the new methodology or new flow as such. Instead, updated wrapper cell design itself, we make it as a design wrap or design wear cell, and then we can call this during the scan insertion. So that's the design efficiency. And the second one is handling the post-silicon debug efforts. So in case if there are some ports which are incorrectly wrapped, how can we handle that during the post-silicon without even fixing the design during the recycle? Third item, reducing the DPPM. So which means that as the improved with the improvised wrapper design, we can freely wrap all the ports. When we freely wrap all the ports, we will have a very good coverage, and hence we will have a reduce the DPPM. So the proposed solution has below recommendations. One is the hardware change. The hardware change, as you see in the bottom of the bottom picture, the proposed proposed wrapper hardware. So the second is software updates. Software updates as such, software need not be updated. Just the guiding the ATPG tool to handle if some wrapper cell to be excluded during the ATPG, we can do that on the fly. So as you see here in the proposed wrapper hardware, there are 3 gates being added and 1 additional signal, which is called a plain shift enable. The plain shift enable is a regular scan enable, which is different from the one which you see in the wrap shift enable. The wrap shift enable is actually will have 3 different wrap shift enable signals, right? Depending on the input wrapper chain or output wrapper chain or a core chains. So these wrap shift enable will be values are different for these 3 types of chains which we see in the design. Whereas the plain shift enable is a plain scan enable, which will be routing into this updated wrapper cell. Then there are 3 additional gates which I discussed. Now let us see in the coming slides how this updated wrapper cell will help us in the improving the coverage and handling the design bugs for the unwanted wrapper. As you see in this picture, so in the proposed wrapper cell, we have explained all the operating modes with the updated wrapper cell. So the first thing is what I explained earlier with the regular current industry standard wrapper cell, right? The cap enable is a static signal, which sometimes it makes the wrapper cell path instead of from the input port, okay, or output port, or to the output port. So that actually limits the, if I want to exclude the particular wrapper cell from the wrapping, then that will limit that that cap enable will limit us being a static signal. So with the additional plain shift enable being routed there, as you see in the gate, the AND gate on the top, right, with a bubble on the plain shift enable, it is taken care in the shift mode. It is clearly taken care that during the shift mode, any wrapper cell will be in the transparent mode, which means that it's completely like functional path only. There is no wrapper cell path being actually visible to the design at all. So during the shift mode, with the plain shift enable being 1, that itself will take care. The input, every wrapper cell will be in the functional path. Now coming to the func mode, of course your plain shift enable will be 0, which make the last AND gate as a transparent, but the cap enable will ensure that in the func mode, that being a 0 will ensure that the updated wrapper cell will not have any issue for the functional path. So now, shift mode is taken care, functional mode is taken care. Now, the only mode is left is the capture mode. In the capture mode, now with the updated wrapper cell design, we can deal the any wrapper cell. Any wrapper cell, if you want to bypass it, we can deal that with a ADBG constraints or a add cell constraint, as you see in this picture here. So if you want to disable the wrap on any port, it's simply defining the ADBG constraint or add cell constraint on the current wrapper cell plus the preceding wrapper cell as a add cell constraint as a 0. So which will ensure that the targeted wrapper cell is completely bypassed during the capture mode as well. So that way, it's any port to be disabled from the wrapping, it's easy to handle with a simple ADBG constraint itself, and we don't have to bother about particular port to be wrapped or unwrapped during the scan insertion time. Coming to the result section, of course, we have done this updated wrapper cell design on a multiple partitions, but for simplicity to explain, I've taken 2 partitions to explain both from the coverage point of view as well as the handling the design bug point of view. So to discuss about the first partition 1, with a standard wrapper cell architecture, we had a structured coverage of 95.88. Whereas in the proposed wrapper architecture, we got a coverage of 98.91. This happened because there were a lot of ports which were having the string called CLK or a reset, but they are purely data ports. So when they are purely data ports, they are supposed to be wrapped for a better coverage. So because of that updated wrapper cell design, we had an improved coverage of 98.91 on this partition. And as such, in this partition 1, we had no silicon issue as such, to talk about. Now there is a case number 2, the partition 2, where structured coverage was 98.7 with the standard wrapper cell architecture. Now with the improved or a proposed wrapper cell architecture, we had a coverage of 99.17, so which is having a benefit of 1.1% improvement. But there is other point to be noted in this one is handling the design bug. So there was a design bug identified close to the tape out where partition boundary port controlling the free running clock of the PLL, right? Exiting from because when we have a hierarchical DFT methodology, the ports PLL will be sitting in some partition, but the targeted partition may be different. So the signal which is exiting from the partition where the PLL is sitting, that before exit of the partition, it was wrapped. And the targeted partition, right, where the input ports were actually not having a conventional names or desired names of a clock in their string, we actually get wrapped actually, which led to the silicon issues. So now, once we identified that with the updated wrapper cell design, it's we could define the add cell constraint and add ATPG constraint on the targeted port and also the preceding port, and hence there was no issue on the clocking part of the design, and even the silicon went successfully with that. So if I go with the standard wrapper cell architecture with this bug actually, now we have to live with the bug, and if you found a issue in the post tape out, the impact is the at-speed testing of the affected clock domain will have to be let go. So impact in the quality of the chip. Now with the proposed wrapper cell architecture, any undesired wrapper cell can be disabled at any point of the design phase, be it pre-silicon or be it post-silicon. We can handle that at any point of time, and hence providing the better results from the coverage point of view as well as handling the design bug point of view. Now, on the conclusion side, as I mentioned, right, we can freely wrap every port in the design without even worrying about whether it's a clock port, test mode, sensitive port, or the PLL port or any ports like that. We can freely wrap all the input and output ports, and then based on the during the simulation or based on the debug, if any ports to be disabled from the wrapping, we can ensure that we define the ATPG constraint and add cell constraint, ensure that that particular cell is bypassed, and you will have a better results from the coverage point of view, also design handling perspective. Yeah. So this is all I wanted to talk about as part of this presentation. Thank you. I thank my co-authors Ratish Vitil, who just presented to 2 sessions before, and also Anvesh Gadi for their contribution in this. Thank you.
Thank you, Sai. We can take a couple of questions.
I have a question. So what percentage, when you implemented this on a block, what percentage of IOs were not desirable? Because you added on every pin of the block.
Yeah.
So when you came to actual pattern generation, what percentage of IOs were actually not required? And so basically, what is the overhead in terms of adding these gates?
So I'll split this into 2 sections. As a overhead point of view, we don't have any additional overhead because we can deal the shared wrapper cell will actually, the shared wrapper cell being is used for most of the ports. But there are few ports where, because of the limitations of the flows, there are ports which will have a dedicated wrapper cell. So for only those ports will have a dedicated wrapper cell, only few gates will be added, and then one additional plane shift enable being routed. Now coming to the what percentage of the ports, we will wrap freely for every port. Now there are few ports which is supposed to be explored. Those are related to clock ports and PLL ports, and then test mode entry ports. Except that, rest all of them can be freely wrapped.
All right, then.
One quick question.
You have a question. Go.
Yeah. So, is there any impact on the timing convergence or area due to the updated wrapper cell?
No. As you see in the updated wrapper cell, right? Everything is actually the scan enable being used actually. So during shift, the wrapper cell are being transparent, and during capture, we can handle that with the ATVG constraints. And now timing convergence perfect, there is no impact as such with this action.
Thank you. Thank you, Hanuman, and thanks Adit for presenting the Momento. Our next presenter is Padmaja. So this is on the paper Mutation Analysis and Model Checking Guided Test Generation for SOC Runtime Monitors. The authors are Surya Srinivasan and Vemuri Ranga, and Padmaja is here to present on behalf of them. So Padmaja is a PhD student at University of Cincinnati. She is working in digital designs and environmental lab, and her research interests are in hardware and trust security.
Hi everyone. Today I am presenting the mutation analysis and model checking guided test generation for SOC runtime monitors on behalf of the authors Surya Srinivasan and Ranganath Vemuri. So today, this is the agenda for today, and let me slide into the overview. Security specification, validation and assurance emerged as a significant concern in the system-on-chip design process. So the verification consumes 70% of the total design time in the SOCs, which showed the security specification, validation and assurance is critical for the modern SOC designs. Assertion-based verification has proved to be an ideal candidate for the pre-silicon specification and verification. And these assertions can be synthesized into runtime monitors for post-silicon validation too. And a directed test suite is required for online testing of these monitors, which I just mentioned before. So here is the problem statement. The lack of verification of synthesized assertion into post-silicon validation is one of the problem statement, and then the automatic generation of non-trivial test suite for the online monitoring, and yielding this test suite with enhanced coding coverage of the design. So in the scope, we will discuss few of the earlier research. First, the first SQED. In this technique, a quick error detection was combined with the bounded model checking, and then it is incorporating a symbol initial state, yielding the SQED methodology. Similarly, for Dr. Mishra and his and his group suggested a method for testing for the test generation for the pipelined functionality, for the pipeline stage, and produce the counter examples for the primary inputs. And this is the overall methodology. In this first, the goal of mutant generation is to change the design or the model so as to cause the assertion failure, and the machine code is extracted from the counter example, and then the alternative counter examples can be obtained using the constraint generation. And finally, the code is translated to a test program using the disassembler. So here we have, we can see here we have injected several faults, or these are the different faults that we can inject, or the mutant type of faults in system Verilog assertions, the stuck at zero fault, negated or flip mutation, and so on. Okay, so these mutations are introduced as Verilog macros like ifdefs or else, endifs, etc. And this mutation triggered the assertion, and then the Jasper goal gives a counter example to it, and these counter examples are translated into test programs or the RAM footprints to get, and these RAM footprints are again used as inputs to generate more tests and complex counter examples. So for the first iteration, the security assertions are verified with no constraints at all, and then the analysis is done where the instructions fetched by the processor for each simulation clock, and then the basic counter increments on each positive edge of the clock when it is introduced. So the system Verilog, they use the negated constraints as the assume constraints, and then the instruction opcodes are extracted. And here we show how the assume constraint is introduced into the design, where assume constraint is used, and these constraints say that we require a different counter example than the existing counter example, and where the instruction opcode OP1 and OP2 does not occur at the first and the fourth clock cycle. So if we have this constraint and we introduce this constraint, we get more complex counter examples, which can be further used to generate alternate test vectors. So yeah, like I said before, they give more assume statements, give impose more constraints, and then an alternate test vectors can be generated so that all the corner cases are covered using the counter examples. This is the algorithm for the test generation tool, and the input to the tool are assertion file, assertion label to verify mutations M1 through Mn, and violation trace as .vcd file, obtained through these mutations. The output of the tool is the test suite L. And here we have the first iteration where I equal to 1. We run the model checker with no constraints. And now for the subsequent iteration, the opcode and the counter values are extracted for the previous violation trace, and the negated constraint, the negated assume constraint here are added as the assume statements, and then the new test programs are obtained by running the newly constrained model added to it. So the finally the test suite is obtained that can be used as an input again to the SoC design. So this is the testing, how we test the runtime monitors. These assertions translated to runtime monitors are deployed with the mutated system on chip design, and the test suite generated is thus validated through the simulation or FPGA emulation. The mutation detection can be emulated through LED blinks, and for the FPGA, like as shown in there, what the test program we have here is blinking every LED for certain clock period. Depending upon the inputs that we provide from the RAM footprints. In some cases, the two mutation implementation for an assertion results in the same test program. These duplicate test results can be eliminated from the test suite and thus yield a consolidated suite. This is the test case SoC. This is an open RISC 1200 SoC, and it consists of RAM, source, open RISC 1200 processor, and timer, JTAG, and GIPO. This is a complex architecture which we try to use it for the mutation analysis. Consider a security policy for the SoC to show the overall flow of the methodology. For example, there is a security policy that I mentioned over there. If the CPU switches from user mode to supervisor mode, then either an exception should occur or the CPU should be in the reset state. This is translated to an SV assertion, and along with the signal description, which is shown in the we have this on the slide. So we then have the clock reset with the LSB SR register as a flag for user or supervisor mode for the SoC, and we have the supervisor write enable bit with the except start flag denoting a start of the exception mode. So all these are the signals that we try to follow. We try to gather for this specific security policy. To trigger the assertion that we just visited, we have used 8 different kinds of mutation. The first one is the stuck-at mutation, and then is the relational operator, and then the next is the arithmetic operator mutations, and flip, then the change in the variable, and then the change in the variable. These are the different types of mutations that we try to introduce. Alternate test programs for ASP. The figure is the violation trace for the assertion and with no constraints, and here is the test program generation, the test program that is generated for no constraints. And here we have introduced a violation. This is the violation trace for the negated constraint, and here is the which is yielding a test case program as shown in here. So here is the table, and the number of assertions that are written, and for each block of the SOC we have generated 8 type of mutations for each assertion. For assertion 1 we have 1 SM3 ohms, 1 CVM, as you can see here. Yeah. So, so these are the results, and these are the tests generated. The code coverage for the generation test comes up to 70%, as we can see in here. And the total coverage. The total coverage metric is computed using the coverage app in the Jasper Gold. It computes the branch statement and expression coverage for the SOC. The table gives the coverage metrics for OpenRISC 1200 processor, OpenRISC 1200 SOC with 1200 processor. The stimuli coverage identifies the code that is reachable, and the checker coverage represents the assertion completeness. So finally, the conclusion. The methodology used assertion directed mutation, mutation generation, and the model checking based test program generation. In addition, the constraints are introduced to generate a variety of test cases, thus building an elaborate test suite, ensuring through the validation of the monitors before deployment, with an improved code coverage, of course. And these are my references. Thank you.
Okay, well, thank you very much, and thank you for being so helpful in presenting in the absence of the authors. Get you in the picture.
Okay.
So before we conclude our session, I would like to thank our session chairs on behalf of VLSI Design Organizing Committee. So we thank Professor Adit Singh. And we will also like to thank Mr. Sriram Saraswatula for his help with organizing this session. Thank you so much.
Thank you, Jaydeep.
And one more request for all the student volunteers and presenters, if you are in the room, please join us for a photograph. Thank you. Student volunteers, please come. If you are here, please come. We'll have a photograph with you as well.
Kolkata, the city of joy. The prestigious conference, the VLSI 2024 Varshan, will try.
A very good evening, ladies and gentlemen. How are you all this evening? No response? No? Okay. A very good evening, ladies and gentlemen. I welcome each and every one to this very, very special and beautiful gala night. My name is Madhvi Reddy, and I'm going to be your host for this evening. So before we start, I would like to wish each and everyone present in this room a very happy New Year 2023. So would you like to even wish me back? Yes? Can I see those hands? Oh, that's lovely. So ladies and gentlemen, we are here to celebrate the past, enjoy the present, and look forward to the future. We are here to celebrate the continuous dedication and effort which each and every one of you have shown in the couple of years. We are here to grow much more bigger and much more stronger. So ladies and gentlemen, today, this evening, I want the energy levels which is there in the room to be really high. So can we make some noise for your own selves who are sitting in the room? All the ones from the front to back and the ones from the left to right. Can we make some noise? That's lovely. So right here on this stage, we are going to see some extraordinary performances. There are people who are going to come, take the awards, and they'll be going away. So when they are here taking the awards, I want each and everyone sitting in the room to make some noise because they deserve each and every bit of it. Apart from the awards this evening, there are going to be lovely performances coming up your way. And these are put up by none other than your own colleagues. Yes, you want to see the performances? Okay, so what we're going to do is, let us keep this very simple. I have 2 rules, which I always tell it to my crowd, is that it's very simple. Anyone who is there on this stage talking to you all, anyone who's coming to take the awards on this stage, anyone who's coming and performing on this stage for you all, what you need to do is give them a huge round of applause, make some noise, scream, shout, whistle, and make a loud noise. So that's the rule number 1. And the rule number 2 is whenever someone is coming on the stage and talking to you all, someone is coming and taking the award, someone is coming and performing on the stage for you all, you need to do is scream, shout, whistle, and make some noise. Yes? Is the rule very simple? Am I very clear? Yes? I think you guys didn't get it. Did you guys get it? There is someone already talking to you. Come on, make some noise. All right. So, ladies and gentlemen, everyone today I want, let the room go up crazy. Today, let us forget about work. Let us forget about your bosses when they come out with EOD. Let us forget all that. We're not going to have any deadlines this evening. Today, we are only going to enjoy, celebrate. Yes, are you with me? Are you guys with me? So what we're going to do is, because I can see the energy levels are pretty low, let us pump up the energy level in the crowd. Let's do that. So what we're going to do is, I want all the ones who are sitting down, if you can please stand up. Wherever you're sitting down, please stand up for a minute. Please do stand up. All the ones who are sitting down, may I request you all to please stand up? Yes. Everyone in the room, please stand up. And what we need to do is, you need to snap your finger twice. 1, 2. The only thing is, I have mic in one hand, so I'm only using one hand. You guys need to use both your hands, okay? So it's 1, 2, and one single clap. 1 single clap. 1, 2, 3. 1, 2, 3. 1, 2, 3. Come on. Can we do it as a team? So as I say, 1, 2, 3, you need to start. And there's a track which will be played for you all. So we need to match ourselves to a track which is getting played. Ready? Let me just come to you all. You are looking so amazing. I love your smile, sir. So, आपके smile के लिए I want to say something before the music starts. आपकी मुस्कुराहट ने हमारे होश उड़ा दिए. आपकी मुस्कुराहट ने हमारे होश उड़ा दिए. हम होश में आने ही वाले थे. आप फिर से मुस्कुरा दिए. All right, 1 second, please. Hold it. Okay, so the track is ready. What we need to do is, as told to you all, sir, may I request, आपके टांग दर्द हो रहे हैं क्या? Everyone in the room, only it's for a minute. I want everyone to please stand up. all the ones who are sitting down. So now, what we need to do is, we need to snap our finger twice and single clap, and we need to match ourselves with the track which is going to play. Can we play the track, please? Loud, loud, loud. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3.
Buddy, you're a boy, make a big noise, playing in the street, gonna be a big man someday. You got mud on your face, you big disgrace, kicking your can all over the place, singing, we will rock you.
Amazing. Sing.
We will rock you.
Great, go on.
Buddy, you're a young man, hard man, shouting in the street, gonna take on the world someday. You got blood on your face, a big disgrace, waving your banner all over the place. We will rock you.
Amazing song.
Sing it. We will rock you.
Go on, let's go on.
Buddy, you're an old man, poor man, pleading with your eyes, gonna make you zombie someday. You got mud on your face, a big disgrace. Somebody better put your bag into your place. We will rock you. Sing it. We will rock you.
Thank you so much. Please take your seats. Fantastic. Now, how do you feel? Is the energy levels up? Yes? You feel good? Yes, right? So, ladies and gentlemen, that's the energy which we want this evening from each and everyone sitting in this room. So, you all remember the 2 rules. Yes? You need to scream, you need to shout, you need to whistle, and you need to give a huge round of applause for all the ones who are going to come on this stage performing for you all this evening. So, ladies and gentlemen, we need to start this evening with one of the beautiful performances. It is a customary to commence an auspicious undertaking by offering salutations to Lord Ganesha, who is believed to remove all the obstacles for the fruitful completion of one's endeavors. So, ladies and gentlemen, please put your hands together for Pankaj Kumar and Surya Chaitanya for the Ganesh Stotram. Give a huge round of applause, ladies and gentlemen.
गणनायकाय गणदैवताय गणाध्यक्षाय धीमहि गुणशरीराय गुणमण्डिताय गुणेशानाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि गानचतुराय गानप्राणाय गानान्तरात्मने गानोद्धारकाय गानोत्सुकाय गानमत्ताय गानोत्सुकमनसे गुरुपूजिताय गुरुदैवताय गुरुकुलस्थायिने गुरुविक्रमाय गुह्यप्रवराय गुरवे गुणगुरवे गुरुदैत्यगलक्षेत्रे गुरुधर्मसदाराध्याय गुरुपुत्रपरित्रात्रे गुरुपाखण्डखण्डकाय गीतसाराय गीततत्त्वाय गीतगोत्राय धीमहि गूढगुल्फाय गन्धमत्ताय गोजयप्रदाय धीमहि गुणातीताय गुणाधीशाय गुणप्रवेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि
Thank you.
A huge round of applause, ladies and gentlemen. What a beautiful performance. So, ladies and gentlemen, now it's time that we kickstart the festivities of this evening. So now, may I have the privilege of having Professor Thomas Lee from Stanford University to please come and join us on stage. Before Sir joins on stage, let me just give a small brief about you, sir. Professor Thomas Lee received his degrees from MIT, where his 1989 thesis described the first CMOS radio. He established the Stanford Microwave Integrated Circuits Laboratory in 1994, after having worked at Analog Devices, Rambus, and other companies. He is a HOAM Engineering Prize Laureate and IEEE and Packard Foundation Fellow. Has won Best Paper Awards at CICC and ISSCC. Can we give a huge round of applause, please? And honoris causa doctorate from University of Waterloo in 2013. And the 2021 IEEE Gustav Kirchhoff Awardee. He was awarded a US Secretary of Defense Medal in 2012 for his work as director of DARPA's MTO and served on the board of Xilinx up to its acquisition by AMD in 2022. He continues to serve on the boards of several startups and maintains an active interest in the history of science and technology. I want everyone to please give a huge round of applause as I request Professor Thomas Lee to please come and join us on stage.
Can you hear me back there? Oh, yes. All right. Very good. Well, thank you very much for the kind honor of the invitation, and thank you for being here. We have a lot to celebrate, and let's see if I can get these slides working here. The theme tonight is actually about a coming, we'll call it a discontinuity in technology that's going to be occasioned by something that people are only now starting to acknowledge is something we should worry about. But we've been so busy trying to push Moore's Law one more generation that not all of us have quite gotten the memo. So first of all, this is the 75th anniversary of the transistor. This is the reason why we have jobs. So I think we should applaud the transistor, yes. And certainly a huge round of applause for the people in this room who have kept this ball moving forward for so many decades. So on the left is the humble first transistor. It's hard to imagine looking at that we could possibly have charted a trajectory to where we are today. I show that to my students, and they think I'm joking. They imagine that the first transistor must have been made the same way we make transistors today, in a very, very clean room with people hushed in silence, tending to their wafers. But no, the first one was built by hand and was every bit as ugly and beautiful as on the left. And today, now, the transistors, of course, are so small we can't even resolve them. We can only see them sort of at the package level. Now, all of you know this, but I'm not sure if you really have internalized it, because all of us in this room have always lived in an age of miracles. And when that occurs, you get used to them. You think that's the normal. But let's look at this. This is a logarithmic plot, and it shows a very steady progression of the number of transistors per chip. We're now at the 100 gigatransistors per chip scale. That's incredible. So congratulations, all of you, for making this happen. And we're not done. This line, you notice there's really no obvious inflection in the slope. It's been going like this for 50 years. It's quite incredible. It's growing at 1,000x every 20 years. That's incredible. Well, my students are so used to seeing curves that go up and to the right that they just sort of glaze over. You know, they ask, is this going to be on the midterm exam? And if I say no, they immediately go into a coma. So in order to get them to really internalize the miracle that this represents, I've shown them a fiducial where I plot the number of transistors that we produce in aggregate in all fabs on Earth every year, and I show them the number of ants on Earth. Notice that we're way above that. In fact, this year we're going to manufacture somewhere between 20 and 35,000 transistors per every ant on Earth. Within 5 years, we will be manufacturing annually a number of transistors that exceeds the number of grains of sand on our planet. Just kind of pause and think about that. So we're out reproducing an insect, and we will soon match parity with the number of grains of sand on our planet. That's amazing. And we're still going. Now, yes, so that's the good news. Now, this is a good news, bad news kind of presentation. So that's the good news. We set you up with and good, yeah. And then we kind of say, oh, how much longer can this party continue? Well, there are a couple of clouds on the horizon we should probably pay attention to. This is just one particular symptom of sort of the becoming victims of our own success. We've achieved what we've achieved by just going to massively greater scale, and we'll keep this up until something breaks. Well, the signs of not breakage, but at least things getting a little stressed at the edges is certainly here. This is just the number of parameters in typical machine learning models, and they've been growing at 25x per year. We've increased on aggregate a factor of 17,000 in just 3 years. That's clearly not a sustainable trend, but we're going to push it as long as we can. The energy associated, the electrical energy associated with the training and inference that this parameter growth implies is tremendous. It's no longer going to become a negligible parameter in our thinking. The training cost is also something we have to pay attention to. In 2018, BERT cost somewhere around $6,000, something that graduate students could do. In 2020, GPT-3 burned somewhere around $10 million, according to Microsoft, which should know because they own it. So we've gone from thousands of dollars to tens of millions of dollars in a very short time. That's a very steep slope, much steeper than any of the other curves that I've shown you. At the same time, we need to keep a track, not just of sort of these islands of activity and how they're scaling, but sort of get a picture of the overall landscape. And there, too, we see clouds on the horizon. Take Bitcoin as one potential example, an illustrative example of what's going on. The energy consumed by Bitcoin mining is pretty substantial. Now, it's hard to figure out exactly what that energy is. We don't have high-fidelity numbers. So I'm showing you 3 different curves, one sort of an optimistic estimate that's low, and a dire estimate, which is on the high side. But you can see that in raw orders of magnitude, it's in the order of 100 terawatt hours of energy. Now, to calibrate you on that, I'll show you how this lines up with the electrical energy consumed by the top 10 users of electricity in the world. So not surprisingly, the US and China are #1 energy consumers, and then you have a whole bunch of others on the longer tail. That red line there shows you Bitcoin, the pessimistic estimate, which may be an overestimate, but again, we're talking orders of magnitude here. So Bitcoin by itself could be consuming as much energy as, say, France, that one app. So if that is an example of where we're headed, we need to be a little bit concerned. This is clearly not sustainable globally. Now, the IEEE certainly has been paying attention to these signals, and just last year they put together this nice white paper, this decadal plan. It's constantly revised, but here's the 2021 version. The green curve shows the aggregate electrical energy consumed by all of our compute activity, all the data centers plus whatever else they could get their hands on. And it's growing at around 10x every decade, and it's been doing that for many, many decades. Now, I noticed that the green curve suddenly slows down its acceleration and levels off at around 10 to the 20th terawatt hours, joules per year. And I asked, what does this mean? Market dynamics will limit it. And they said, well, if the physics gets in the way, then we'll just increase the cost of computing until we modulate the energy down, or legislative incentives or disincentives will appear from governments worried about this, and so some saturation has to occur. As to where it flattens out, there was a rough, and this tells you that engineers were involved. They said, well, we'll allow compute energy to be as large as maybe 10% of the total global electrical energy production. If it gets much above there, then it's a serious problem, so we're just going to have to level it out there. Now, you see how soon that's going to occur. That's going to occur within about a decade, decade and a half, if we don't come up with some new ideas. And this is really coming along at a difficult moment in our technological history because we've kind of run out of lithographic scaling. So the number of magic tricks we have up our sleeves is at the lowest level it's been in the entire history of Moore's Law. And so just when we need it the most, we have fewer tricks at our disposal to moderate this problem. So that's a concern, but it's also, I think if you're an optimist like I am, it's a source of stimulus for innovation that will get us past this. Now, in terms of what sort of innovations could possibly show up, well, one of these is just to be smarter about how we compute. Max Tegmark's group at MIT has looked at some very interesting ways of deriving new laws of physics from experimental data using machine learning. To test out their ideas, they said, well, can we successfully discover laws that we've already discovered from the original data set that was used to discover them? So they decided as a challenge to their own group, they looked at 100 equations of physics in Feynman's 3-volume series of lectures on physics. Well, they tried once using sort of normal ML methods, and it was a disaster. It crunched billions and billions of instructions. It crunched all the data and came up with nothing. They stopped and they said, why is it so bad? Why is it doing so poorly compared to Galileo sitting in a room with a quill pen? They decided it was because they were asking ML to discover everything about physics, things that we already take for granted, like the general symmetry of nature, just aesthetic ideas that we've got embedded in our souls and our brains from billions of years of evolution, and that we already use to sort of pare down our problem set and our problem statement in a more efficient way. So they said, let's add symmetrical requirements to the ML algorithm and use that to prune it. It was incredibly successful. It rediscovered 300 years of physics, 100 physics equations from as few as 10 data points each in most cases. That's astounding. And using compute resources that are kind of equivalent to a modern gaming laptop, things that my students run around with all the day. So that's pretty impressive. They were able to cut the amount of energy required to do a higher fidelity compute just by framing the question in a way that was a lot more sensible than the way that we typically do with a lot of ML work. Another approach is to ditch the von Neumann architecture altogether and just take a look at the classes of problems that we find interesting or relevant to solve. One of these is just finding the minimum of something, the minimum energy, finding an optimum of some kind. Well, it turns out that nature does this all the time thermodynamically. If you take a ball and roll it down a hill, it ends up where nature wants it to end up. I didn't have to compute. So if I simply use that sort of minimum energy criterion as the goal, I can now solve that problem using fabrics other than algorithmically driven von Neumann machines. So there's a type of machine that's 100 years old. It's called the easing machine. Most Americans pronounce it Ising, but the Germans always get upset. The easing machine is a way of very, very simply taking a look at a complicated problem. All you have to do is define the constraints and let it relax into the final configuration. So your answer is just a result of waiting for natural processes to evolve. I won't go into a whole lot of detail in this particular example, but what you want to do is write a thing called the Hamiltonian, which for most engineers is just simply the total energy of the system, and you make the thing find a minimum energy configuration. So on the left, all the spins are pointing in one direction. That's the highest energy configuration. Eventually, they'll flip and flip and flip and flip at random until finally it ends up at a very low or minimum energy configuration. And you don't have to write any algorithms. You simply tell it what the constraints are, and after that, the system just finds the answer for you. In recognition of that class of problems being very, very important, because you can map it to a whole lot of other problems of relevance, the photonics people actually were very early to try to implement machines based on minimizing the Hamiltonian. So here's a photonics implementation of an easing machine, actually done by one of my colleagues, Professor Yamamoto, who's now with NTT Research Labs. And it's a physics tour de force. But my only complaint is I can't do this. I'm not a photonics person. I deal with silicon. If it's not silicon, I don't know what a material is. So my periodic table has sort of one column of atoms and a couple to either side. And that's it. Beyond that, I don't know what those other atoms to do. So we decided that the basic easing model was very interesting, potentially extremely relevant and powerful, but are there CMOS-compatible ways of doing what the photonics people are doing? And the answer is yes. We can use all sorts of fabrics that already physicists and other engineers have been looking at for a while. But now that the need is pressing, we can dust off some of these older creative ideas and really pay some serious attention to seeing whether or not they are going to be helpful in reducing the total energy of compute. And so just to give you one example, the one in the upper right-hand corner shows how you can build neural nets using oscillators. Oscillators are very interesting as compute elements because if you encode your data as phase, oscillators themselves are memories. So if you wanted the ultimate in a compute in memory fabric, there it is. The compute element itself embeds within its fundamental structure some notion of memory. So there's a way here to moderate the energy cost of memory accesses because you don't have to go out for the memory, it's right there. And today in compute fabrics, that's typically 1,000x savings in power. So already, if we do the right things, we might be able to pick up a good fraction of that 1,000, maybe a factor of 100 or something, and that forestalls the day of doom enough extra years before some other smart person comes up with a better idea and continues the game for that much longer. I haven't mentioned yet one of the most interesting compute fabrics of all, and that's the human brain. If you take a look at the stats of the human brain, it's really quite extraordinary. In green, I've enumerated some of the properties that we consider to be positives. The brain's 20 watts. That's very low. 20-watt data centers do not exist. A 20-watt brain can do an awful lot of good inference, can do a lot of pattern matching. 20 watts, that's an extraordinarily low amount of power. Some politicians even less. But overall, we have 20 watts for, yeah, it's a cheap shot, sorry, politicians. But But it got a laugh, so it served its purpose. But 20 watts is sort of nature's gauntlet. It's thrown down and challenged us to try to beat that, even try to match it. We're nowhere near being able to do these incredible things that human brains can do on a 20-watt budget. The comparison with what we're doing in silicon and what nature has already done is even more embarrassing for silicon people when you consider the brain does whatever magic it does using millisecond speed switching elements. Neurons are millisecond speed things. So think about this. If I were to describe it this way, silicon starts off with transistors that switch on picosecond time scales, a factor of 1 billion faster than the neurons in our brain. So already silicon is starting off with a factor of 1 billion advantage in speed, and yet somehow we lose the race. How is that possible? So what it tells me, really, again, putting the optimistic spin on that data, is that we don't have to come up with some quantum magic to start to do something useful. All we have to do is be less stupid. So, because what we're doing right now actually is, miraculous as it is compared to what we were doing, it's still pretty stupid compared to what nature has managed to evolve. 10 to the 14th synapses, the connectivity is very interesting. And Wernher von Braun, the rocket scientist, made a comment once that computers are the only, brains are the only computers that can be mass-produced by unskilled labor. So brains are producible by unskilled labor. Now, on the opposite side of the argument are people who say, yeah, but the brain is very fragile. You know, if I step on it, it's gone. So my answer is, well, then don't step on it. But that's true. It has a fairly high error rate. That is true. It's hard to replicate. So you spend a lot of time training one brain, and you can't immediately just copy it and make another one of those with the identical training. You're going to have to train it all over again, and you end up with a very, very low yield and a very large distribution of defects. It also only operates over a narrow temperature range, which is something that we always worry about in actual deployment scenarios. It would be nice if we could take the attributes of silicon, which seems largely not to suffer from the things on the right-hand side, and combine them with the attributes on the left-hand side and end up with a mashup that somehow is better than either alone. And that's sort of my optimistic take on all of this challenge. And now that we have this problem with about to hit the compute limits within lifetimes of most of the people in this room, we're going to find that our technology is going to be shaped by having to pay attention to the signal. Right now, when we notice it, soon it will become an urgent thing, and after that, it becomes the main driver of designs. It's going to happen quickly because that's exponentials. It goes from, well, it's sort of barely in my consciousness, and then all of a sudden becomes headline news as a catastrophe. That's where we are now. We're kind of at that knee of that curve. So pay attention to it. That signal is going to get louder and louder, and it's going to affect your daily work more and more sooner than you would expect. Because engineers hate limits. We hate limits. We love problems. In fact, we love problems so much, we'll create technology to create problems so that we can then solve those problems. And on it goes. It's a fantastic cycle of virtuosity for engineers. It guarantees prolonged employment. It's all of our jobs to create that future. So let's all resolve to make it a good one.
Thank you so much, sir.
I don't know if there's any Q&A that's supposed to take place or not. I'm happy to get off the stage.
May I request everyone to please give a huge round of applause, please. Now may I request Mr. Sanjay Churiwala, General Chair, VLSI Design Conference 2023, Corporate VP AMD, so to please come and join us on stage. And please hand over a memento to Professor Thomas Lee.
All right.
Applause, ladies and gentlemen, please.
Oh, thank you very much. Oh, my goodness. Oh, thank you very much. Appreciate it. Thank you so much. Oh, no, I got it.
Thank you so much. Now may I request Shri Palem Raju sir to please join us on stage. But before you join, sir, let me give a small brief about sir. Shri Palem Raju sir currently is the Managing Director of Advanced System and Package Technologies Private Limited, a company in the process of setting up a global standard semiconductor OS80 facility in Hyderabad, India. He has been a founding director of 2 companies in India in the semiconductor design services and IP development arena. Shri Palam Raju sir had served as the Union Cabinet Minister of Human Resource Development, Government of India in the Council of Ministers of Prime Minister Dr. Manmohan Singh, a vast responsibility that entails policy formulation for the entire education system in India, from school education to university education. Shri Palam Raju sir had served as Union Minister of State in the Ministry of Defense, Government of India in the tenure of 2006 to 2012, one of the longest serving ministers in defense. He had handled defense production along with other functions of the Defense Ministry. As a minister, he has represented the country in many international conferences and bilateral defense dialogues worldwide. He was proactive in strengthening the defense industrial base and had been the visible face of government, articulating the defense offsets policy in defense expos and at Aero India conferences. Mr. Palam Raju sir had been elected to the Lok Sabha thrice from Kakinada, East Godavari district of Andhra Pradesh. May I request everyone to please give a huge round of applause as I call Shri Palam Raju sir onto this stage.
Good evening, ladies and gentlemen. At the outset, I would like to thank Professor James Lee for a wonderful talk. And going by one of his slides, I want to say here is a guy with the less than 20-watt brain who's going to be speaking after you. I must thank you again for the enlightening speech for this very enlightened audience. And again, I would like to thank the organizers, the Government of Telangana, the IESA, and the industry for putting up such a fantastic show. I've heard that it was oversubscribed, very active participation at times like this, and it shows that the industry is very alive and kicking in this country and portends a fantastic future for the industry, not only for India, but for the world. So getting back to the topic, every conference like this is a reinforcer of the capabilities that the nation has and the industry has, and also opens our eyes to the opportunities that are coming. We all know where we stand today. The world is certainly in challenging times. India's population is going to overtake China's, and we've hit the $8 billion figure. And in a few years, we'll be coming up to the 9 billion figure. You know what that means? It puts a lot of stress on the resources of the planet, which we are already facing. Climate change is a huge impediment to growth. It increases our stress levels. We are seeing conflict happening all across the world. So it is for this generation to find solutions to lessen conflict, improve the quality of life on Earth. And I think that's what the real intent of conferences like these are concerned, which especially touch on emerging technologies. And just how the professor has shown us, we are going to see a rapid increase in the application of silicon and its products. We are seeing that in every application of our life today, and that's going to grow exponentially. Now, we are aware of the demographic dividend that a country like India has. They say that the median age of India right now is about 28 years. And 65% of the population is under the age of 35. And how are we going to use this demographic dividend? Are we going to use it for the betterment of the world? I think that would be a noble objective. Not only the betterment of the country, but for the betterment of the world. And that is where our knowledge power comes in. We've seen the presence of every notable industry in the semiconductor industry having their design outfits out of India. And the work that is happening out of India is being appreciated. We've become the workshop, the knowledge workshop for the world. And I think it is about time that we find solutions for our own needs. We've seen the deterioration in the quality of life in India. We're growing as an economy on one side, but I think the population that is going under the poverty line is also growing. So this disparity has to be addressed. I think today, as we sit here, it is obvious and very apparent that there is scope for improving the quality of life in every aspect of the country, starting from our education systems, to our transport systems, to our dwellings, to the way we do our livelihood, whether it's agriculture or manufacturing or services, to the way we deliver healthcare, to the way we deliver sops to the citizens all around the country. There is definitely scope for improving the quality of life in every sphere. But I wanted to also touch on one equally important aspect, which is the nation's defense. I think we are all aware of the challenges that we live in. And I think one of the subjects that I had handled has been in the Ministry of Defense in addressing our future challenges. Today, as we grow as an economy, it is imperative that we sustain the growth rate and increase the growth rate, not only to meet our internal challenges, but also to address our security challenges. A lot is happening in the country. We have a very sizable defense industry and very credible private sector playing an important role in the defense industry. Hyderabad and Bangalore have been very fortunate to have investments from Government of India in the space sector and in the Ministry of Defense, with substantial investments coming in here, which has helped grow the ecosystem of the small and medium sector that sustains both these industries, both in Bangalore and in Hyderabad. And there is an increasing application of semiconductors, emerging technologies in warfare today. We've seen what's happening in the conflict that's happening between Russia and Belarus, how drones and handheld weapon systems are making a difference in the way warfare is being conducted. I'm not an advocate of warfare, but I think when there is tension across borders between nations, deterrence capability is very, very important. And that's where I think the role of technology comes in. It is important to build strong deterrence capabilities to ward off any unsuspected challenges across the border. And there, I feel that the semiconductor industry and the electronics industry has huge opportunities in India. It is important for a country like India, which does not believe in taking the first step in offense, to build strong deterrence capabilities. And there, I would expect the industry to rise up to the challenge. And I also hope that IESA would take an active interest in, I know that you have several verticals addressing various opportunity areas. And I feel that IESA also should have a separate SIG probably for the defense industry in order to identify capabilities and also opportunities for the industry. There is a lot happening with Bharat Electronics Limited, Bharat Dynamics Limited, and there is a very, very vibrant private sector that is also playing an important role. I remember that when I was in the ministry, we were a very active proponent of the offset policy, which helped bring in a lot of capabilities and technologies into the country. And that is one area where industry can also look at if there are opportunities to work with, in the defense arena. Once again, I thank you all for this opportunity, and I am certain that tomorrow will end on a very resounding note. Glad to see the active participation of government, industry, a lot of students, I believe, who've been volunteering. And another suggestion that I would like to make to the organizers is to throw open maybe the late afternoon of tomorrow or day after, whereas when the conference ends, for students to come and see what exactly is happening out of Hyderabad and the capabilities that India is building. Thank you, and Jai Hind.
Thank you so much, sir. So I will request you to please stay back on stage. May I request Mr. Venkata Simhadri, General Chair, VLSI Design Conference 2023, CEO and MD, MOS Chip Technologies, to please come and join us on stage. And I will request you to, sir, please present the memento to Shri M.M. Pallam Raju, sir. I want everyone to please give a huge round of applause. So ladies and gentlemen, now we have seen the speech. Now it's time that we see something performance on the stage. Yes? So shall we see some performances coming up your way? So let us begin with the AMD team performing for you all. And the dance is Kuchipudi. Kuchipudi is one of the oldest classical dance forms of India. Started only by men in a village called Kuchipudi in Andhra Pradesh, way back in 10th century. Now from AMD's team, I would request Sri Ram, who's coming to perform this fusion of Varaha Avatara of Vishnu. I want everyone sitting in the room to please make some noise.
मूषिकवाहन मोदकहस्त चामरकर्ण विलम्बित सूत्र वामन रूप महेश्वर पुत्र विघ्न विनायक पाद नमस्ते मूषिकवाहन मोदकहस्त चामरकर्ण विलम्बित सूत्र वामन रूप महेश्वर पुत्र विघ्न विनायक पाद नमस्ते विघ्न विनायक पाद नमस्ते
देववरीतं वराहरूपं देववरीतं वरस्मितवदनं वज्रदन्तधर रक्षाकवचम् शिवसम्भूत भुवि संजात नम्बिदवगिम्बु कोडुववनीत ಸಾವಿರ ದೈವದ ಮನಸಂಪ್ರೀತ ಬೇಡುತ್ತ ನಿಂದೆವು ಆರಾಧಿಸುತ್ತ
What a fabulous performance, Sriram. It was amazing. I think Indian classical dance is the only form in which a man and woman look so graceful when they're performing. So can we hear it once again for Sriram, please? The next dance, which we're bringing for you all, is from the Bosco Dance Company. Bosco Dance Company is been performing nationally and internationally in many places. The next act is the Mirror Act, which is also being designed by them. So I want everyone to please put your hands together for Bosco Dance Company.
This is a Landlord World premiere.
They told him, don't you ever come around here. Don't wanna see your face हमको भी तू आजमाना जान जा एक बार मेरी बाहों में आ तुझको सिखा दूं है प्यार क्या और क्या है दिल का लगाना मैं दीवाना मैं दीवाना जाने ना दूंगा जाना मैं दीवाना ऐसे जाने ना दूंगा जाना यूं ना हमसे नजरें चुराना होगा हमसे ही दिल लगाना
Fabulous. So ladies and gentlemen, you all also will agree with me. This is a dance performance of one of its kinds. A huge round of applause for Bosco Dance Company. Thank you so much, guys. Thank you so much. So ladies and gentlemen, moving on with our first set of awards. And to give away the first set of awards, I will request Mr. Bruce Wire, Corporate VP, Microchip, and Mr. Chaudhry Musnuri, Chair VLSI Design Conference 2023, Senior Director, Microchip, to please join us on stage. This is the award which is given to an individual or team who has designed and implemented a successful and impactful design idea. So now we are presenting the awards for the runner-up and winner for design contest.
Check.
I would request you to please announce the runner-up for the design contest.
Yeah, before I announce the runner-up for the design contest, I would like to mention one thing. We've got about 75 submissions this time, and it was a very difficult, it was a lot of participation. It was very difficult for us to choose the runner-up and first prize. There was a tremendous amount of effort by all the participants, but since we need to choose two, first let's go with the runner-up. The runner-up contests are Syed Asrar ul Haq, Animesh Sharma, Anurag Gulati from IIIT Delhi. Would you please come up on the stage?
I request the runner-ups to please join us on stage. The runner-ups for the design contest.
The title of the design is, title of the runner's design is Design and Performance Analysis of Deep Learning Augmented Channel Estimation on System on Chip. There you go.
I want everyone to please make some noise for the runner-up of design contest here on stage.
So this also comes with an award of 15,000 rupees.
I would request Mr. Bruce Wire to announce our winner for the design contest.
The finalists for the design contest, the first prize winners are Vinay Raipati, Gogireddy Ravikiran Reddy, Sanampudi Gopal Krishna Reddy, Gandhi Ajay Kumar, Nandita Rao from IIIT Bangalore. Come up the stage. Their title was Hardware-Software Co-Design to Accelerate Brain Tumor Segmentation and Classification. Congratulations, guys.
So we are having here on stage the winner for the design contest. I want everyone in the room to please make some noise for the winners of design contest.
This comes with a 25,000 rupees prize.
So I want you to please keep the mic with you. So now, ladies and gentlemen, we are here to announce our lucky draw winners. Can we have the lucky dip box, please? Okay. So what you need to do is just mix it up well and pick up one. And the one's name would be announced. I want you to please identify yourself. You are there in the crowd. Please raise your hand if you're there in the crowd. And then you can claim it offline.
The name is B. Chandra Kiran Reddy, AMO 9160141082.
So you there? You can please raise your hand if you're there. All right. Okay.
All
so
right,
now, sir, we need to take one more lucky dip. Sir, if you can please do the honors.
The next lucky winner is Shyam, 852-757-9758. Shyam.
Is Shyam there in the audience? You're there, Shyam? If Sham is not responding, then we have to take another lucky dip.
Well, this one says Marvel 200.
So that I think we need to go for one more. Yes.
All right. This one says Pallavi synopsis.
We're going to read out the mobile number. It is 9901-38214. If this mobile number belongs to anyone in the audience, it is Pallavi from Synopsis. Okay, I don't think we do even have. So we move ahead with one more.
We have to go with one more. All right. This one is Vadla Shiva Prasad AMD. There you go.
Okay, you're the lucky one. So the two lucky winners can please, I'll take this from you, sir, can collect your gifts from offline. Thank you so much. Thank you so much, sir, for joining us. Thank you so much. A huge round of applause, ladies and gentlemen, for Mr. Bruce Wire and from Mr. Chaudhry Musnuri. So now, moving ahead with the dance performances. So now the dance team which is going to come here on stage is one of you all. That is from the Qualcomm team. As we all know, dance has no barriers. It is something which everyone can feel, understand, and definitely enjoy. But this group even believes that anyone can learn, that ABCD, anybody can dance. If we have passion for it, hold your breath. Let's welcome the one and only dance club of Qualcomm Hyderabad, the Q Nritya crew, presenting you a powerful, packed performance. Give a huge round of applause for the Qualcomm team.
Dhum ta na 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 dhum dhum ta na 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 dhum dhum agappa dhum dhum ta na na de ra na 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 dhum dhum agasa ragda dhum da 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 di ra na 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 da da gda dhum da da gda dhum da gda dhum 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 da na 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 de ra na 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 dhum gda na di ra na gama gama ma gama ba ma ga sa ni sa gda na di ra na gama gama ma gama ba ma ga sa ni sa gda na di ra na gama gama ma gama ba ma ga sa ni sa come on now follow my lead come on now follow my lead
అది రమ్మంటే రాదుర సలియా
the biggest party, boss party. Where is the party? Also, where is the party?
No bote me ku DJ no ku bombato party.
Where is the party? Also, where is the party?
No bote me ku DJ no ku patlu di party.
కొంచెం బీట్ మార్చండి రా బాబా.
Come on, everyone. Give a round of applause for this power-packed performance of Qualcomm. What a performance, guys. What an amazing performance. It was really, I think you guys took 2 days to learn it, right? Yeah, 2 days? Okay. So please make some noise for Qualcomm. That's amazing. So how is the energy? Good? All right, ladies and gentlemen, I'm going to say something. You have to tell me which language am I speaking. Kem cho? Majama? Which language is this? Gujarati. So, ladies and gentlemen, the one dance which rules India is the Dandiya, isn't it? So now, Bosco Dance Company is getting something masala on this stage from Gujarat. Please put your hands together for Bosco Dance Company.
केसरिया बालम आओ नी पधारो नी मारे देश रे पधारो नी मारे देश केसरिया पालम आओ नी पधारो नी मारे देश
Alaka buharu agano
जी आओ घूमरड़ी खिलबान पधारो सा घूमरड़ी खिलबान अलम थारो गुरर गुरर गुरगाव आसो मारो जीवड़ो घणो हिचकावे ओ घबरावे मन में भावे मारो पागलो भवन मन भावे चमक चम बाजे पायल बाजे बाई सा ढेरे चमक चमक घुघरा बाजे आओ सा घूमरड़ी खिलबान आओ सा घूमरड़ी खिलबान
कनक पीत की सर पे ओढ़ कर घूमर घूमर घूमे हाँ घूमर घूमर घूमे ओ ललक रीत सब जग की छोड़ कर घूमर घूमर घूमे भर के भोला वाले ठाट घूमर 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 घूमे घूमर घूमर घूमे रे भाई सा घूमर घूमे भारी सारे काया बोले ढोला जी की छाया होले मन का घूमर जब भी डोले सोनेपन में नीला करके ढोला वाले ठाट घूमर 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 घूमे घूमर घूमर घूमे रे भाई सा घूमर घूमे
आओ जी आओ रे घूमर खेलो आओ अपा साथ साथ घूमर सगड़ा खेलो आओ हर रंगो कुर्ती चूनरी पाए याते पहनो ओ झूमर 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 घूमर घूमर ते खेलो तेरा ढींगे ठाड़ी खेले सासू जी घूमरड़ी खेले ननद भौजाई खेले भाई सा घूमरड़ी खेले घूमे रे घूमे रे घूमे घूमर घूमर घूमे झूमे झूमे घूमे झूमे घूमर घूमर घूमे घूमे रे घूमे रे घूमे घूमर घूमर घूमे झूमे झूमे घूमे झूमे घूमर घूमर घूमे घूमर 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 घूमे घूमर 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 घूमे घूमर 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 घूमे घूमर 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 घूमे
झूमे गोरी घूमे गोरी चली कहाँ चोरी चोरी हवा से है बंधी डोरी रे हमारी सैया रे खिंच लई और डोरी ना डोरी बाजा झूमे गोरी घूमे गोरी चली कहाँ चोरी चोरी हवा से है बंधी डोरी रे शर्म छोड़ी थोड़ी थोड़ी नैनों की ये बोले छोड़ी शर्मी करने दे हम ढोलीड़ा हम बजे ढोलीड़ा हम बजे ढोलीड़ा हम बजे गज गज रे ढोल पे हवा ढोलीड़ा हम बजे ढोलीड़ा हम बजे गलियों में भागती सोती न जागती घूमती भागती रातों में चांदनी है चांद पीछे पड़ा गलियों में भागती सोती न जागती घूमती भागती रातों में चांदनी है चांद पीछे पड़ा
मारी रूप न तू अंबार ए चंदा सूरज तारा लिया गाए तारा गुण हजार खम्मा खम्मा मारी माँ बरड़ी तुझे जगदी तारण यार ए जोगी नाना डूंगर वाली चंडी चामुंडा बिरदाड़ी ए चंडी चामुंडा बिरदाड़ी
Ladies and gentlemen, please give it up for the Bosco Dance Company. What a lovely fusion of Rajasthani and Gujarati.
Great, thank you. So,
Before we get to the next stage, which is the awards, I just wanted to briefly talk about what we do, right? I mean, I'm sure all of you are waiting for who's won the prizes, but let's first talk a little bit about how long this process is and what goes on while we get through the whole conference, right? We start back in March, April timeframe. We got about 282 papers submitted over 14 different tracks, right? That's actually a huge number for the conference, right? And I've also heard the quality of the papers has gone up significantly. So it's actually a testament for everything, all the work that has gone in. I won't go through all the list of different tracks that we selected, but we actually picked these based on all the latest technologies that are important. The next one is important is that it's not only about from academia. In this conference, we got papers from both academia and industry. 65% came from academia, and there was a good number from the industry as well. We put together 24 different trackers to review these papers. We had about 280 reviewers set for this. Reviewers from all over the place, from India, from all international locations and all that. These people came together. There were more than 1,000 reviews that were done. All these reviews were collated. We found the best ranking papers and picked 54 papers to be presented at the conference here. We have gone through, I'm not doing the math here, but we have 18 more papers left to go, and that's tomorrow, right? And there was about 17 papers that were presented as posters, and that was a great session as well. So that's all the things that we did as a TPC team. And in addition to that, we also had about 11 invited speakers come in and talk about it. Right? So this is all the effort that has gone in from the technical program team to put together this conference on the technical side. Obviously, there's a lot more beyond the TPC that has done. There are many people who have helped in this effort, right? So I think that's what I wanted to talk about. Thank you.
Thank you so much, sir. And now moving on with our next set of awards. To give away this set of award, I will request Mr. Jaideep Kulkarni, Professor UT Austin, and Professor Usha Mehta, Fellowship Chair, VLSI Design Conference 2023, and Professor Nirma University to join us on the stage, please. So we are presenting the awards for the winner of poster segment. So it's already come out of the envelope. You need to announce the name.
So the paper ID is 103, a 105 525 megahertz integer n phase lock loop in indigenous SCL 180 nanometer CMOS technology. And the authors are Shivam Nigam, IIT Madras, Mukund Murali, Qualcomm, Harishankar Gupta, SAC, ISRO, and Saurabh Saxena, IIT Madras.
That's the name for the winner for the poster segment. A huge round of applause, ladies and gentlemen.
Okay, the name of the winners, the authors are Shivam Nigam, IIT Madras, Mukund Murali, Qualcomm, Harishankar Gupta, SAC, ISRO, and Saurabh Saxena, IIT Madras. If you are in the audience, please come to the stage.
If not, I would request Mr. Kalpesh Mehta, Senior Director from Qualcomm, VLSID 23, from Organizing Committee to please come and collect the award on behalf of the team. I want everyone to please give a round of applause for Mr. Kalpesh Mehta. Mr. Siddharth Rale from Organizing Committee, Senior Director AMD, and Mr. Shiv Govind Singh, Professor IIT Hyderabad, to please come and join us on stage to give away the next award, which is Naresh Mallipeddi Honorable Mention Award. A huge round of applause for the dignitaries who are coming on stage to give away the present the award.
Paper ID 136, author Sanjay Kumar Day, Intel, Mukul Sarkar, Sauri Brata Chatterjee, IIT Delhi.
So the award which we are giving away is for the Naresh Mallipeddi Honorable Mention Award. A huge round of applause. And this is the award to present for the winner of Nrpendra Nath Biswas Best Student. So I would request you all to please be in the center of the stage.
It's paper ID 108, automatic implementation and evaluation of error correcting codes for quantum error correction. Authors is Thomas Gruhl, University of Applied Sciences, Upper Austria, Christoph Pichler, Johannes Kepler University, Linz, Austria, Jürgen Fob, University of Applied Sciences, Upper Austria, and Robert Will, Technical University of Munich. Congratulations.
We are announcing the winner for Nrpendra Nath Biswas Best Student Award. And we have the winner. I want everyone in the room to please make some noise for the winner of Nrpendra Nath Biswas Best Student. Thank you so much, sir, and congratulations. Now to present the next award. Thank you, sir. I would like to call on stage Mr. Dasaratha Gude, Chair and CEO, Invacus and VLSI Design Conference 2023 Organizing Committee, and Mr. Srinivas Bairi, Senior Director, Intel and VLSI Design Conference 2023 Organizing Committee. A huge round of applause for the presenters coming on the stage to present the award for the winner of A.K. Chaudhary Best Paper. And request you to do the honors.
And the award goes to Paper ID 8, a portable, ultra-low-cost, multi-gas sensing system on module for wireless air quality monitoring network. Authors are Anamika Sharma, Sachin Divekar, Rajesh Zele, IIT Mumbai.
A huge round of applause for the winners of A.K. Chaudhary Best Paper. Can we hear it for the lady here on the stage? A huge round of applause, ladies and gentlemen, please. Thank you so much, Mr. Srinivas. And so I would request you to please stay back as we announce our lucky draw winners. Can we have the lucky dip, please? Here, give it to me. You need to mix it really well so that we see who's the lucky dip winner this evening.
I swear this is just coincidence. The winner is Satyanarayana at Intel. Is he here? Satyanarayan from Intel. We have phone number. Should we call or take the next one? If anybody in the crowd, Satyanarayana from Intel, please raise your hands. Did you take Intel because I was here? Okay. I think you have Semiconductors. Yeah. The winner is Nitesh Maurya from Semiconductors. Semiconductors, Nitesh Maurya. Can you raise a hand?
Oh, he's there. He's identified himself.
Nitesh, you are here?
So, you can claim it offline. Yes, sir. One more.
And the next winner is Anshul Verma. Anshul Verma in crowd.
There we have. So he's also identified. That was very quick. Thank you so much, sir. Thank you. I'll take this. Can we hear it for the lucky draw winners, please? So now it's time that we start seeing some more performances coming up. So now calling the AMD team to come on stage to perform. TAMD will be presenting a performance showcasing different dance forms. So I want everyone in the room to please make some noise for the AMD team. We're going to synchronize the dance move with the music beats.
¿Quién eres tú? ¿Dónde has estado? He removido cielo y tierra y no te encontré. Y llegas hoy tan de repente y das sentido a toda mi vida con tu querer.
ना मैं समझा ना मैं जाना जो भी तुमने मुझसे कहा है सेन्योरिटा, मगर फिर भी ना जाने क्यों मुझे सुन के अच्छा लगा है सेन्योरिटा.
No desvíes la mirada, quédate cerca de mí.
मुझको बाहों में तुम घेरो, समझी ना सेन्योरिटा.
चाहत के दो पल भी मिल पाए, दुनिया में ये भी कम है क्या, दो पल को तो आओ खो जाए, भूले हम होता हम है क्या सेन्योरिटा. सुनो सुनो सेन्योरिटा कहते हैं हम क्या.
ఇంతకన్నా మంచి పోలికేది నాకు తట్టలేదు గాని అమ్ము, ఈ లవ్ అనేది బబ్లు గమ్ము అంటుకున్నదంటే పోదు నమ్ము. ముందు నుంచి ఎందరన్న మాటే గాని మళ్ళీ అంటున్నానే అమ్ము, ఇది చెప్పకుండా వచ్చే తుమ్ము ప్రేమ నా పలివు నన్ను నమ్ము. ఎటగానే ఎదురు చూపుకి తగినట్టుగా నువ్వు బదులు చెబితివే. అరి దేవుడా దేదనే కలోపటే పిల్లడాంట దగ్గరై నన్ను చేరదీస్తివే. బుట్ట బొమ్మ నన్ను చుట్టుకుంటివే, సిందటికే అట్ట
Amazing performance by AMD. They've actually synchronized it very well with the dance steps and the music beats. Yes? Do you agree with me? If we actually had time, I would have learned 1 or 2 steps from you all. If I really had time, I would have learned some dance moves from you all. All right, I want everyone, please make some noise for AMD, please. Lovely, guys, lovely. Thank you so much. They've actually been eagerly waiting backstage कि हमारा कब आएगा number, कब आएगा करके. And at last उनका number आ गया. Now, ladies and gentlemen, I'm going to call the Bosco Dance Company, but they're coming up with one of the performances which has bagged Golden Globe Award. What's the number? Which is the song we are talking about? Yes, from Triple R, Natu, come on, please give it up for Rajamouli sir for coming up with such a beautiful movie and a very beautiful original song. So calling on the Bosco Dance Company.
Are you okay?
कोई बात नहीं.
Oh, I am so sorry. Don't worry, it'll come out. I'm so sorry.
Oh no, it's completely fine.
Every damn wanker thinks he can dance. What do you think of yourself, huh? You country oaf. Look at them.
Wait.
Look at all these brown buggers. What do they know about art? About finesse? About dance?
Not salsa, not flamenco, my brother.
Do you know
Desi Nach?
What's Desi Nach?
बैल जैसे धूल उड़ा के सींग उठा के तुम भी नाचो, बाज जम के ताल ढोल बेटा राजू उड़ के नाचो।
हीरो से भी तेज कोई कर सके जो बेद नाचो,
अस्तबल में घोड़े जैसे बाग डोर छोड़ नाचो। मिट्टी जो रोट मोटा मिर्च खा के ऐसे नाचो। हाँ जा छोरे,
हाँ जा गोरे,
हाँ जा छोरे नाचो 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 वीर नाचो 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 यार नाचो 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 कच्ची कैरी जैसा खट्टा नाचो 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 बिच्छू काटा लागे ऐसा नाचो। ऐसे शेर हाथी नाचे
देखो दिल का ये मेला यार अपने साथ नाचो
एड़ियों के जोरों पे तुम धड़ाका देसी नाचो
पसीना माथे का चमके दमके ऐसे नाचो
हाँ जा छोरे हाँ जा गोरे हाँ जा छोरे नाचो 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 वीर नाचो 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 यारा नाचो 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 आगो वारा राग छेड़ा नाचो 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 उसने चक्रा लागे थी नाचो
गाँव है रेला ऊंचा पाँव यूं पटका है ये देसी मेला कैसा रहा यकी नाचो 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 नाचो
अरे धूम धूम थिरके जा पाँव में जान जगा धुमक धुमक नाचे जा दुनिया हिला दे सारी नाचो नाचो नाचो
नाचो
I think हम सब नाचना चाहते हैं मगर प्रोग्राम खत्म होने के बाद. So I want everyone to please make some noise for Bosco Dance Company. What a performance, guys. So moving on with our next set of awards and to give away the User Design and Track Honorable Mention Award from Academia, I would like to call on stage Mr. Sashi Reddy, VP Qualcomm and Organizing Committee, and Mr. Subhash Chintamaneni, Senior Director, Micron and VLSI Design Conference 2023 Organizing Committee. Please come and join us on stage to present the User Designer and Track Honorable Mention Award from Academia.
Okay, this is for the special mention for the paper, for the track paper from Academia. It's a novel adiabatic puff for portable devices. Authors Vishnu Bajuri, Nalesh S. and Kala S.
That's the award for the User Design and Track Honorable Mention Award from Academia. I want everyone to please give a round of applause. Congratulations. Thank you so much. Congratulations. So I want you all to please stay back. To give away this award is given to an individual or team who has most innovative, developed and implemented circuit or system. To give away the award for the best user designer design track, I would like you to announce the name.
The best paper, actually this is tying into a lot of things which is related to automotive. This is for physical implementation of functional safety features in automotive chips. Shashikiran Srinivasa and Badri Ramasubramaniam from Marvel, I think. Yeah.
So this is the award for the best user design track. And the winner is already announced. Congratulations, and thank you so much, sir, for joining us on the stage. Now, to give away the Best Exhibit Award, I would like to call on stage Dr. Satya Gupta, Steering Chair, Executive Chair, VLSI Committee, and Mr. Srinivas Raju, CEO, Pi Square, to present the winner for the Best Exhibit.
Best Exhibit Award goes to AMD. Somebody from the AMD team to come and collect it.
AMD.
AMD team to come and collect it. Yeah.
Everyone, come on, put your hands together for AMD as the winner for the Best Exhibit.
Rohit Gopal Krishna, Raveen from marketing team. Okay, then I'll collect it.
Congratulations, AMD.
Thank you. I had nothing to do with it. Our marketing people did it. And when we got the booth,
Dr. Satya.
Sorry.
Sir, I'm so sorry, sir,
Sorry.
to cut you off. I want you to please stay back.
So I had nothing to do with it, right? I just came in to collect the award because Aditya didn't come in time. When we got the booth, our marketing person, Mukesh Bajpayee, he said, "Sir, इस बार booth award AMD को मिलेकर आएंगे." Okay, and he has done it.
Congratulations, sir. Now it's time that we announce our lucky draw winners. Dr. Satya, अच्छा मिला ये उसे.
Robert B. Susai. Is he here? Robert? Robert.
Mr. Robert is not there, so he's not showing off.
Prateek Kumar from ISC Bangalore. Prateek Kumar.
Okay,
Yay!
he has showed up. Okay, I'll take this. And yes, sir. There need to be one more, but this lucky draw is sponsored by Western Digital. So I want you to please take one more lucky draw, sir.
Again. We are very lucky. Again, it's Satyanarayan from Intel. Okay. So what I'm going to do is, my name is also Satyanarayan, and I'm ex-Intel, right? And once Intel is always Intel. So I'll take it.
So hasn't showed up.
Charles? Anybody named Charles? 99859-8181503. So your mobile number is public now.
So girls will start reaching out now to.
I think last we can close it. नाम भी पढ़ने को नहीं आ रहा. Diksha. Diksha, right? DHIKSHA, right?
So there are a couple of names which are not really written properly.
Diksha.
Diksha has showed up.
Yeah.
All right. Thank you so much, sir.
Thank you so
Thank
much.
you so much for joining us. I'll take this. So, ladies and gentlemen, bringing up for you all one very beautiful performance. But before that, I would like to say something. हम अपने जान के दुश्मन को भी जान कहते हैं. हम अपने जान के दुश्मन को भी जान कहते हैं. और इसी खूबसूरत मिट्टी में जहां हम पैदा हुए हैं, हिंदुस्तान कहते हैं. तो एक बार जोरदार तालियों के साथ I'm going to call Bosco Dance Company for a very beautiful number which Mr. A.R. Rahman has given music. Jai Ho! Put your hands together for Bosco Dance Company.
आजा आजा जिंद शामी आने के तले आजा जरी वाले नीले आसमाने के तले जय हो जय हो आजा आजा जिंद शामी आने के तले आजा जरी वाले नीले आसमाने के तले जय हो सच्ची मैंने जान कमाई है न
भी थोड़ी अदा थोड़ा अंदाज है ऐसे हैं चाहे वैसे हैं अरे जो भी हैं जैसे हैं खुद पे हम नाज है जाने ना हमको ये जमाना चाहो तो हमको आजमाना यारबाज हम चालसाज हम इश्कबाज दिल वाले कहते हैं हमको प्यार से इंडिया वाले छू लेते दिल के तार से इंडिया वाले हर जीत छीन ले हार से इंडिया वाले दुश्मन के छक्के छुड़ा दे हम इंडिया वाले दुश्मन के छक्के छुड़ा दे दिल पे सबको नचा दे
जय हिंद भारत माता की Thank you so much. A huge round of applause for Bosco Dance Company, please. So, ladies and gentlemen, moving with the next set of awards, which is the Lifetime Achievement Award. This award is given to an individual who has made significant contributions to the field of VLSI over the course of their career. Let us hear a few words about the Lifetime Achievement Awardee from Mr. Naveed Sherwani, CEO at Rapid Silicon, a world-renowned chip expert, author of several books, serial entrepreneur, and academician.
Yes, absolutely. So first of all, thank you very much for including me in this very prestigious ceremony. It's a great honor. And it's a great honor to be part of this award for Dr. Satya Gupta. I met Satya in 1989 when he was a graduate student, and he was his advisor asked if he could have a room to sleep in, because at that time in Chicago they didn't have enough room. So me and Satya slept in the same room, and I got to know this incredible person who I spent then many years, over 2 decades working with him. And then when we started a company called Intel Microelectronics together in late 90s, went on to become a very successful company. And then Satya and I started a company called Open Silicon. And Satya took on the task to create a design center in India. And then he led the team with Chitra, Ravi, and many other amazing people, and did hundreds and hundreds of tape outs day after day, actually put India's name all over the globe for becoming a tape out center of the world. Satya went on to do many other great companies. His passion is still there, and he has actually 2 passions. He has one passion is to do something for chip design, VLSI design, but his other passion is to do something for India. And he has spent his entire life doing both of these things, and he still has the passion. Last week, I had a call with him, and he wanted to start a new company about RISC-V and processor design and things like that. So in the end, I would like to say that I do not know of any other person who is more who should be more deserving of lifetime award than Dr. Satya Gupta. I think Satya should be very proud of his accomplishments. I am very proud to be a brother and partner of Satya, and I think India should be very proud of having a son like India. Thank you very much. Congratulations to Satya.
Now to give away the Lifetime Achievement Award, I would like to call on stage Professor Thomas Lee from Stanford University, Mr. Sanjay Churiwala, General Chair, VLSI Design Conference 2023, Corporate VP, AMD, to please come and join us on stage to give away the Lifetime Achievement Award.
So Satya sir, please be seated. No hurry. Okay. I have the mic. I will need to speak. Okay, sir. So we have a special guest here. Let's see if the special guest can walk in. Do you have the special guest here coming in? Do you have a special guest coming in? So I now request Madhurima ma'am, lifetime partner, to escort Satya Gupta, the awardee for Lifetime Achievement Award. Madhurima ma'am.
So that was the surprise element of this evening. Everyone, please give a round of applause for Dr. Satya taking away the Lifetime Achievement Award. So having more than this, how was the surprise which came to you?
Behind it now. Thank you so much, Sanjay. Thank you, Sanjay. Thank you, sir.
So this is not the end. This is the beginning.
What do I do now? Okay, I would like to say a few words. So my journey for VLSI Design started when I graduated from BITS Pilani in 1983. And instead of taking an offer from TCS, I decided to join IIT Delhi as a junior research scientist. And the first person I would like to thank is Professor Anshul Kumar. A lot of people know him. He has been an integral part of this basically conference, recently retired. So he introduced me to the field of VLSI design. Very early, he had a dream of building a silicon compiler all the way from HLS to layout. I think we have not achieved that dream till today, but he had the courage of doing that in those days. Throughout the journey, my career is basically because of the people I worked with. So starting my PhD advisor, Dr. Mohammad Zubair. Then at Intel, I had some wonderful colleagues and guides. So Naveed was one of them. Another person I would like to mention is Craig Patterson. Wonderful engineers. At age of 75, also he is just doing some incredible work with the technology. 2001, I moved to India, started the first chip design activity at Intel India, and that's where we started the Intel Microelectronics. Some of the wonderful people joined. I think a lot of colleagues, some names I would like to take, who basically I called upon them and they joined me, moved back from Portland to India. Sumit Agrawal, who became the VP at Intel. Sachi Vardarajan, who became basically later on MD of Qualcomm. Chitra, who was basically been part of all the startups which we did together. Ravi Srinivasan, Anuradha Srimas. We had a wonderful team at IME, and then we started Open Silicon, which Naveed mentioned, and I think I've worked with almost everybody in this room, be it EDA partners, be it basically technical guys and so on and so forth. Obviously, Madhurima was there with me, and just a small incident when our son Abhishek was young. One day he came and asked, what is picosecond? How big is the picosecond? So Madhurima explained, picosecond is very, very, very small, basically unit of time. And then he said, why two of you keep fighting over picosecond all the time, right? That we are not meeting timing for picosecond, and all the time on the phone I keep hearing about picosecond, right? So having somebody with you who knows more about chip design and being always there for basically helping in all the endeavors which we did. Certainly, Professor Vishwani Agarwal and other people. One more name I would like to take who has been a mentor and guide to me. And together we started the foundation of India Electronics and Semiconductor Association. Rajendra Khare, visionary, first chairman of ISA, founder. He has been always been a guide and mentor to me and so many of other people. As part of my work in the VLSI area, I think a lot more to do. I have two more things or two dreams which I want to accomplish with the help of you. In next 5 years, we want to have 1,000 fabless companies in India. And the way to achieve is to democratize the fabless industry so that we have a fabless company in every part of the country, and to put it into some concrete term, if we have one fabless company from each district of India, then we have about 750 districts in India, then we can achieve this dream of 1,000 fabless companies in India. Second thing which I want to do is that take the VLSI education to the grassroots. And at least 100 colleges in next 2 years, we want to start the BTech program, undergraduate program in VLSI and electronics, so that we can get this subject introduced to our kids very early, catch them young, catch them bright, and that's what will shape the destiny of India and the VLSI design. Thank you so much, everybody. And last but not least, I want to thank the VLSI Design Organizing Committee for putting a wonderful conference. I think this is one of the best conferences. I would like all of them to stand up and basically get recognized. Or better, you come here. Sanjay, come. All of you. So Hyderabad conference is started.
I want everyone to please give a round of applause to the whole team who has done a fabulous job.
Thank you, thank you. Party abhi hua.
Can I see some more people making some noise here? Give a huge round of applause to the whole team standing here on this stage.
Sumit, advisors are also welcome, right? Viresh,
Satish, Mustaq.
This is the team which has put the incredible conference for putting India on the map of VLSI. Academic, industry, government, we covered everything basically during this conference, and probably this is the most impressive conference in the history of VLSI design. So thank you all the team on behalf of all of us.
So this is the whole team which has put on the hard work the whole last 3 days, and 1 more day is left. So please give a huge round of applause for the back end, the whole team which has been working to see that everything goes well and the successful event which you have seen this evening. Thank you so much, team, and congratulations for everything. So your Lifetime Achievement Award I am taking along with me. Here you go. So you're too young to take the Lifetime Achievement Award, sir. But yes, your work in the industry has exhibited everything, I guess. You are very young, sir. Thank you so much. Thank you. Now, ladies and gentlemen, moving on with our next award, which is a Special Recognition Award. This is a Special Recognition Award given this year to Mr. Saurabh Gaur for his outstanding contribution in formulating and implementing semiconductor and electronics manufacturing schemes during his tenure as a Joint Secretary, Ministry of Electronics and Information Technology. To give away the Special Recognition Award, I would like to call on stage Dr. Madhav Pulipeti, CEO of Photonics Corporation and Organizing Committee. I would like to call Professor Ajit Singh to please come and join us on stage to give away the Special Recognition Award to Mr. Saurabh Gaur. I want everyone to please give a huge round of applause to Mr. Saurabh Gaur. So, on behalf of Mr. Saurabh Gaur, I would like to call on stage Mr. Venkata Simhadri to please come and accept this on behalf of Mr. Saurabh Gaur. Saurabh Gaur. Give a huge round of applause, ladies and gentlemen. It's a Special Recognition Award which is being given to Mr. Saurabh Gaur, and Mr. Venkata Simhadri is here to accept the award on behalf of Mr. Saurabh Gaur. Congratulations, sir, and thank you so much for joining us on the stage. Now, may I request Mr. Preet Yadav, R&D SOC Technical Program Manager, NXP Semiconductors, to come on stage and announce the IEEE Asia Pacific Conference on Circuit and Systems 2023.
Good evening, my dear friends. I'm Preet, and as I said, I'm part of IEEE Circuit and System Society. As you can see on our right, under the technical sponsors, CAS, which is Circuit and System Society of IEEE, is one of the technical sponsors for VLSI 2023. But not only this year, CAS has been a technical sponsor for this conference from decades now. And I'm here to talk about one of the CAS conference, which is coming to your own city, Hyderabad. To start with, first of all, I would like to thank VLSI 2023 team for giving Circuit System Society this opportunity for the outreach for this particular conference. So as you can see on the screen, this is the 19th edition of Asia Pacific Conference on Circuit and Systems, which would be held later November 2023 in your own city of Hyderabad. So this conference would be coming to India for the first time ever in last 2 decades. So on the one side, certainly we have to wait for 2 decades, but on the positive side, we're pretty happy that this conference is coming to India. So I'll quickly, briefly take you through this conference. So this conference, along with, would be collocated with Asia Pacific Conference on Postgraduate Research in Microelectronics. This is an initiative by IEEE Hyderabad section, but this would be jointly held with all other CAS sections of India, which is Bangalore, Delhi, Kolkata, Kerala, along with Hyderabad section. So as you can see, the theme of this conference is safe, secure, smart circuits and systems for a sustainable society, which is covering almost all the major aspects which we as a circuit or system engineers are working on. You might have seen already the call for paper, which is there in your pen drives, which is covering all these greatest technology topics. These are the submission timelines. So with this, we welcome you all to please give the same love, affection, and your contribution to the conference as like VLSID to take forward India's name, not only within our geography, but to the Asia Pacific and the global region. We have a quick video which will talk about this conference. Can we have the video, please? Thank you, and I'm sorry for this lag between the audio and the video. I hope we'll fix it up by November 2023, and hope to see you back here in the same venue. Thank you.
Thank you so much, sir. Thank you so much, sir. Now I would like to call Ms. Chitra Hariharan, Engineering Strategy Head, Intel and Organizing Committee, to announce International Symposium on VLSI Design and Test 2023.
So much. Team, I think VDAT 2023 does not need any introduction, right? VDAT 2023 is a sister conference for this conference, VLSI Design 2023. This time, VDAT 2023 is going to be held in BITS Pilani, and the dates are, can I have the PowerPoint, please? September 29th to October 1st. This is going to be a 3-day symposium. Last time this was held in IIT Jammu. This time it's going to be held in BITS Pilani, and let's make it bigger and better. Look forward for seeing you all there, folks. Thank you.
Now I would like to call on stage Professor Hafizur Rahman, Indian Institute of Engineering, Science and Technology, Shibpur, and General Co-Chair VLSID 2024 to announce VLSID 2024. So welcome, sir.
Good evening. In semiconductor industry leaders, academician, researcher, and government personnel. We welcome to the 37 International Conference on VLSI Design and 23rd International Symposium on Embedded Systems. So, theme is VLSI meets quantum, AI and quantum for cyber physical system. And the date is 6th to 10th January 2024. Venue is ITC, Royal Bengal, Kolkata. We have a small video for giving a glimpse of Calcutta and VLSI Design 2024.
Welcome you all to the VLSI Design 2024 at Kolkata, the City of Joy. The prestigious conference, the VLSI 2024 version, will try to focus upon very important areas of VLSI design and embedded systems and try to involve the leading people from industries, the academia, startups, researchers, students, and many more. The theme of VLSI Design 2024 is VLSI Design makes AI and quantum computing towards cyber physical systems. And as we all know, the cyber physical systems are the major drivers of most of the applications in the present world. And we hope that the tracks and the components which will be discussed during the sessions of this conference will surely lead a lot of research ideas, a lot of novel industry designs and practices. I once again welcome you all to the city of Kolkata and to participate at the VLSI Design 2024, which I hope will be a fascinating experience for all of you. Thank you all.
Good evening everyone, announcing the call for free part of VLSI Design 2024. The program will consist of several tutorial sessions for the first 2 days and the main conference for the last 3 days. We have planned to include in the VLSI Design 2024 program visionary talk by eminent experts, several keynote speeches by eminent experts from industry and academia, industry forum talks, design contest, student design contest, hackathon on VLSI and embedded system, talk on women in engineering, startup forum talk and contest, highlight of the academic and research activities by Indian academics. I hope the VLSI Design 2024 will be great success with all of your support and help. So with this, I welcome you all for the VLSI Design 2024 in Calcutta, the City of Joy, from 6 to 10 January.
So we have opened the call for papers. Now researchers are requested to plan for submission in VLSI 2024. Finally, I am earnestly requesting the industry leader, researcher, academician, government body to join the VLSI Design 2024 scheduled to be held at Kolkata during 6 to 10 Jan 2024 to make it a grand success. Thank you very much for your patience.
Thank you so much, sir. Now may I request Mr. Srinivas Berry, the organizing chair of conference, to please come on stage and deliver the word of thanks.
So we were originally expecting 700 people audience, and we have 1,560 total numbers today and yesterday. We all are engineers, so we believe in quantitative data, and based on the numbers that we have, 700 versus 1,560, I would not even call this as a 100% successful event, but I would call 220% successful event. First of all, I would like to thank VLSI Society of India. The credit goes to all of you. I'd like to thank VLSI Society. We'd like to thank VLSI Society of India for trusting us and allowing us to host this event in Hyderabad this year, and I hope we did full justice to that. I would like to thank Ajay Naini and Venkat Simadri for spearheading and advocating to bring this event to Hyderabad after 6 years and making it a grand success, 220. Thanks Ajay and thanks Venkat. I would also like to thank our esteemed guest of tonight, Professor Thomas Lee, who traveled all the way from Stanford to give an insightful speech tonight, and Mr. Pallam Raju, who's been there since the first hour, taking time out of his busy schedule and being with us, and is still here. Thank you, sir. Thank you for being there. I would like to thank Government of Telangana, especially Rajesh Ranjan, who's been there all the time. I personally had 5 meetings with him, one-on-one, just for this event. He's been our backbone and given full support for this event. I'd like to thank all the speakers, sponsors, delegates, and everyone who supported this event. It was a selfless act from everyone. All the students, a lot of people have traveled not only across India, but there's a lot of people who traveled across the world. So thanks everyone. I would also like to thank volunteers and organizing committee. It's a true selfless act. I know they worked round the clock, especially the last 15 days. People have not seen their families. They are sleeping here, working all the time here. So thank you all the volunteers and organizing committee. I thank all the judges and juries for your due diligence. I would like to thank Mark 7 for doing the excellent event management. I would like to also thank Qualcomm and AMD performers. They did an excellent performance tonight. Thank you, thank you. I know you had a lot of work last 1 week and you are practicing after the work here, so thank you. And I think you really did give a good competition to Bosco team too, right? Thank you. I'd like to thank Bosco team for their wonderful performance. All our people who were sitting on the first and second floor, I could see that their legs were shaking. They really wanted to come on stage. Few of us had to hold them back, right? So thank you. I'd like to thank the man of the gala night, Suman. He's the man who made this evening so interesting and excellent, outstanding thing. He's there last 15 days. He's been working. Suman Tumireddy from AMD. He's the man who put every minute, right? Every minute of this event. Thank you, Suman. Thank you. Without you, we could not have this gala night. Thank you. Thank you, man. I would also like to thank Cloud Portal. This is a company with only women entrepreneurs, and they did this event, the whole graphic design, you see all the things and all the cards that you see, they did this with real selfless act. They did it as a volunteer activity for us. They didn't charge us. And it's a company from complete women entrepreneurs. So I really, really thank Mr. Cloud Portal. Thank you. Thanks, ma'am. We really appreciate that. Thanks. I would like to thank Madhvi Reddy also being the host tonight. And last but not least, I would like to thank all the audience. You were very active, very engaged tonight, and hope you had a lot of fun. Hope whoever has not had dinner, we have dinner. Enjoy the evening. And we have load full of contents tomorrow, and we'll start the session exactly at 9 a.m. tomorrow. We got today late, but we'll start the session tomorrow exactly on time. And I apologize if I forgot somebody's name. And thank you, and hope you'll enjoy tomorrow's day too. Thank you.
Thank you so much, Mr. Srini. Ladies and gentlemen, with this, we have come to the end of a very, very successful event. This end only marks the beginning in the life of each and every one of you. Here's to many, many more years of success, dedication, and hard work. Ladies and gentlemen, thank you so much for taking out time and gracing this occasion. Please do take good care of yourself. This is Madhvi Reddy signing off. Good night. Shubh Ratri.